We are now live on YouTube.
Good morning, everyone. Welcome to the first Greek ACM Winter School on Fairness in AI. I'm Evi Pitoura. And I'm a professor at the University of Ioannina in Greece. And together with Yuli Kutrika, who is a research director in Athena Research Center in Greece, and Irini Douci, who is a professor at the Freie Universität in Berlin. We are the organizers of this winter school. Since we wouldn't be able to meet you in person, let us at least share your name and welcome you again. So I will leave the slides on for a few seconds for you to read each other's name and spot yours. Welcome. So in this short talk, I will say a few things about the organizations that support us, say a bit about the goal of the event, present statistics about the applications you received and the attendees, and then Irini will guide you through the program and show some useful information about how to use Zoom and Discord. So I guess you are all familiar with ACM, the Association for Computing Machinery. It was established back in 1947. It is the world's largest educational and scientific computing society with nearly 100,000 members in more than 170 countries. The mission is to help computing professionals to be their best and most creative. ACM, as you know, organizes some of the most prestigious conferences, publishes several top-tier journals, provides the ACM Digital Library, various chapters, working groups. So if you are not a member of ACM, I encourage you to join. And if you are a member of ACM, I encourage you to take advantage of the various opportunities offered by the ACM. You can browse through the ACM page for more information. In particular, we are supported by the ACM Europe Research Visibility Working Group. The group was established by the ACM Europe Council a few months ago. And the mission is to achieve a greater visibility of European research and to ensure a high degree of recognition for the achievement of European researchers within the scope of ACM Europe. The school is organized by our chapter, that is the Greek chapter of the ACM Council on Women in Computing, which was established almost 3 years ago. And the mission of the chapter is to equally help women and men be inspired by the world of possibilities that computing opens, to follow computing-related professions, and to be their best and most creative in computing. The chapter organizes various activities and an annual summit, which we hope this year will be in person. And starting this year, the chapter organizes a series of annual winter schools on typically computer science related topics. And we are very happy and very proud that you are the participants of this inaugural event. And we hope you enjoy it. Now, why we selected fairness in AI as the topic of our first school? We live in what we can call the revolution of AI. This offers enormous opportunities in, for example, scientific discovery. We may not even have the COVID vaccine without AI, and promises to improve our quality of life. But all this comes with a danger. AI-driven systems are increasingly being used in all aspects of society to assist or even replace human decision-making. So can we trust a system? Every day, every one of us use search engines, recommendation, personal assistants, the web, social media, to assist us in all sorts of decisions. For very simple one, for example, where to dine or what movie to watch, to more fundamental ones. And we get informed and shape our opinions through a variety of such systems. Also, AI is being used by public and private bodies to assist decisions, for example, in courts, in college admissions, in job recruitment, you name it. And of course, there are concerns about bias treatment, exclusion, and fairness. In these following 2 days that are going to be really intense, you will learn from top experts the theory behind algorithmic fairness, the state of the art in ranking, recommendations, web search, online market, computer vision. You learn a little bit about the software tools. And since fairness is not only a computer science problem, and we have included a couple of talks and a panel that will provide you with a broader multidisciplinary view, including policy, education, legal, philosophical, and societal views. Now let me present some statistics. We received around 150 applications. In the figure, you can see that we have applicants with more than 20 different nationalities and being located in more than 20 countries. And there is also with various educational backgrounds, most of them are holding a master's degree. And we received applications from both men and women. Now, in selecting the participants, we have basically 2 criteria, mainly the relevance of the school topic to the research or the work of the applicant, and the expected usefulness for the applicant from his participation in the school, and also the background of the applicant in terms of academic and other achievement. We also put emphasis on diversity in terms of gender, geographical coverage, and educational level. And here is the statistics for the participants. Again, more than 20 different nationalities, people coming from more than 20 different countries, and with different educational background. Most of the attendees are PhD students, but we also have graduate students, undergrad researchers and professionals, and we have balanced gender. Okay, and now Irini will guide you through the program. Irini.
Hello everyone. Hello also from my side. Let me share my screen. So you should be able to see my screen now. And let me also share my camera. Hello everyone. Welcome to the Winter School on Fairness in AI, also from my side. So I'm Irini Tucci, one of the co-organizers, and I would like to start with the program. So as Evie said, we have a very intensive schedule, 2 full days of activities, which can be categorized into different types of activities. So we have scientific talks, we have tutorials, we have working sessions, group working sessions, and we have a panel discussion. And you can find a detailed program online. And let's take a closer look to the different days. So starting from today, Thursday, as you can see, we will start with a tutorial by Toon Calder. So this is an introduction to the fairness problem in machine learning. And then we'll have a small break, and we will continue with an introduction to working groups. What are the working groups? What sort of topics you will work on? What are the group members, etc. And we'll continue with a research talk on fairness in online labor markets by ACM Europe. And after the lunch break, we continue with the tutorial on fairness in ranking and recommenders, a tutorial by Evangelia Pitoura, Kostas Stefanidis, and Georgia Koutrika. And after that, we will have a bit of a more technical talk. It's about the AI and the quality coding toolbox by Sofia Kypreou. And we close today, so Thursday, with a meeting with meetings of the working groups, so you can work together on the topics of the groups. And we continue with Friday, so we start at 9, and the first session consists of 2 talks, Bias on the Web by Ricardo Baez-Ayates and Disparate Effects of Recommender Systems by Carlos Castillo. We have a small break for refreshment, and we continue with two other talks. The first one by Jan Lauterbacher about computer vision, and the second one by Bettina Berendt on algorithmic fairness, visibilities and invisibilities of algorithmic fairness. We have a lunch break, and we continue with the panel, which, as Evie said, is a multidisciplinary, because the topic of fairness is really a topic that goes beyond computer science, so we need input and contribution from many different disciplines. And in this panel, we try to cover as many disciplines as possible. So we have computer science, Timo Selis, we have sociology, Katerina Kinder-Kulanda, we have philosophy, John Cerilli, and we have also law and Thikos Kina. So this is going to be an interesting panel also. And we finish, after that, we have another research talk by Julia Stojanovic on building data equity systems. And we finish the day and the school also with your presentation. So we have the presentations of the working groups. And before that, we have a small break, which you can use also to fine-tune, finalize your presentations. So this is the schedule. And the school, due to the current situation, takes place virtually, as you know already. And for this, we will use 2 tools. So we will use Zoom for the school activities, talks, group meetings, panel, etc. And we will use also Discord as an informal exchange platform. And if you are a participant of the school, so this is a participants-only event, you have received the link information for the Zoom and the Discord. This is information only for the participants, so only participants can join. But if you have some friends or a network, etc., that also want to attend the school, then they can watch the stream, the event live. It will be live streamed. It is actually live streamed via the Greek ACM Women Chapter YouTube channel. So you can share this link with this network. So let's start with the Zoom. So all the activities will take place via Zoom. We have one central link which you have received and you will use for all the activities. And if you have any technical issues, etc., please contact us using this email here and mentioning your full name, the one you used during your registration. And again, you should not share this link. You can share the live streaming. About the talks, so we start with the talks. So in each talk, there is a dedicated Q&A session at the end, which can be used for your questions, and to the speakers, depending on time, so as time permits, can address some or all of your questions. So the question now is, how do you ask? And there are two different ways. So you can raise your hand, or you can post your question in the chat. There will be a dedicated session chair, which will handle these questions. So the questions from the chat, he or she will read the questions from the chat to the presenter, or if you have raised your hands, he or she will give you permission actually to start speaking. And the order is the first in, first served, right? So if you have any question, please do not wait until last minute, because someone else might already ask, and maybe then there is no time for all of the questions. So ask as early as possible if you have any question. And if you are given permission to pose a question by the session chair, then you can unmute your microphone and you can turn on your camera if you want. Again, remember that this is an event that is it is live streamed, right? So please keep this in mind. And of course, depending on time and on your questions and interest, we might not be able to address all of your questions. So let's move now to the working groups. So again, we'll use the main link, but each group will work on a dedicated breakout room, and all the details about the assignment of participants, or your assignment to the different groups, and how exactly what are exactly the group logistics, they will be discussed today, later from 12 to 1 in the dedicated introduction to working group slot. So all the answers will be provided there. In the panel on Friday, again, we have the same process as with scientific talks. So we have the last part of the panel is dedicated to your questions, and again, you can pose your question either by using the chat or raising your hand, and depending on time, we'll handle some or all of your questions. And you can, if you have a question, you can actually address a particular panelist, or it can be a question for the whole panel. And as I mentioned, except for the Zoom, which is, let's say, our formal communication platform for all the school activities, we have also a Discord server, which is a platform for informal exchange between the participants, mainly between the participants. So the idea is to allow you to discuss on the topics of the school and to exchange on all the talks, tutorials, etc., information you receive, and also to facilitate networking and connecting with each other. The link has been already provided, and we'll repeat it also in the chat, so you have already all the information. And of course, you should respect the rules, which are also repeated in our first page, in the introductory page of the Discord channel. So if you use the Discord link, this is the first page that you will see. So you see the rules actually, so the welcome and the rules that you should respect. And we have 3 channels, so we wanted to keep it simple. So welcome and rules, networking, right, where you can start introducing yourself and networking with each other, your interests, etc. And then we have a channel on the lectures, right, so on the content of the school, where you can start discussing school-related activities. And that's all from my side. If you want to share the event in Twitter, you can use this hashtag, and I wish you all a great time, and I'm hoping this will be useful for all of you. Thank you very much.
Thank you, Irini. I'm Georgia Koutrika. I would also like to welcome you to this school. It is going to be two very exciting days for all of us, and we are going to learn about a lot of interesting things on a very hot and critical issue of fairness in AI. And at this point, I would like to welcome our first speaker, Toon Kalders. We are very lucky to have Toon because he's actually one of the first researchers to study how to measure and avoid algorithmic bias in machine learning. Toon is a professor in the computer science department of the University of Antwerp in Belgium. He is working in data mining and machine learning. He is one of the editors of the book on discrimination and privacy in the information society. And currently with his group, he is studying theoretical aspects of fairness in machine learning, but he's also looking into practical use cases, collaborating with tax authorities, public welfare, and insurance companies. So Toon, welcome. The floor is yours, and please go ahead.
Right, thanks for the introduction. So let me share my screen. Yeah, looks like this is working. And we're all set. Hi. Well, have you ever heard the sentence, it's nothing personal, it's just statistics? Computer says no. And this is a model which is built with machine learning. Well, this is what this talk is going to be about. It's going to be about giving you ammunition to counter such statements. So I will talk today about machine learning fairness. And well, AI and machine learning is everywhere. This is a slide in this group I can probably skip, but it's being used in spam detection, in route planning. Search engine results are being ranked using machine learning, automatic translation, tax fraud detection. These are all domains where artificial intelligence is being used to support people to take important decisions. And the benefits of machine learning, well, and they are clear. If you look at human performance on some of these tasks, then you see, for instance, and this is an example of the Cypher-10 dataset, which is a dataset consisting out of pictures for 10 classes. And the classes are like an automobile, there's a car in the picture, there is a ship, there is a bird. If you look at human performance, human can classify on average 94% correctly, and because the pictures are very pixelated, so it's not easy to distinguish what's on the picture, or at least not always. And if a human is specifically trained for this task, he or she can probably do about 100 per minute, and that's even quite optimistic. If you compare this with machine performance, and there the best known model is 99% accurate, and machine can do thousands of images per second. So it's very clear. There is a huge benefit of using machine learning. It can be more accurate, and it will be faster. And so in the early days, there was this promise of machine learning, and machine learning was seen as a potential way to get away from human decision makers that are susceptible to prejudice and bias. For instance, there are gender and racial stereotypes. But now with machine learning, we can base everything on statistics. We will be free from bias. Decisions will no longer be based on gut feeling, but on facts and statistics. However, it turns out that this is not entirely true, because models may pick up and amplify bias from training data, which may lead to unintended effects. So I'll give you some examples of this in a minute. And this becomes particularly problematic as models may have millions of parameters, and predictions can hence not always be explained. If there is a human decision maker and you do not like his or her decision, you can always ask the person, okay, why did you take a certain decision? It can be explained, there will be some reasoning behind it. If a deep neural network was used to make a decision, it's much harder to actually get an insight on what was going on when the decision was taken. So here is an example where which is probably just based on statistics. And this is about a Walmart store. And it's, well, it went national, this news in the United States, where there were Barbie dolls, and there was probably based on sales, and the black Barbie doll was only $3, while the white Barbie doll was $5.93, and they were next to one another. So this is a clear example where probably from a sales perspective, this made sense, and maybe the white doll was sold more than the black doll because of the neighborhood where the doll was being sold, where the store was located, was predominantly white. But on the other hand, this is also creating a very weird situation where it seems as if we are valuing white people, or at least white dolls, more than black dolls. So the outline of my talk will be, will motivate why fairness in machine learning matters, by giving 3 recent examples of bias in automatic decision making. I will further motivate that this is really an issue that is playing. I will talk about how to measure fairness as a next step, which turns out to be surprisingly hard. And once we can measure, how we can remedy fairness algorithmically. And in the end, I will give some outlook. So first, motivation. Why does fairness matter? So why do we want to study bias-free classification? And we already saw the example of the Walmart, where there was reputation damage. But next to that, and there are also discrimination laws that do not allow you to use certain rules that are based on ethnicity, gender, and religion, even if that happens indirectly. So this is already a quite old ruling of the European Court of Justice in 2011. This was about insurance companies using the gender for in order to price car insurances, where they decided that taking the gender of the insured person into account as a risk factor actually is discrimination. Even if there is statistical evidence that males are more likely or more prone to be involved in car accidents than females, it's not allowed to use this attribute. Your model will become less accurate if you do not use this attribute, but we are not allowed it. And the reason behind this is that because correlation is fine for prediction, but if you want to make decisions, this requires causality. Males are making more accidents, not because they are male, but because the gender of a person might be correlated to certain risk factors. There are also some ethical guidelines for trustworthy artificial intelligence, also under the Obama registration. There was something similar in the United States and in the European Union. Nowadays, people are looking more and more into AI and how to regulate AI. And the high-level expert group on artificial intelligence in 2019 came up with a set of guidelines for trustworthy artificial intelligence, and that also included oversight, safety, if you're looking at critical systems like automatic cars, privacy of your data, transparency, being able to explain decisions that are being made by AI. And also an important chapter there is about the diversity, non-discrimination, and fairness. It's a very readable document, and so I definitely advise you, if you're interested in the topic, to read this document. And if you look at the document, then you will see that there are a number of the guidelines are actually translated in a list of questions that you can use as a checklist if you're making AI critical system. And some of the questions in this questionnaire are, did you establish a strategy or a set of procedure to avoid creating or reinforcing unfair bias in AI systems? And so you need to show that you have a strategy, that at least you're thinking about how the system that you developed, the algorithms that you're learning, the models that you will be using to make your decisions, how they may actually perpetuate discrimination and bias, or even amplify it. Diversity and representativeness of end users in the data is also an important aspect, and because if certain groups are not represented in the data on which you train your algorithms, it's very likely that your algorithms will perform worse on these groups, creating an unwanted effect for these groups. And also, did you ensure a mechanism that allows for the flagging of issues related to bias, discrimination, or poor performance of the AI system? And so basically, from the European Union also, and they're requiring that you take actions when using AI systems that look into this issue of bias. There is also a question about definition of fairness, which will be quite relevant when later on we will be talking about different ways to measure bias in your data. And where we will be talking about quantitative analysis, and we'll show that this is actually not a very easy question. And the definition of fairness that you are using in your work and when building your AI system, is it something that is commonly used? And do you have a good motivation for using that particular measure? So before diving into different ways to measure fairness or to measure bias, I will go into 3 recent examples of bias in automated decision-making. I will use these examples later on to illustrate some of the concepts that we will see when we will be talking about measuring bias. And the first example that I will cover is about racial bias that is found in a major healthcare risk algorithm. So this is something from a few years ago, in October 2019, where a system was used in the United States to predict for patients which patients would be likely to need extra medical care. And because for those patients, insurance companies could take special precautions, and these patients could benefit from high-risk care management programs. So they would get access to specially trained nursing, I assume with the goal of reducing the costs later on by treating those patients that are at risk to need extra medical care, and to start treating them early and to start treating them correctly. However, it turned out that this system that was used on more than 200 million people in the United States was heavily favored towards white patients over black patients, even though race was not a variable in this predictive model that was built. So it was completely unintentional, and there was no intention from the people that made the AI algorithms to discriminate against race or to give an unfair advantage to white people. It was just an effect of the way the model was trained. And so when we analyze the reasons why this is, and basically what they did in order to train the model is they looked at the patient's record and then at the future healthcare needs of the patients. And that's basically what the prediction they want to make. As we normally do, and data was collected, different patient records from a few years ago, and then we can look at the current healthcare needs of the patient. Based on that, we can build a model and that correlates the patient's records with his healthcare needs a few years later. However, they did not have direct access to the future healthcare needs of the patient. So instead, they used the future healthcare costs. And these are insurance companies building the model, so they have access to how much money they needed to spend on a patient. And so basically, they can make a link between a patient's records in a certain year and then the healthcare costs a few years later for that same patient. And this, the more you spend on the patient, well, and the more healthcare needs the patient has. It's very logical. However, one thing that they overlooked, and the reasoning behind this is, of course, and that if you have the health condition of a patient affects his current record or her current record, and the health condition also has an influence on the future health intervention, which is then correlated with the future healthcare costs. And so in this way, and this is the assumed model by the insurance company. However, one thing that was overlooked is that actually there is ethnicity, and ethnicity has an influence not only on the future healthcare costs, which is used as a proxy for the healthcare needs, and also on the healthcare intervention. And so it turns out that depending on whether you're a Black or a white person, you will get different healthcare interventions. The Black people in the data went to different hospitals that were cheaper. And the healthcare interventions that were taken for these patients were differently depending on the race, probably also because of the status of insurance, and maybe some healthcare interventions were not covered for certain patients, and this is correlated with the ethnicity of a person. And so in this way, unintentionally, a bias was introduced in this prediction, where the patient's record was used, and the health condition, the patient's records also contains information about ethnicity. And so actually there should also have been an arrow from ethnicity to the patient's record, and by the neighborhood where he or she lives, the hospitals where he or she got certain interventions, the interventions that they got, there are some correlations with the ethnicity. And so in this way, the relation that we want to learn between the patient's record and the future healthcare needs is tainted by using the future healthcare costs as a proxy for the future needs. And the effect was actually, here is the arrow, and the effect was actually quite dramatic. So if you look at all the patients that were classified as very high risk, then the Black individuals turned out to have more than 1/4 more chronic illness than the white ones, which indicates that they were added into the program less easily added into the program. It was more likely that they were having serious chronic illnesses. So this is one example, and this is of course something that we do not want to have. In this case, it was because the label that we were using to train our model is not the label that we want to predict, and the way that the target is influenced is racially biased. Some remarks on the study by the authors, and not the authors of the model, but the authors of the study that uncovered this bias in the data, is that, and the point that they are making, I think, is really important. And the point of the study was not to discourage the use of AI in healthcare, because the models they were using, they were more accurate. People were helped more often, and it is just impossible to manage millions of healthcare variables using humans alone, and you need the help of AI in order to help to manage these problems. But this is an important conclusion there, they hope that one of the things that would come out of this paper is that AI manufacturers would do a basic set of audits before their product touches a real patient. And so here again, very similar as what we just saw in this EU guidelines from the high-level expert group. And here also they're striving for audits and for trying to get a grasp of how decisions made by the system influence different groups of people. So that was the first example, where actually the bias comes from the fact that the label that we are trying to learn is different from what is in our data, and what is in our data is affected by sensitive attributes. A second example is about Amazon that used an AI recruiting tool, and this AI recruiting tool apparently favored men for technical jobs. And So it was in 2015 and that Amazon realized that their algorithm that they used to hire employees was biased against women. And the algorithm was based on resumes that were submitted over the past 10 years. And so it was quite a bunch of data. Most of these applicants were men. It's a technical sector, and there is a cultural bias towards these jobs being male dominated. And so the algorithm was trained on these resumes, and after the training, it favored men over women for certain jobs. It even turned out, if they look deeper into the algorithm, that it penalized resumes that included words like women's, like in women's chess club captain, or even downgraded graduates of some all women's colleges. So this is, of course, something that we do not want to have in all our algorithms. So where does this come from, and what are the reasons behind this? How does such an algorithm pick up bias? And one of the underlying reasons is technologies that are being used, and word embeddings are techniques when we do text analysis, which are very popular, where in a word embedding we represent words or text as vectors of numbers. And this is, of course, because all our algorithms, they work with numbers. They work better if we can work with tabular data. And now text is not very convenient to work with directly. So for instance, we have the word banana, we turn it into a vector, father, a vector, baby, vector. And we want these vectors not to be just arbitrary, but we want them to have to capture as much meaning as possible. Father and baby, these are both people. So we want their vectors to be closer to one another than father to banana, and banana needs to be closer to apple than to baby, etc., etc. And so basically you want these vectors to capture semantic information, and because if they capture semantic information, these are things that the algorithm can exploit. And if our text is talking about one word, then other words that are related to it, and they will also trigger similar reactions from our algorithm if we're using these embeddings. And so our embeddings are like an adapter that we can use in order to insert text and to apply classification on texts. Embeddings are not random, and words used in similar contexts should have similar vectors. That's what I already said. Here is a made-up example of how we could classify adjectives based on whether they are used for people or for food, and whether they're more positive or more negative. So then a word like excellent, it's an excellent dish, or this is an excellent person. It's a very positive word. It can be said about food and people. And so this will actually be here on the x-axis, and that represents if it's more a people word or more a food word. It will be central, and in the y-axis, which represents if it's positive or negative, it will be more at the top. Obnoxious is a negative word used for people. We do not have obnoxious bananas. Intelligent, a very positive word. Delicious is then something positive that is used more about for food, etc. So in this way, and different words get a position, and we get a two-dimensional representation. And this is something that we want to do, but we do not want to do it manually, placing all the words in a multidimensional space, but it needs to be learned automatically. So basically, learning this type of embeddings, I compare it with a game that we are learning to play. And the game is guess the word. And so here we have these infamous Florida man snippets and news articles. And the game we are playing is, I want you to guess the word which is missing. Florida man charged for assault with a deadly weapon after throwing something in Wendy's drive-thru. And basically we want an algorithm to learn about context and to learn about text such that it is able to predict this type of words. It's easy to generate test data in order to learn this task. Basically, we just create small context. A Florida man, the word we want to predict for assault. If this is the context, we want the algorithm to predict charged. Man charged, some word missing, assault with, and then the word we want to predict is for. etc. If you look at these embedding techniques, basically what we will do in order to learn an AI to play this game is to first have a model that turns the words, the context words, into vectors of numbers, and these will become our embeddings later on. And for each word we will learn a vector of numbers, but not just an arbitrary vector of numbers, but vectors of numbers that will allow us and that we can use as an abstraction for a second model that then will predict which is the word that is missing. And this is actually a very clever way of using unlabeled data in order to learn a representation of words that makes sense. Because basically, if you want to predict which word is missing, we need to know a lot about the context in which the word appears. For instance, if Florida man is the subject of the sentence, and then we know that there will be a verb will be the next word. So it will be important whether it's singular or plural in order to predict the correct form of a verb. Also, and the assault is a word that carries a lot of meaning that will allow us to derive, and that maybe charged is the missing word. And by learning this model that turns words into numbers in such a way that these numbers allow us to predict the missing word, then we will actually automatically insert meaning of the words into our vectors. And so it becomes a traditional optimization problem. This is what we want to predict. This is what we want to predict. This is our input, and we can measure the quality and by comparing what comes out of our algorithm. And so this is our second model with parameters being applied to the first model applied to the first word, the first model to the second word, etc., etc. And we compare what comes out of it with the true label, and we want to have this expected value of the loss, which expresses how good or how bad our prediction is, and we want to minimize our loss or our incorrect predictions. So after we learned the model, and the model is able to very well predict what will be the missing word, after that we can just throw away the second model and we just keep the intermediate results. And in this way, this part of the model captures semantic information in a vector that allows you to play the guessing game, but it allows you to play many, many more games than just a guessing game. It also allows you to build classifiers based on text, and by turning it into these vectors that carry semantic meaning. And this works remarkably well. For instance, if you look at the relation between words, and so these are representations that are typical dimensionality is 300 dimensional or representation. Basically, if we then, and this is a projection in 2 dimensions, if we then look at the position of the vectors, and this is a very nice visualization where we see that if you look at the comparatives of words, slow, slower, slowest, and the relation between them, then we see that for different words, and their comparatives have a similar relation. And this is logical because we will have some dimensions that will express which comparative a word is in, because this will allow us to predict other words. If there is slower, it's much more likely that there is than the next word. I am slower than some athlete. If it's slowest, and then it's much less likely that the next word is than. Also, if we look at these words as slower, then this probably is something about running or biking or driving or whatever. There's something with motion. So probably there will be some dimensions expressing that it has to do something with motion. Stronger, and then there will be a different context there. It also allows us to do this kind of arithmetic. if you want to know what is slower relates to slow in the way that shorter relates to, and then basically we can compute by looking at the difference of the vectors. And we can look slower minus slow, and that's then this direction that brings us from slow to slower. So if we add it to short, and then we would get the vector of shorter. And so in this way we can use it to solve some of these comparisons. Also, gender information is captured, which also makes a lot of sense, because will the next word be he or she, and then it really matters whether it's a male or a female subject that we're talking about. So the difference between man and woman and between king and queen is more or less the same. So a man relates to woman like king relates to, and then we can add to king and the difference between man and woman. And we subtract from the vector of king the vector of man, and we add the vector of woman. We see where it ends up, and we end up with queen as the word. I see there is a question if the word embedding study is done with BERT. No, this study that I'm talking about here was done by with non-contextualized word embeddings. And so this means these are word embeddings that give the same vector to a word independently of the context in which the word appears. Later on, improvements to this method have been made, like for instance BERT, which gives you contextualized embedding. So an embedding of a word may depend on the sentence in which it appears, like the word stick, and we need to stick to the plan, or he hit the dog with a stick, and the embedding of stick will be different in BERT, but for the word playing game type example, the word to vec that I'm giving an example here, it will give you the same embedding. But it doesn't matter. Also for BERT, and to answer to the second part of the question, also for BERT, similar conclusions hold. And the vectors produced by these word embeddings, whether they're contextualized or non-contextualized, they carry a lot of meaning, gender information, whether it's singular or plural, comparatives, and a lot more, and also information that we cannot really directly imagine ourselves, but that might be very helpful. And this has amazing applications. Actually, models based on these embeddings, they perform extremely well. They perform better than when we just take a representation that tells us whether a certain word appears in a text or not. One of the reasons is because we can pre-train these embeddings on lots and lots of data that is freely available, and get embeddings that are semantically extremely rich, and then apply it in other applications. And so because there is this unsupervised learning stage, or at least we do not need labeled data, and we make our own labeled data by masking out some words and trying to predict these words, and we can really make excellent applications out of it. At the University of Antwerp, where I'm working, one of the professors, for instance, is using it in order to predict whether some social media messages constitute cyberbullying or not. Because there, the sentiment of the words, it will be very informative. Is it a positive word? Is it a negative word? You can use dictionaries, but it works much better if you use word embeddings in order to amplify your predictions. And here is an example. It's taken from another source. It's not from this study, where they look at tweets and do sentiment analysis for tweets. And here again, it's projected down in 2 dimensions. We have positive words, the red ones, and negative words. And here you can see, looking at the embedding, well, it's of course not a perfect separation, but you see some tendency that the positive words are more to the right and the negative words are more to the left here. If we look at the higher dimensionality, you can probably identify positive and negative words much more accurately. So this is a technique that works very well. but it turns out it also captures cultural bias. The paper that I'm quoting here is from 2016. Later on, a lot of follow-up research has happened. Some of them questioning the way conclusions were reached. But I think the initial message of the paper still stands, in a sense that the word embeddings capture cultural bias. And the way they show it in this paper, and Bologbasi and others show it, is by making this kind of analogy, where they show that the gender information is captured, but not only gender information, but also cultural bias. For instance, they play this game with the vectors. I take a man and the vector of a woman, so I get the gender dimension by subtracting woman from man. And so I have computer programmer, which is a predominantly male profession, at least in Belgium. I don't know statistically throughout the world, but the fact that they were using this example, it seems to indicate that it's also true in the United States. So basically they add to computer programmer and the difference between these two words in order to get the female equivalent of a computer programmer. And then the machine answered homemaker, which is clearly a bias, a cultural bias, which is present in the data. The system that they were using was trained on news articles. And so this equivalence or this example illustrates that in these news articles, computer programmers were much more likely to be associated with male people in the data, and homemaker and much more with female words. And so if the sentence would be John is a, and then the algorithm that guesses the word, that was much more likely to add computer programmer. And if it is Jill is a, and then it was much more likely in the guessing game, you would have better chances winning it if you would enter homemaker. And this was information that was captured by the algorithm. Also, if you look at the gender stereotypes and she-he analogies, and then sewing is then the female variant of carpentry, according to the algorithm, nurse and surgeon. Of course, and this is information that is present in the data, there is a certain cultural bias. We need to be aware of it. It's not the fault of the algorithm. And then why is it problematic? Now, of course, it's problematic. And now the circle is completed. We're back to the Amazon example. If you use this type of techniques, Word2Vec for screening your CV, finding the perfect job for you, and this is not the type of associations that you want to make, even though if you play the guessing game, and that it will give you an edge in this domain. Since then, things have changed. People have been working on changing the embeddings, trying to remove some of the cultural biases. But still, here is an example that I made myself, where I took a list of the most popular white female names in the United States, the most popular black female names, white male, black male names. And I compute the average similarity between the vectors, just cosine similarity between the names and some selected terms. And then you see that there still is some bias in the data, and there are still significant differences. So the position that white female names get, if you compare it to the position of robbery, and then you see that the black male names will be closer to the term robbery than female names. And this is, of course, it's based on news articles. So probably it was much more likely that there is a black male name that then the news article was about a robbery than when there is a white female name. Also, if you look at terms and like trustworthy, then you see that typically males are closer than females to those terms. Professional and similar. Here the difference is extremely high. Intelligent and so on. And so these are things that we need to be aware of if we will be building classifiers on top of word embeddings, which are very, very powerful techniques. We need to be aware that these word embeddings, that they are biased because of the data that they have been trained on. This also has to do with in these guidelines from this high-level expert group, where they were saying if you use data and make sure that your data represents everyone, represents them in the right context. And here we see for the task of for playing the word guessing game, this embedding is excellent, but for connecting resumes to jobs that people need to do, this is probably not less suitable. So this is a second example, and again, and this is a point that I want to make, and I think is very important. Again, it was absolutely not the intention of the people making the AI to be discriminating. Maybe if the team would have been more balanced and they would have been more aware of these problems that might have occurred. But anyway, it was not intentional to have this discrimination. It's just an effect from the fact that we do not know our data perfectly. It's observational data. These are news articles. We have not carefully selected the data, but the data is around and we want to use it in order to make predictions. A third example, and this is probably the most well-known example, it's like the canonical example when we talk about machine bias, is that of the COMPAS study by ProPublica. And ProPublica is a consortium of investigative journalists. And in one of the studies, they looked at the correctional offender management profiling for alternative sanctions system, which is a system that was developed by a company in order to predict risk of recidivism. And the label they were using is for a person, and so they take data from a person in year X, and then they see in year X plus 1 and year X plus 2, was there a new arrest for this person, taking the information about arrest, whether there was an arrest or not, as a proxy for recidivism. So kind of assuming that everyone who recidived was actually arrested. Anyway, I think it's a fair, well, it's a logical proxy to use. And data they were using were, for instance, pending charges, prior arrest history, which turns out to be quite important one, pre-trial failure, and did they fail to turn up when the trial was in court, residential stability, substance abuse, and these were all aspects that were taken into account in order to predict the risk of recidivism. And so ProPublica, and they studied people that were, for which this system was used. And because of openness of information, the COMPAS score that was given to those people, which is a number from 1 to 10, these numbers were known for a number of people, and also, and then they could correlate it with the recidivism status of these people. And now one thing that they noticed is that the errors that are made by this model, and that they were highly biased. So basically, they looked in the study, the people that they followed in the study, and some people were labeled as being high risk, and they got a high score by COMPAS, 8, 9. But it turned out that they did not reoffend. And so they look at how many people are in this particular case. And if you look at the white people among the population that they followed, then they see that there was a probability of 23.5% for white people that this error is being made. And for African-American people, actually it increases to 44.9. And so of all the African-American people that did not reoffend, 44.9 were labeled high risk anyway. If you look at low risk, so people who receive a low risk label but did not reoffend, then they see that this error, but they did reoffend, and then they see that this error is being made much more often for white people than for the African American people. And so this was for them an indication that there is some unfairness in the way that people are being labeled. I think they are actually making a really strong case here. However, and I think it's also fair to add the point that is raised by Northpoint, which is the company that made this model. And basically their defense is, okay, our model is fair, maybe not in the way that ProPublica intends, but we try to make it fair in the sense that scores need to be calibrated. And by calibrated, they mean that if we look at people that are assigned to low, medium, or high risk categories, and so here, instead of the score from 1 to 10, we have lumped them into 3 categories. If you look at people that have been assigned in the high risk category, how many of those did reoffend? And then you see that there is, let's say, between 70 and 75% that did reoffend of people that are in the high risk category. In the medium risk category, it's a bit lower. In the low risk category, it's even lower, which is good, of course. Our system is working to some extent. It's not perfect, but at least if you're assigned to a higher risk category, then your real risk is also higher. And then they say, okay, looking at the risk category that someone is assigned in, it shouldn't matter whether the person is black or white to determine what is the true risk for this person. And so this is what these 2 bars are representing. And so if you look in the high risk category, how many white people did reoffend in this that were assigned to this category, how many black people did reoffend. And then we see that this is more or less the same. It's actually even for the black people, it's even slightly higher than for the white people. If you look in the medium risk category, the same. Proportions are more or less the same. In the low risk category, it's more or less the same. And this makes sense to use this as a criterion, because basically the Northpoint will score the people that are in court. The judge will see whether this person is high risk, medium risk, or low risk according to the system, and might base his or her decision on this label. So then it's important that high risk means the same for black and for white people. We do not want the judge to start thinking, okay, this person is assigned high risk, and high risk means that if you're black, it's 90% recidivism. If you're white, it's 70%. No, high risk needs to be colorblind. It needs to be a label that allows interpretation of the risk of a person without having to look at the race anymore. So how can it happen that ProPublica comes up with these extremely high differences, while it's not, the problem is not really in the statistics, and while here it looks like, okay, it's more or less fair. The problem is actually because the representation of the different races in this group, and in the data that was used in the study and to train the models, there were more, and the proportion of black people, that's what this black line is, it's the proportion of black people in the different groups. If you look at the high risk category, it's almost 80% black people. In the low risk category, it's 50%. And so there is a difference, and the base rates are different for the black and the white people. And if we now look at the errors that are being made, so let's just divide it into 2 categories, high and not high, and to mimic the situation that we have here. We have high risk, predicted low risk, predicted high risk, etc. And so just 2 categories. Let's make the situation the same. Then if you look at the errors that are being made, they are here. And so there are 80% of people that are assigned to the high risk category are really high risk and did reoffend, and 20% did not reoffend. Well, it's a little bit more. 25% did not reoffend. So it means that by assigning this label high risk versus non-high risk, that in this category, we are making 25% of this group are actually false positives. If we look at the low and medium risk categories, even though we mark those people as not being high risk, and there still are people that reoffend in this group, and these are all false negatives, so they got assigned a negative label, but they are actually positive. And so in these groups, it's slightly more than 50% for which we make the error, and this is here it's almost 40% for which we make this error. But what we see here is, if you look at these different risk categories, low, medium, high, these different groups, then in the high risk category, only false positives are made. And this is a non-beneficial outcome of the process. It means that you do not deserve to stay in prison, but the system says, okay, you need to stay in prison because you're going to recommit a crime. And in those two groups, only false negatives are made. And so in those groups, if you're low or medium category, and none of those is predicted to be high risk, while they do not reoffend, the errors are always in the other direction. So all false positives are in the high risk group, all false negatives are in the other groups. And now if you look at this black line, then we see that the black people are relatively more frequent in the high risk category than in low and medium group. And so they're actually overrepresented in those groups where the false positive errors are being made, and they're underrepresented in those categories where the false negatives are being made. And so this is basically the reason why these two situations can coincide, and that we can make predictions that are calibrated. The categorization means the same for black and white, but the ways errors are being made is very different. If we would split out this table into the three groups, into the ones for which predicted medium risk and for ones predicted low risk and high risk, and then and these numbers would actually be different, and the effect would not be that bad. I think it's actually fair, if we consider this ProPublica case, to also consider this this answer there. Voila. And so these are about 3 recent examples of bias in automated decision making. And as you can see, this made an impact. And so it's important to do something with it and to deal. And a first start is to measure how fair a certain data set is, how biased a certain data set is, and how fair a certain solution is. I see that there is one example still for the one question for the examples that I gave. So let's first pick that up. So someone is asking, words like robbery are found in the text. So John can be connected to robbery. What about words like smart? And how are such terms connected to gender in the news articles, or intelligent? And well, this is because indeed in much the same way as robbery is connected to more often to the black male names in the text, words like intelligent, smart are more likely to be connected to males in the text. And so if you look at the news articles, they might be talking about a politician who is very intelligent, and then it's more often a male politician and a female politician, or just in general, it's more likely to be about a male than about a female in these articles. Yeah, you can dispute whether that's a result of the selection of the data, but basically that is the way it is. And again, we should be aware of that when building models using those techniques. All right, and so I hope to have established that it's important to take these things into account and this bias into account. because it can have a big adverse effect. And these 3 examples, they stirred up a lot of commotion. There was a lot of reputation damage for the companies and institutions that were involved. And there are many, many other cases I didn't talk about. In the Netherlands, there was quite recently a case about benefits that were taken away from people by a decision procedure that was racially biased, and many, many more cases. And so, basically what we want to do is before we start using our algorithm, we want to measure whether it's fair or not. And that's basically the subject of the second part of my presentation. So what does it mean to be fair? If you look at ProPublica studies and Northpoint's response, and that already raises an intriguing question. How can we define when a decision procedure is fair? The disagreement between those 2 groups already reveals that it may depend on your perspective. What do you want to do with the label that you have assigned? A first attempt that we could try is to say the decision should not be based directly on sensitive attributes. It makes a lot of sense. We do not want to have gender discrimination. So a very good starting point is to remove gender from our set of attributes. However, and this was shown in many different works, and this actually does not work, and that's not too surprising, because we can still build models based on correlated attributes. Now, here is an example where in the past this was used on purpose in a non-automated decision procedure. And this is a map of illustrating the redlining effect. There were actually access to certain benefits. I think in this case it was loans were disallowed for people living in certain neighborhoods. And these neighborhoods, and not surprisingly, were predominantly Black. And this is what we call the redlining effect. People are marking with a red marker on the map. People living in those areas should not be given a loan because discriminating based on race was no longer allowed, but discriminating based on the place where people are living was allowed, or at least differentiating your rates for the loans. It is allowed to differentiate based on the place where people are living. And if we just remove our sensitive attribute, for instance, sex or race from our data, basically our models can still use correlated attributes. And so if there is an unfair correlation between your label and the ethnicity of a person, for instance, in the hospital data, well, the hospital data is a very nice example of that, and where the algorithm uses proxies of the race in order to still come up with a model that is more accurate according to the tainted label in that particular example. So that doesn't work. It's an illustration. This is from an old paper of mine where we use the adult data set. And the adult data set contains information, demographic information about people and whether or not they have a high or low income. And we made this kind of simulation where a bank would use this information and would only give loans to people with a high income. And then if you look at the original data, a high income, low income, no loan, high income, we give a loan. And then we see that the difference between males and females in the data set is 19%. So this is, by this I mean that if you look at the percentage of males that has a high income, that we would give this cheap loan, and females that have a high income, if we look at the difference between those proportions, there is a 19% difference. If we then learn a classifier that makes predictions, and it can base its predictions on gender, we see that the effect is even amplified and becomes 31%. And so it's actually a very bad situation, because here in the predictions, for the females, it's going to be amplified, this effect. And if we remove gender from our data set, actually it's almost no difference between the two. And the reason is because there is a lot of gender information in the other attributes. The studies that people did, the jobs that they are doing, also the marital status contains information about the gender in this particular example. So there was actually some information leakage there, and this is true in general. And so just removing the sensitive attributes will not help us. We need another way, even if the gender is not used, our predictions may correlate with gender in an unfair way. And there is a whole lot of different ways to measure fairness. And we distinguish two big categories. And the first one is group fairness, where we basically look at statistical measures, where we look at Black people and white people as a group, and we see if this group has been discriminated, if there is a disparate impact of our classifier or in our data for this group. And we look at individual fairness measures, and individual fairness measures, and they are more aimed at if we look at one specific instance that received a label, would the label of this person change if it would have belonged to a different group? There we will look at situation testing, and also causal-based fairness are actually categorized in this category, although it's not entirely clear in which of the two categories it should belong. But we will first start with the group fairness measures. And there, the first one we look at is statistical parity. With statistical parity, the setting is that we have two sensitive groups, and I will use the attribute A to indicate the sensitive group. There are true labels, and true labels will be expressed by Y, and there is the predicted label Y hat. And the predicted label, and we basically want and that both groups have equal access to a certain benefit, and we will consider the 1 is the beneficial outcome and the 0 is a non-beneficial outcome. And so to make the link with the example with the adult data set, and should I give someone a loan or not a loan, we have two groups based on the gender of the people. I use here binary gender. In reality, of course, we need to do this more fine-grained here, but in this data set, there is just binary gender available. So A is equal to 0, or for instance, the females, A equal to 1 are the males. 0 is then the person does not have a high income. 1 is the person has a high income. We try to predict that. And if we predict that the person has a high income, that's a desirable outcome, because then we will give the loan to that person. So statistical parity basically says that we want to have both groups to have equal access to the benefit. And so basically we want to have this equality to be satisfied. So the probability of being assigned the positive, the beneficial label, if you belong to one group, and should be equal to the probability of getting assigned the positive label if you belong to the other group. And then basically what we typically want to do is, okay, this is something that we want to attain, and we want to optimize accuracy constrained by this statistical parity. So of all the models that give equal access to the benefits to both groups, give me the one that has the highest accuracy, that makes the most predictions that are in line with the true label on high or low income. So there are some pros and cons of statistical parity. Some say it's a bit like affirmative action. And for instance, if we have data, and in this data CEO jobs are more likely to be given to males than to females, but we still want them to be offered in an equal proportion to both genders, and that's a typical situation where statistical parity would be a good idea. Statistical parity would mean that we would offer the job in equal proportions to males and females, and so we are implicitly assuming that males and females in our data are equally qualified for the CEO job, even if the data seems to indicate something different, and because of historical reasons. And and at the same time, of course, we want that the labels that we are giving are maximally in line with the labels that are available in our data. And so we're correcting, but staying as close as possible to the original data. So that's definitely a positive. It's very useful in that case. But what if there are explainable differences between the groups? And so here, one important thing that I said is that we have this implicit assumption that in this particular data set, and the two groups are equally capable. And because of that, it's logical that we will give them equal access. But maybe in the data, again, because of historical reasons, whatever, the diploma held by the candidates might be different. And in that case, we basically want to take into account the diploma. And so we want to give equal access under the condition and that people have the same diploma. And then we end up with what we call conditional statistical parity. And so that is a refinement, because it's a critique that you often hear about statistical parity, but people have been thinking about it and have corrected for it with conditional statistical parity. So basically, with conditional statistical parity, we're saying, okay, there are some certain conditions that are explaining part of the differences between the two groups. For recidivism, for instance, it could be that on average, the Black people in the data set are poorer than the white people, and that the income of a person is correlated with the risk of recidivism. So then we can basically take this as a condition, and basically what we're saying is, okay, if you look at the poor people, and then the probability of access to the benefit should be the same for both groups. If you look at the rich people, access to the benefit should be the same for both groups. So this is conditional statistical parity. There are also critiques for conditional statistical parity, and namely, and I think this is a very fair comment, it is very hard to fully identify all acceptable explanations for differences. If it was easy to fully identify all acceptable explanations, then why would we be machine learning? Then we would just use these acceptable explanations and we would use them in order to make our predictions. Yet, there might be differences between the groups. And if there are differences between the group, even though we do not really have access to a condition that can divide them into groups such that the differences go away, it would still be unfair to force equality in prediction on both groups. And so basically, another thing that people started looking at is, instead of looking at the differences between the groups, instead of looking at conditional statistical parity, let's look at the errors. And when we look at the errors, we end up with what we call equal odds. And in equal odds, the rationale there is that errors are acceptable, but the errors should be similar for all sensitive groups. So basically, when we are implying conditional statistical parity, what we are saying is, okay, we will divide people into groups, and if a person is in a certain group, and the group is associated, it's a little bit like this calibration. The group is associated with a certain risk that the person has, and within this group, black and white or male and female should be treated equally. And so we're making errors in this group, 80% of recidivism in the high risk category. So we're making an error of 20%, and we accept this. We're classifying, we're predicting something. We cannot be perfect, but at least we want the errors to be similar for all sensitive groups. So this is an example of ProPublica, where this is not the case, and basically they're looking at the errors that are being made, and they see, okay, the errors that are made for white people and the errors that are made for African American people, they're so different, and that I do not consider this to be fair. And so the equal odds takes another turn. There we use the true label of a person as it is present in the data. And so that is y is equal to 1. And we will look at all those people that actually deserve the benefit. So let's again look at the high income, low income of the adult data set. So we actually divide people into 2 groups, the people that truly have a high income and the people that truly have a low income. And for the people that truly have a high income, and we look at the difference between males and females, and we say, okay, the predictions, the rate at which they are predicted to have a high income should be the same for both groups. It is very similar to conditional statistical parity, but now we divide people not based on a characteristic that they can explain the discrimination, but we're dividing them according to the true label that they have. And we're basically saying, and so these are the true positives. And so the true positive ratio for males should be the same as the true positive rate for females. This is false positive rate, and we're predicting 1 while it's actually 0. The false positive rate for females should be the same as a false positive rate for males. Voila. So we have statistical parity and we have equal odds as 2 different measures. Now, one thing, if you start to think about it, which is almost immediately clear, is that these 2 measures are actually incompatible. So let's just make an example to show this to you, and then we can draw some conclusions from that. Let's assume that males on average have a higher risk than females with respect to car insurance, and they're more likely to be involved in a traffic incident. And we want to assign expensive premium to high risk customers and a cheap premium to low risk clients. At the same time, however, we have followed this lecture and we want to be fair in our classification. And so we want to be fair with respect to gender, but we do not know, okay, how should we exactly do this and how should we exactly measure? Let's look at equal odds and demographic parity, and let's try to satisfy both of them. And so males and females should have equal access to the cheap premiums, and that's of course the desirable outcome, and equal odds, but at the same time we do not want the errors to be very different, the false positive rate and the true positive rate to be very different between the 2 groups. So let's assume that this is the distribution. And it's a very simplified example. I have 100 males, I have 100 females, 60% of males, and they are in this blue low risk category, 40% are in the high risk category, 80% of females are in the low risk, 20% are in the high risk category. Let's just assume that this is the base rate. And so this is true in general. So let's now try to satisfy equal odds. And so equal odds, that's this ProPublica measure, this false positive rate and this true positive rate. So the premium should depend on the actual risk and not on the gender. We will consider 2 premiums, cheap versus expensive, demographic parity, and we want to have the same number of males and females with cheap insurance. That's basically what our demographic parity and equal access means. So here is a way to satisfy equal odds. If we have a classifier that assigns 80% of low-risk males the cheap premium and 80% of females the cheap premium, 30% of males the high premium, and 30% of high-risk females the cheap premium. And so our classifier is not perfect. So these are the statistics that come out. Well, this classifier satisfies our equal odds. It doesn't matter. It only matters whether you're low or high risk. It doesn't matter whether you're male or female. The probability of receiving a cheap premium is 80% and 30%. And so our true positive rate is 80% and our false positive rates are 30%. However, if we have a classifier with these statistics and we compute the number of males that receive the cheap premium, and there are 60 that are in this low risk, 80% receive the benefit, 40% are high risk, and 30% of those still receive the cheap premium because of the error that our classifier is making. So it turns out that 60 of the males receive the benefit, and for the females, we can do the same computations of these 80%, and of these 20, still 30% gets the cheap premium. So we have 70 here. And this is not satisfying our statistical parity. And I think this is very logical. It is not very surprising if we do not want to make more errors on the females than on the males, and the females have a lower risk than the males. Well, it's logical that on average more of those will receive a low premium. So let's now turn it around. Here we make another classifier. If ProPublica looks at these and makes the tables, they will say, okay, it's very discriminative. For the males, if you're low risk male, our classifier will always give you the cheap premium. For the females, only for 75%. If you're high risk, and no one who is high risk will get the benefit. Well, in this case, we get something which satisfies demographic parity, and we get here 60 and 60, because all 60 males here in the low risk category got the cheap premium, and of the females, only 75%. So this is an example where we satisfy demographic parity. So let's try now to satisfy both at the same time. So we want to satisfy equal odds. And so both males and females, it should not depend on the gender, only on the risk category. Let's say that we have A% of the low risk category receives the cheap premium, B of the high risk category, independently if you're male or female, receives the cheap premium if you're in the high risk category. And so there's some margin for errors here. If we then look at the number of males and females receiving the cheap premium, and basically we want to satisfy this condition here, as the 60 males times A plus 40 times B should be equal to 80 times A and 20 times B. Well, I can already feel what will be the solution here, and we can only get degenerate solutions. This will only be possible if A is equal to B, which basically means that your premium is independent of risk. And that doesn't really make a lot of sense. It doesn't matter whether you're low or high risk, the probability of receiving a cheap premium will actually be the same for both groups. So these two measures, they cannot be satisfied at the same time. From this, we can draw some conclusions. An intermediate conclusion here, assuming that sensitive groups behave differently with respect to the target. And that's, of course, in our example, this example, we got that the only possibility is if A is equal to B, because there was a difference in the base rates. 60% of males are low risk versus 80% of females. If these two proportions would have been the same, well, then it wouldn't have mattered. And if the two groups behave exactly the same, and then any classifier will treat both groups similarly, and we will automatically have our equal odds satisfied, and we'll automatically have our statistical parity satisfied. And so we assume that the sensitive groups behave differently with respect to the target. In that case, if we enforce demographic parity, this means that automatically, by definition, you will make errors at different rates for both groups. So your predicted label will not be independent of the group given the true label. So this means that in that particular case, you're implicitly assuming that either the labels in the training set are incorrect, so we want to get away from it, and we have reasons to believe, for instance, for the jobs. In our data, males receive the CEO job more frequently than females, but we are convinced that this is actually not representing the true capacity of both groups. And so if we use the label who received the CEO job in the past, it's only a proxy for predicting who should receive the CEO job in future. And we have this additional constraint that we assume that both groups are equally capable, and so our labels in our training set are not entirely correct for our prediction task, and they do not represent our true target. Or maybe statistical parity is a hard legal constraint. It could be that you are required to hire 50% males and 50% females, and then it can also make sense to do that. But I think here this this quite obvious result, and that you cannot satisfy both of them at the same time, is a very good indication of some implicit assumption that we're making if we want to enforce demographic parity. This is also related to one question that I just got, where someone was making the remark that in equal odds it is assumed that the ground truth labels are correct. That is indeed fair to say. If we assume that the ground labels are correct and they truly represent who should get the loan, who should get the job, and then enforcing demographic parity does not make sense, because it means that we will make our predicted label dependent on the group given the true label, and the true label truly represents what we want to predict. But if in the past decisions might have been biased, for instance, against Black people, could one also consider the uncertainty of the ground truth? Yes, and that is here implicitly assumed, and at the ground truth, we are still assuming, we're still trying to optimize accuracy of our classifier. So we're still assuming that the labels that are given in the data set are more likely to be correct than incorrect, and we want to stay close to it. But there is some uncertainty because we have this additional constraint, this strong belief that both groups are equally capable. And so a probability distribution that is close to the original labeling, but makes both groups equally benefit is more likely. And so in some sense that is being assumed here. Voila. So here I think this is also a good point to mention the accuracy fairness trade-off. And the accuracy fairness trade-off is a notion that we introduced like years ago, where we basically looked at classifiers that we were learning, and the classifier we were looking at the fairness of the classifier by looking at how well does it enforce this demographic, this statistical parity. And so do both groups have equal access? We can just measure the difference between the two. We were assuming that there are differences in the data set. So we are in this insurance example. We want to have statistical parity there. Like if we make our model more fair, it means that we need to make more errors. And so we will get a less accurate model if we measure it with respect to our original data. And so the accuracy fairness trade-off basically means that if our data contains a bias, that if we want to become more fair, we need to get farther away from the labeling as it is available in the data set. And so if we measure our accuracy with respect to our labeled data, then we get this apparent trade-off, making things more fair. It will also mean making things less accurate. However, in the case of label bias, and these are some remarks that recently have been made independently by many researchers. In case of label bias, fair models may actually be more accurate than unfair models. And that's, of course, the reason why we are doing this. And so if we are assuming that males and females are equally capable of getting the CEO job, and by offering them in equal proportion to males and females, we actually hope to achieve a more accurate decision model. And so we do not optimize accuracy on the tainted training data, but optimize expected accuracy for fair test data in a situation where we want to apply. We want to get better decisions by moving away from the labeling of our data set. If you look at this paper here, is there a trade-off between fairness and accuracy? This is a very interesting paper where they basically look at this, and where they also do some experiments, and in related papers where they also do some experiments where they synthetically generate data containing label bias. So we generate data, we assume that two groups are equally capable, and then we introduce a bias by subsampling the capable group for one of the communities. And so we assume males and females are equally capable of doing a CEO job. So we generate data, and then we undersample the females that were capable of doing the CEO job. So in this way, we introduce label bias. Now we learn a classifier on this data, and we try to make it more fair. And so here on this axis, the horizontal axis, models become more fair. The vertical axis measures accuracy, how accurate is our model on our test data. So here we see that if we measure on our biased ground truth, that if we become more fair, we will go farther away from the original label, so we will become less accurate. But if we test it on the unbiased ground truth, so without subsampling one of the groups, for instance, or without changing the labels for some of them, then we actually see that by becoming more fair, actually we also become more accurate. And so this is, I think, a very nice observation, and it's very nice that these people showed this, even though in a synthetical example, and that by making a classifier more accurate and by making the right assumptions of things that really hold in reality, but that are not reflected by the labels, may result in a more accurate prediction. Voila. And so this is already two group measures, and the statistical parity equal odds. The third measure is calibration, and that is the measure that that the North Point was using to defend their approach. And calibration is actually a concept that comes from classification, and a classifier that gives you probabilities. And so P, M of X, and so M is our classifier, but it does not only predict whether you're in class 0 or in class 1, but also gives you a score, a probability. And then we call this probability score calibrated if the probability of getting the positive label is actually equal to the probability assigned by your classifier. So if you look at our recidivism prediction, where we had high, medium, and low risk category, and low, medium, and high category, and then our prediction, our classifier M, gives us a prediction, high, medium, and low. But apart from that, it also gives us a probability. If you're in the high risk class, there's an 80% probability of being a recidivist. So when do we call this calibrated? If we lump together all the people for which we predict, there is an 80% probability that you will recommit a crime. And then we look at how many of those did really recommit a crime. If this is 80%, and then we say that the classifier is calibrated. And the same like the weatherman is forecasting, there is a 50% chance of rain tomorrow. So we just look historically at all the times where he said there's a 50% probability of rain tomorrow. And then if indeed in half of the days following a day in which he predicted 50% rain, there was rain, and then our weatherman is calibrated. And then this is the same with our classifier. So any classifier can be made calibrated by estimating these class probabilities. And so we have a model that makes a certain prediction. We can look at the label that is assigned by the model, and then the probability that we give to an instance is just the probability that is associated with instances receiving this label. And so how to translate this? So we had our recidivism case. So if someone is assigned to the high risk category, and the probability we're going to assign to that instance, as we're going to look at in which group does he belong, in the high risk group, and which percentage of people in the high risk group recommitted a crime. Well, that is a probability that we are going to give. And this we can easily compute. And so if our model gives us a prediction of 1, the probability is then the true positives divided by true positives plus the false positives. And so all those that were predicted to be positive, how many of those were truly positive? So that's the probability if the classifier assigns you to this group. It can also be extended to multiple labels, and that we already saw with the low, medium, and high in our recidivism case. Decisions will be based on these predicted labels. So hence, and this is the rationale behind calibration, and since decisions will be based on the labels that I'm giving to people, the meaning of the labels should not depend on the group to which this person belongs. That's basically what we had in our recidivism case and North Point's defense. They were saying, okay, we are just an intermediary in the whole decision procedure. We are going to give labels to people, and based on those labels, it will be input for other decisions that are being made. And so our labels should be neutral with respect to the group. So if you look at the probability of being truly positive, given that you're predicted to be positive, it should be independent of the group that you belong to. Voila, so that's calibration. So if you now compare calibration and equal odds, they seem quite similar, but because they're talking about errors. Equal odds is saying, okay, errors should affect all groups in the same proportion. Calibration is looking at also at errors, and it's basically saying if I have a label and the label is high risk, and then I'm making an error of 20%, and this should be equal for both groups. And so they seem to be quite similar, but still they cannot be satisfied at the same time. So actually combining them is not possible, as I will show. I'll show it with an example where basically I have two groups. I have then the black and white here, for instance, and I have people that for which I predict that they are low risk, people for which I predict that they are high risk. A plus means someone who really is a high risk person. A minus means someone who really is a low risk person. And so the minuses are people that did not recommit a crime. The pluses are people that did recommit a crime. If we then look at the whole low risk group, a calibrated classifier will assign the probability of 1/3 to the low risk category. And it doesn't matter whether you're black or white. Indeed, 1 out of 3 here did recommit a crime. Here, 1 out of 3. For the high risk group, it's 2 out of 3 for the black people and 2 out of 3 for the white people. So this is what calibration means. So what does equal odds mean? And so with calibration, we are comparing the groups in this direction. For equal opportunity, and we're basically comparing in this direction. We're looking at the errors that are being made. So if you're positive, what is the probability of ending up in the high risk group? So this is a true positive. And then if you're negative, you did not recommit a crime, what is the probability and that there will be a false positive error? And then we see, if you look at the people with the negative labels here, 50% gets assigned to the high risk group. And so these are the false positives. So that's 1/2. And while here for the pluses, if you look at the pluses, most of them are in high risk group 4/5, which is quite good, of course. This is a bit worse. If we then look at the white people, and then we see of the minuses, people that did not recommit a crime, only 1 out of 5 ends up in the high risk group. And of those which are positive, who did recommit a crime, half of them are in the high risk group. So if we compare these numbers, and so we need to compare this one with that one, that's the true positive rate. They are different. And the false positive rates they are different as well. So in order to fix this, basically we need to move pluses from left to right or minuses from left to right. If we move a minus from left to right, we will increase the false positive rate from right to left, and that's of course making our classifier better. We're improving our false positive rate by making it lower. Moving minuses here will make our false negative rate better. But if we start moving things around and minuses go from here to here, we will start changing this proportion in this direction. And there is a tension between these two, and there is no solution possible to make it fully fair. And because we can say, okay, if you want to make it, if you want to satisfy equal odds, we want to move pluses around such that the probability of being in the high risk category, if you're a plus, becomes X. And here in this, it's the same. And like if there are 5 here and 4 out of 5 end up here, and there are 10 here, then 8 should end up here and 2 should end up here in order to have the same proportion. We also fix the ones that get the higher risk if they're negative. High risk if they're negative, we fix it to the same number. So if we would do that, and then we would get here, X is a probability of ending up in this group if you're truly positive. And so of those that are positive, a fraction of X ends up in this group. So P1 is the total number of people that are really positive, and that are the number of pluses that were here in this whole region. Fraction of X should end up here on the right. N are the number of negatives, and 1 of this first group, proportion of Y ends up here, and so misclassifications. And then, of course, the rest, X 0.8, let's say, ends up here, then 0.2, and 1 minus 0.8 ends up here, and the same here. So in this way, we satisfy equal odds. If at the same time we want to satisfy calibration, then we want the meaning of being low risk to be the same for black and for white people. So if you look at this proportion and we divide them, and the percentage of positive people and the percentage of negative people, it should be the same for both groups. Here the same, a high risk, and so we're computing the odds, probability of being positive and the negative, positive and negative, it should be the same for both groups. Well, if we analyze this mathematically, and the only way to satisfy equality, this equality is in one of 3 cases. Either P1 over N1 should be equal to P2 over N2. And so in this case, if this fraction is the same as this one, and this part is the same anyway. And so then they become equal, the same here. And the only difference is that here is P1 over N1, here P2 over N2. So that's one possible solution. What does this mean? This means that if I look at the number of people having the negative label and the number of people having the positive label, that actually for black and for white, it's the same proportion. So equal base rates. This is satisfied or it's not satisfied. If it's not satisfied, and then only the other 2 options remain. And the other 2 options is that X is equal to 1, such that we get a 0 here, and Y is equal to 0, or X is equal to 0 and Y is equal to 1. Now, what does this mean, these 2 cases? X is equal to 1, Y is equal to 0. This means that everyone who is really positive gets assigned to the high risk category. Everyone who truly is negative, no one of those gets assigned to the high risk category. So this means that our classifier is perfect. And then we have also this degenerate case, and where basically we're saying that everyone who is positive gets assigned the low risk category, and everyone who is negative gets assigned the high risk category. And so that's actually the other way around. It's doing everything like exactly incorrect. And so it means the only way that we can satisfy calibration and equal odds at the same time is when either both groups behave in exactly the same way, but okay, that defies the purpose, then there is no need for a fairness intervention. It's already fair to begin with. Or if we can learn a perfect classifier, which is also not a very realistic situation. And so basically, and these two are in a trade-off. We cannot satisfy both of them at the same time. They can only be realized under very exceptional conditions, and this is summarizing for the equal odds and the calibration. The very exceptional conditions are either there is perfect predictability, and this is a screenshot from the movie Minority Report. But if we can do that, if we can perfectly predict whether someone will commit a crime or not, and maybe we should not even wait until they commit a crime, we can look them up, and that's basically the bottom line of the movie. Of course, absolutely unrealistic that we can build a system which is that good, or if there are equal base rates, and so black and white behave in exactly the same way. This result was proven again by multiple authors in multiple domains. But I think this paper here of Kleinberg and others is probably a very nice resource if you want to read more about it. I have now given it in the context of classification, and so I assign a label 0 or 1. In Kleinberg, they even extended for classifiers that are allowed to give a score in a probability. Also there, it holds that the two cannot be satisfied at the same time. So maybe before I continue, can someone tell me how, until when I have time? Because I don't know the timing exactly, and there's a time difference between Belgium
we
and
have
Greece.
Approximately 20 minutes, 23 minutes to be precise. So we are very good in terms of time. And I see there is a question also in the chat box.
Yeah, I saw it. So for the question that I see in the chat is for the equal base rates, can we synthetically achieve such an equal base using augmentation? Yeah, that can be achieved, but there is of course the question what do we want to do? We can achieve this in our training data, but we assume that then our classifier will be used in a realistic situation, in a realistic scenario, and so there, if people come from for a loan, we cannot just artificially insert additional people in order to make a classifier fair in an operational setting. So if you're looking at we want to make our classifier fair in an operational setting, and the situation is that there are two groups and they are not the same with respect to their capacity, then we cannot satisfy both at the same time. Either we're going to make errors in a different way for both groups, or if we're going to look at the label that we assign to them, and the meaning of the label will be different. And what we can do, however, is something similar to this conditional statistical parity, and maybe we can divide our whole community, consisting out of 2 or more groups. Maybe we can divide them in one way or another using a certain condition, an acceptable attribute on which we can discriminate, which is acceptable. Income, for instance, if we give a loan, if we then divide people according to this attribute, that then we get equal base rates in these particular groups. That could be a way to actually achieve this. And so without having perfect predictability, and so we could say we see recidivism rate, it's not the same between both groups. But if we divide them into 2 groups, the poor people and the rich people, and then if you look at the recidivism rate in the group of poor people, we see it's the same between black and white, and in the group of rich people, we see it's the same between black and white. And then we could actually learn 2 classifiers, one for each group, and these classifiers could in principle satisfy both conditions at the same time. Voila. All right. And this is about group fairness. We looked at the group as a whole, and then we need to decide, is a group disadvantaged as a whole? Different ways, different perspectives to look at it. We can also look at individuals, and this is often also quite interesting, where a decision has been made about one person, and we want to know, is this one person being discriminated against or not? A first approach there is individual fairness. And in individual fairness, what we are basically saying there is that we want to treat people that are alike, and we want to treat them in the same way. And so here I have a example where people are divided. Every object is a person. Some people have been hired, some people were not hired, and the green ones were hired, the red ones were not hired, and we have males and females, and the rounds are the females, the squares are the males. And now we want to know, individual fairness, is this particular instance being discriminated against? And we're not interested in the whole group, but in this specific instance. Here we have work experience on the horizontal axis, education level on the vertical axis. And one thing we can do, and this is what is done in individual fairness, and basically you can look in the neighborhood of this point. We can look at males and females in this neighborhood, and then look at how many of those received a positive label for the female neighbors. In this particular example, it's only 1 out of 5. It should have been 20%. And for the male neighbors, it's actually 3 out of 4 received the positive label. And so in this case, we would conclude that it is likely that this individual was discriminated against. And because if we look in the neighborhood of this instance, in this neighborhood, females have a lower chance of being accepted than males. This female was not accepted, and so there is a possible claim of being discriminated here. So this takes us away from all these inconsistencies that we had at the group level, and we just look at an individual level, and we can try to correct it for this particular individual. But nevertheless, for individual fairness, the principle is fine. Treat people that are alike in the same way. But what does it mean? When are two instances alike? And this is a very difficult question, because if we want to treat people that are alike in the same way, we only want to consider attributes that matter for the prediction that we're going to make. For instance, are we going to hire someone? Yes or no? If you look at the length and the weight of a person, and it's a job as a CEO, let's say, and then length and weight probably does not matter. And so it's not fair to take this into account if you're computing the distance. This also means that for every attribute, we basically need to decide, is this an attribute that can be used, that makes sense to use, for instance, education, grades, experience, but the length, weight, and the place of birth of a person, maybe we should not use that in our distance measure. The languages that someone speaks, maybe we should take it into account to a certain extent, and not fully, because that could be a proxy for the ethnicity of a person. And for some jobs, it's important to be able to speak English very well, for instance, or French, whatever. And then the languages that are spoken can be important. And so basically, one critique that I have on this type of fairness measures is that basically we're moving the problem a little bit. We're not removing the problem, but we're moving it into determining a good distance function. Let me see. I see that there is a question. Okay, that's one that will come up later. It's about the incompatibility of equal odds and calibration. That I will pick up later when we'll be talking about ways to remedy discrimination. Yeah, so this is about individual fairness. I think it's a very nice approach, but be aware that it's not easy to determine a good distance function. And if you're not able to determine a good distance function, basically your system will break down. And because you will look at people that are in the neighborhood of our point, if length and weight are taken into account when computing the distance functions, and then females will be here and males will be here, and you will not have a lot of male neighbors for your instance here, for example. Voila. So this is one part of individual fairness. Another type of measures that I want to talk about is causal-based fairness. And I know there are a lot of different things being thrown at you, a lot of different measures. Later on, we will also try to make a bit sense out of it in order to give some guidelines when to select which ones. So in causal-based fairness measures, there the question that we want to answer or that we're asking ourselves is quite similar as the question with respect to individual fairness. And that is, how would an individual have been treated if she belonged to the other group? If the treatment would have been different, then we say that someone has been treated unfair. If we look at individual fairness, basically we are trying to do the same. We look at males and females that are like the instance that we're considering. And so the only difference is the gender of the person in the example that I gave. And so we look at how is someone treated that is alike the person that I'm looking at. How is it treated if it's a female? Now, how is she treated how would she have been treated if she would have been a male? If the treatment is different, and then there is unfairness, the 75% versus the 20% that we had in our example. Now there is a lot of reasoning that you can make about it. So if someone has the same length and the same weight, that's probably not relevant for a CEO job. The education level, however, should be taken into account. The race should not play a role. I should not use it as an attribute, but the education level may depend on the race. There might be all kinds of correlations. And that is where basically causal models and a technique that already exists for a long time, people started realizing that this may be a good formalism to express and to reason about how data is generated and explaining how variables influence one another. So here is an example of a causal model. This is an example from a paper about counterfactual fairness, where they look at people being admitted to law school. And the admission procedure is based on the grade point average, the result of LSAT, a standardized test, and there is also the first year average. And so that is basically the thing we want to predict. Now, one thing that they observe, and so through studies, historical studies in the domain of sociology, basically we know that some of these things are actually biased in the sense that the race will influence the grade point average that you may have, may influence your LSAT score, and may even influence your first year average that you have. Of course, not only race and gender influences that, but also the knowledge that you have. But the knowledge that someone has is typically something which is unobserved. If we would know how knowledgeable someone is, then we wouldn't need the tests. And basically we use the tests as a proxy for the knowledge of the person. But these tests may be racially biased. Now, the grade point average may be influenced by the school that you went to. The school you went to may be influenced by the neighborhood where you live, which may be correlated with your ethnicity. Also the gender. For the LSAT test, maybe there are some language-based questions that require you to be very fluent in a certain language. that might be correlated with your ethnicity. So basically it means that if we look at people from different race and different gender, but with the same knowledge, and that then the GPA and the LSAT may be different. And a causal model is able to express this type of dependencies, and it also, and the direction of the edges is also important. The direction of the edges shows you how things are causally related. So if I would take a person and I would change the race of the person, but keep the knowledge the same, and then I expect that the GPA, the LSAT, and the first year average might change. But if I take a person and I change the LSAT score of the person, and then the race of the person or the gender of the person will not change, and also the gender of the person, and the knowledge of the person will not change. If I take the same person, I change the knowledge, and then the GPA and the LSAT will go up. And so this is, in these models, they allow to reason in a causal way. And if we have such a model of our reality, it allows us to reason about whether some label that we assign to people is discriminative or not. Here is another example for recidivism. It's not exactly the example that is in the papers, but one that I made myself. And so we have the race. Race may influence prior conviction. Unfortunately, some groups are being targeted more often, and they are more likely to be convicted. Gender also influences prior conviction. The age of a person may influence it. Young males may be more easily convicted, for instance, either directly because of people are being prejudiced, judges might be prejudiced, or maybe because there is an aggression problem which is unobserved, but which might be correlated with the age and the gender of the person, and may directly influence a prior conviction, and a prior conviction may influence recidivism. And so this allows us to make causal reasoning. If I would change the gender of a person, and then the prior convictions may change, the level of aggression may change, and the risk for recidivism may change as well. So our causal models, they allow to estimate the effect of an intervention, and an intervention is expressed by an operation do, and do means that you will actively change one of the things. And important to realize is this inequality, that the probability of having a certain label given X and that you do a certain treatment is not necessarily the same as the conditional probability of looking at the outcome Y and looking at people with the same attributes X, except for the treatment. Let me give you another example that will make this immediately clear. And suppose we have two groups of patients, and one group of patients is given a medicine A, another group is given the medicine B, but the reason for giving medicine A or medicine B is related to the severity of the condition of the patient. So medicine A is a very cheap one, medicine B is a very expensive one, so we will give B to those patients that have a more serious condition, and A to those who have a mild version of the condition. Then what is the difference, and where do causal models help? And so basically, if you want to see what is the effect of medicine A and medicine B, then we are interested in, if I have a patient that received medicine A, the cheap one, what would have been the effect if I would have given him medicine A instead of B on the outcome? And that is different from, I will look at all the patients that have the same characteristics as this patient in my data, and that were given this other treatment and their outcome. And this is because the treatment is actually correlated with the severity of the condition, which here I assume is not in X. And so this allows us to make these derivations. And let me reiterate once more here. If I would apply conditional probabilities, then if I would change I would take an instance in my data set and would change the LSAT score, then it would change the probability that he belongs to a certain race because of the LSAT score being correlated with the race. If I look at interventions, then I look at an instance, and if I would change the LSAT score of this person, it would not affect the race because there is no causal relationship from LSAT to race. Apart from the fact that it is incredibly difficult to come up with this kind of causal models, and that there are always a lot of discussion on whether a causal model, whether an arrow should be in one or the other direction, or maybe some edges should be added. Apart from that, if we do have a causal model, then we can look at interventions and what will be the effect of interventions. And now finally we arrived back to fairness, and then we can look at things like counterfactual fairness, where we say that a label that we give to a person is counterfactually fair with respect to a sensitive attribute A and data X that we have for this person, if it holds that for all possible data and all possible sensitive attributes, it holds that the decision that we would take for this person, which has label A and which has a certain ethnicity, if the label would have been the same if this person would have been black or if this person would have been white. And we model this as a treatment, because if the person would have been black, then he would have gone to a different school. He would have lived in a different neighborhood. So these things change if we apply this treatment and are taken into account when we make our prediction. And so to paraphrase what is in the paper, changing A while holding things that are not causally dependent on A constant shouldn't change my predicted label. Often we want some variables to causally depend. Often, however, some variables may causally depend on a sensitive attribute, but it may still be acceptable to base a decision on those variables. For instance, education level may indirectly depend on race and sex because of the neighborhood where you live, and you go to a school in your neighborhood, and schools in black neighborhoods may be underfunded, having a direct effect on the education level. Even though that might be true, when we want to hire a person, we can still take into account the education level, and it would be considered to be fair. If you want to make this differences, and then we can look at path-specific effects. And a path-specific effect will be the effect of one variable on another one along certain causal paths in the graph that we have, where some of those can be allowed, be fair, and others being disallowed. So if you look at counterfactual fairness and causal models, and fairness in the context of causal models, and it basically means that we are able to express with our causal model how things are causing, some variables are causing some other variables. And here, for instance, I would say, if we want to predict recidivism, we do not want to have this direct link from race to recidivism. So this is a path-specific effect that we want to remove, but we want to take into account prior convictions of a person. We want to take into account maybe aggression, which is unobserved and which only observed indirectly, and correlations with race through prior convictions are allowed, but direct correlations are not allowed. I'm not going to go into formulas. There is a lot of research in this domain, also about which path-specific effects are identifiable and which ones are not, which basically means which ones can be estimated consistently from data and which ones are not. I'm running out of time, so I'm going to wrap up a little bit. And so conclusion about fairness measures. There are many different measures, and a bottom line I would say is that when looking at these measures, you need to take into account what kind of implicit assumptions these measures are making. With statistical parity, and there was this assumption that the labels as they are in the data set are not necessarily the correct labels. If that is a correct assumption to make, a statistical parity might be a good one to look at. And equal odds will not be a good measure. On the other hand, equal odds is a good measure if you assume that the labels in your dataset are indeed the correct ones, and you do not want to amplify errors, and you want to actually achieve some kind of status quo where the errors that you're making in both groups are actually very similar. Sandra Wachter has a very nice recent paper also about this, about some measures being a remedy for discrimination. If you optimize them, they actually remove discrimination, and other ones that basically try not to make the situation worse. Calibration, and that makes sense if you look at it from a perspective, and this is just one step in my decision. I will base further decision on the labels that are given, and so my label should not correlate with the ethnicity, and then this individual fairness measures. So for the outlook, I would say this causal-based fairness is definitely something to keep an eye on. A lot of work being done there, and this also allows us to reason about fairness if we have a lot of information about how things are related. And so we know that the place where someone is living is related to the race of a person. Whether you should give someone a loan or not might be depending on the place where he lives. If he lives in a very good neighborhood where houses are attractive, you will more easily give a loan. So that aspect you want to take into account, but not the aspect that's correlated and that's a proxy for the race of a person. And so this type of things and causal-based fairness, we can go much more fine-grained. So I will now skip immediately to the end of my talk. There are a couple of more slides about how you can actually, if you know the measure that you want to optimize, how you can algorithmically optimize for that measure. Let me just give you one example. If we want to achieve equal odds, and so equal odds was this: if you deserve to remain in prison, then the probability of receiving the high risk label should not be dependent on your race. If you want to realize that, and basically the paper of Hart and others give a method of that. With equal odds, we want to realize that the true positive rate and false positive rate are equal for both communities, and so the errors that are being made should be equal. And so basically what we could do is we could look at the ROC curve, and we can split our classifier into two classifiers, one for A is equal to 0, one for the group A is equal to 1. The ROC curve plots the true positive rate versus the false positive rate. And so basically where the two intersect, and this is a place where the true positive rate and the false positive rate are the same. And so basically we can choose our thresholds, and we can choose different thresholds for A is equal to 0 and A is equal to 1. And by moving our threshold, we move along the AOC curve, and by picking a threshold as such that the two intersect. If they do not intersect, we can always change the models in such a way. Basically, if we have an ROC curve, then any point in this region here is actually achievable, is attainable, and so there will always be an overlap between the two techniques. And so this is, for instance, one way to fix it. Another way, if you look at demographic parity, would be where we do this augmentation, and to come back to Erini's question at some point. there we could resample our groups in order to make our training data satisfy the demographic, the statistical parity. And then when we learn a classifier on it, because the classifier is trained on data in which both communities had the same capacity, so it's also likely that it will make predictions where both groups have the same capacity. So to summarize, machine learning models are not fair out of the box. I spent quite some time there. That's why now I run out of time. If bias goes in, bias comes out. There are tainted labels in our hospital example, for instance. Fairness is then the question, how can we build models that optimally avoid certain types of bias? But we need to be aware that bias is partially inherent to decision making. Unequal base rates between groups provably leads to differences in treatment. Either we will make different errors in this group, or the access to the benefit will be unequal between two groups. But a positive message to end with, fair models may actually be more accurate than unfair models if we measure them against a world in which the assumption that we made for a fairness measure actually hold. And so this concludes my talk, where basically my statement or my final statement is that ethical machine learning is not about maximizing accuracy with respect to your test set, but about maximizing accuracy in a fair world, and where I live in the middle and what it exactly means to be in a fair world. All right, I'm sorry for going slightly over time. Can I still take some questions or?
Absolutely. We have time for a couple of questions. We are out of time, but we have time. It was an excellent talk, so we want to share the questions as well. Mm-hmm. Okay, so I'll pick some from the chat. So Sihem is asking, does the work on fairness in binary classification extend naturally to multi-class classification? Yeah, that's an excellent question, and because in my whole presentation, I made the simplification that there are only two groups and there are only two classes. Some of it does, some of it doesn't. I would say, for instance, all the work on causality, there it doesn't really matter. If there are multiple classes, it extends in a natural way. For demographic parity, you can always do a one against all if you have multiple groups, or you have multiple. It's about binary classification versus multi-class classification. Yeah, so there it would probably work as well, because you can do a one against all type of classification, and then require that it holds for all the classes. If you look at, for instance, the work of Hart and others with the equal odds, and there I don't see how you can immediately extend it to multi-class classification, because there for the AUC curves, it is important that you only have two classes in order to draw the AUC curve, but there might be similar things possible there. So to summarize, for some of the techniques, it extends naturally, but definitely not for all. The question you're asking is about one direction where we can extend it, from the binary classification to multi-class classification. And there is also another dimension. And when we go from two sensitive groups to multiple sensitive groups, and there it's also the same. And for some methods, it will generalize naturally. For some others, it will not. Then there is a question about the place where someone is living, if that is biased. For instance, US and EU have different city structures. In the US, expensive houses might be away from the city centers as opposed to in the EU.
Yes, that is definitely true, but this is something, a relation that you would expect your classifier to pick up from the data, that it will pick up that and probably also depends from city to city, because for instance in Brussels it might be more beneficial to live near Brussels than inside of Brussels, while for Antwerp it might be the other way around. It might also depend on the neighborhood that you end up with. So I agree, and the place of living is biased, but you would expect the classifier to learn this bias and to learn for which city is beneficial to live inside the city and for which city it is beneficial to live outside the city. But the point that I was trying to make there when I raised this issue about about place where someone is living, is that this is an attribute and that's not always clear cut. This attribute I can use, and this another attribute I cannot use. And sometimes you can use an attribute partially. And for instance, the place where a house is located that someone wants to buy and he wants to get a loan, or she wants to get a loan for that house, might carry valuable information about how nice the neighborhood is, and for the bank's perspective, if you default a loan, it's better to have a mortgage on a house which is in an attractive neighborhood, and so they will more easily give the loan in an attractive neighborhood. But at the same time, it's also proxy for race, and so it's actually somewhere in between. So you can use the place where someone is living, but not in order to use it as a proxy for the race, but to use it as a proxy for the attractiveness of the neighborhood. Voila. I don't know if there are still some questions out. I think I covered most of them.
That is true. Thank you so much. It was an excellent talk. I think it was a great start for the school. So we are grateful. There may be some additional comments or questions coming up in the chat. So you may continue there. Let's now take a break. We will be back in approximately 15 minutes. And we will continue then with the working groups. So see you in 15 minutes.
Right, thank you.
Hello again, everyone. Welcome from the break. We're now going to talk a little bit about the working groups. So let me share my screen. Okay, so we have already formed 10 groups with about 6-7 people each. The groups were randomly formed with some post-processing to achieve diversity. And we have a small assignment for each of the groups. We have the detail. You will have the details soon. You will work together as a group, and you will prepare a short 3-minute presentation. And we have more details for this in a while. Okay, so why working groups? We wanted for you to meet and somehow network. We cannot meet in a physical place, but we thought it would be a good idea to have small groups that will discuss with each other, be exposed to diverse views and backgrounds, and be able to collaborate and get the opportunity to think a little bit about fairness and its implications. So we have come up with 3 general questions. And for each one of them, we would like to have just one answer per group. And then you will have 3 minutes to present your answer, your views on these questions at the end of the school. So this is the first question. The first question is, we're asking you to name what you think are the 3 fairness-related problems that are the most pressing, relevant, or interesting. And here you can be as creative as you want. You can answer in general or pick a specific application domain, for example, healthcare, education, or recommendations, or web search, whatever. Or you can choose a very specific and concrete problem, for example, a problem that you have faced, or a very broad and fundamental one. Okay, so this is the first question. In the second question, we want you as a group to reflect on what you have learned in this winter school and on possible ways of applying what you have learned in your research, your work, or even your daily life. And this is an open question in the sense that you can give a couple of examples, different kind of examples. For example, you may have liked a model or a concept or a method, and you think that you can use this model, your concept or method in your research or in your work. Or you can reflect on how what you heard here, the examples, for example, that you hear this morning were invited about by our speaker, have changed your perception about the fairness of various systems. For example, how a recommendation system works, or how job recruitment works. Or you can even suggest courses that you wish you have taken or would you like to take in the future. So in this question, we want you to reflect on what you learn and think of how this may affect your work, your life, or your research. The third question is more fun question. So the idea here is that we want you to be creative. So imagine that your group is invited to create a plot for a movie, a mini-series about some dystopia that was created by an unfair AI application or algorithm. Of course, you can be optimistic. Everybody loves a happy end, right? So you may be, your group may be the hero scientist that by addressing unfairness, save the world. Okay, so we want you to come up with a short summary of the plot to pitch your idea for a screenplay. Using we want it to be short, like 150 words. Okay, so this is the assignment. So we ask you to think about these questions and prepare a 3-minute presentation of your answers. And this will be presented at the last session tomorrow at 5:30 Greek time. Okay. Now, some logistic. We have created one Zoom room per group. You will be automatically redirected to the dedicated groups at specific times. In these rooms, you have full functionality. And the time we have allocated for these groups is in this session today, by the end of the session. Today, after the last presentation at 5:30, and tomorrow, just before the last session. Of course, you can meet with your group outside the school, and you can arrange for that. Okay. Christo, we will share this with these slides with the attendees, right? Now we thought that this is a good time to take like a group photo. So I will stop sharing. And Christo, would you take over?
Yes, if you would like, open your cameras to take the photo.
Hello everyone, nice to see faces.
Okay, now 1, 2, 3, smile. Perfect. Thank you very much.
Thanks everyone. If you have any questions, you can ask them now. Okay, so
hi. Yeah, hi, I have one question. Yeah, hi, my name is Karima. So
hi.
Just hi. About the presentation, it will be per group or per individual?
One per group, yes.
One per group.
One per group.
Like work together we prepare the thing and then one of us will present it.
Right. Unless you want in these 3 minutes to have more than one person to talk, but
yeah,
but it would be one talk per group.
Okay, I see. Thank you.
Mm-hmm.
We are now ready to move to the breakout rooms. Are you okay?
Hi, I'm just reporting from group 1. Everything is fine. They were trying to figure out how to share things.
It's me. You are now live on YouTube, so maybe please wait until please join again the speaker room.
Okay.
Everyone, welcome back. We are now streaming on YouTube, so please keep your cameras and mics off. Thank you.
Hello, everyone. Welcome back from the break. I hope you had a nice time, and it's now time for the next event, for the next talk. And it's my great pleasure to introduce Sihem Ahmed Yahia. She's a silver medal research director at CNRS, which is the French National Center for Scientific Research, and deputy director at the Lab of Informatics of Grenoble. And she works in the area of exploratory data analysis and fairness in job marketplaces. So today she will talk about fairness on online labor markets. And before joining CNRS, she has held many interesting positions, for example, in the Qatar Computing Research Institute, at Yahoo Research, AT&T Labs, etc. And she currently leads the Diversity and Inclusion Initiative for the data management community. And she's actively involved in the community. So, for example, she's a BC chair for SIGMO 2023, and she's the vice president of VLTP from 2022. Sihem, thank you very much for accepting our invitation, and it's our great pleasure and honor to have you here. The Zoom floor is yours.
Thank you, Irini. Thank you, everybody. Thanks to my friends and colleagues for organizing this great event and for inviting me. I'm sharing my screen right away. So this should be okay, I guess. Let me just move something around and we'll be all set. Okay. All right, so hi everyone. So I'm going to be telling you about fairness on online labor markets. And what Toon told us this morning is fairness in classification. And what I'll be focusing on is mainly fairness in ranking, because what happens on online labor markets is that people get ranked. So are you all seeing my screen properly? And you're not seeing anything else, right? So because I had a bit of an issue earlier. So I'm assuming this is working. Okay. So what are online labor markets? Online labor markets can be defined as web destinations where one finds work. They can also be seen from the perspective of people who have work to provide as open calls to hire cheap, immediate, skilled, and easily accessible labor online. They act as intermediaries between people, and in particular, they can be classified, roughly classified, into crowdsourcing platforms and freelancing marketplaces. So on crowdsourcing platforms, work presents itself in the form of microtasks. Example of microtasks are image labeling, where people are asked to identify what is on a picture. For instance, a damaged building, when the goal is to label images for the purpose of training algorithms for the automatic identification of damaged buildings after, for instance, an earthquake. Tasks can also, on crowdsourcing platforms, can also be provided in the form of collaborative tasks, where more than one individual collaborate together to complete a task. For instance, people could be asked to go out together and take pictures of the biodiversity of insects and plants all together and deliver the result of achieving a task together. The second type of online labor markets that will be really the focus of our talk is freelancing marketplaces. On these labor markets, work presents itself in the form of microgigs. And microgigs are basically, mini jobs that can be done entirely virtually. For instance, hiring somebody to prepare a resume for you, or, and I won't recommend it, do your homework. But they can also be partly virtual and partly physical. For instance, you could hire someone to design, you could hire someone to design a website for you that would be entirely virtual. The hiring is virtual, and the individual, you don't even need to meet that person. But you could even also hire someone virtually but that person could come to your place and fix your plumbing problem you may have. So schematically speaking, these freelancing marketplaces present themselves as follows. You have workers on potential workers, right, on one hand, and you have micro gigs that are provided by job providers or requesters. And many such platforms exist out there, including TaskRabbit, Kappa in France, Google for Jobs, and so on. Okay, so you can see that the platform sits as an intermediary. So let's now look at discrimination at work. So discrimination at work has been studied extensively from very early on, and it is generally defined as the unbalanced targeting of workers based on their protected attributes. These attributes are also referred to as sensitive attributes or discriminatory attributes or discriminatory patterns. For instance, the French criminal law lists 25 such attributes. So if you can explicitly bring a proof that you have been discriminated along one or many such attributes when compared to others, then you have a case in the court of law. What happens with online labor markets is that they blur the boundary between physical and virtual worlds, as we have seen just earlier. And there are many actors, not just two actors, right? And most of the legislation has been designed to regulate the relationship between employer and employee, right? In our vocabulary, requester and worker. While here we have additional actors such as the platform. So from a legal perspective, the fact that digital platforms interface between several economic players makes existing legislation difficult to apply. Many different legislations could be taken into consideration: competition law, criminal law, consumer law, labor law, and so on. Also, there are two notions. There is a notion of an alleged offense. So you go to a court of law and you say, I have been discriminated, for instance, for acquiring a job or in a recommendation that I have gotten. But if you cannot bring proof that allows observing such an offense, then you don't have a case in a court of law. So to observe, we need to be able to quantify that there has been a discrimination. And one more thing about the legal perspective. In France, since 2016, there is a new article in Consumer Code here that includes a legal definition of what online platform operators are. So before even starting to regulate these platforms, now one needs to introduce exactly the specific operators that intervene in those platforms. So this text of law is a precursor at the European level. And it considers platform not only as an interface between two or more economic actors, but also as an intermediary between the state and the public at large. In addition, this legislation requires platforms to provide information to their users on how recommendation algorithms in particular work. And that has been considered as a very, very first step toward legislating these online platforms and providing protection for individuals. But we all know as computer scientists that simply explaining how a recommendation algorithm works, or even making it fully transparent, is not enough to make a case for discrimination. So in particular here, we're going to be looking at ranking, because on online freelancing platforms, this is what happened. So let's take a very simple example where we have a set of men, a set of women, and where each one of them has a certain relevance to a search, a job search. For instance, I want to hire somebody for event staffing. So if I only look at the relevance, what's going to happen is that all men are going to be ranked higher than women, despite a very, very, very small difference in aggregated relevance of men and women. And this is simply proper to how a ranking algorithm that is based on relevance is going to work. And that's something we all integrated, right? In a just a regular, search, Google search online. The organic search that we obtain, we tend to look at it from top to bottom, which means that the exposure of individuals is a function of how high up they are in the ranking. And if we know how to quantify this notion of exposure, in addition to taking into account the relevance, right, then we can observe, we can quantify that despite this difference in relevance, exposure of, or the average exposure of males here is higher than the average exposure of females. And we will come back to these notions of exposure. So let's first take a first study that was done a few years back on two platforms, TaskRabbit and Fiverr. So how does TaskRabbit function? So on TaskRabbit, customers that are considered customers of TaskRabbit, meaning paying actors, meaning job providers or requesters, provide a category of interest. They also provide their address and specify dates and times. Potentially, for instance, if you want to hire somebody to come help you move furniture, you specify a number of criteria, such as date and time, and also when you would like the task to be performed. And the notion of query result, the result that you get as a customer, is basically a ranked list of workers with a picture, their expected wage, so workers have entered that information, and reviews from prior tasks that workers have achieved. And a customer may write a free text review and rank the worker or the tasker with a thumbs up, thumbs down. Okay, so one can see that there is also feedback from people who hire others. So that was for TaskRabbit. On Fiverr, the other platform that was studied, a customer inputs a free text search query, and that text search query returns a ranked list of tasks and not a ranked list of workers. For instance, your text query could be web design, okay? Then the task serves as an indirection. By clicking on a task, I get to see a set of workers. And in particular, I get to see for each worker, a worker's profile page that contains performed tasks, customer reviews, and an average rating for that worker from the beginning, from the time that worker started being online. And just like in TaskRabbit, after a worker has been hired by a customer, the customer may write a free text review and rate the tasker from 1 to 5. Okay, so this is the setting where the work was done. And here's an example of how this presents itself. In particular, the case where you're searching using a search query such as web designer. And this example comes from Kappa, which is a site that is available. In fact, Kappa is a startup in Grenoble, where I work, and with whom we have been exchanging on this topic. So here you can see that on the left-hand side, you can set up a number of conditions, and you can basically say that you want to, Okay, you can set up a number of conditions, and you can say that you want to hire people, and then they're returned ranked, and the system will rank them. Okay, so let's look at how the system works in the backend, or all these systems work in the backend, right? So as input, what we have is a query and a set of workers. And this table is showing a number of individuals, okay, each line per potential worker. And also, I'm distinguishing in red the a number of attributes that are demographics attributes and that are considered as protected attributes, but there are also inferred attributes on the right-hand side, which are attributes that the system is going to infer about you. For instance, you have taken a test online, or you have an approval rating, which is basically the proportion of tasks that you have completed that have been accepted. And all of those are things that are potentially used in the backend by the system. And let's say that in one particular case, I am going to be returning a ranked list of workers based on a function that is provided by the system. For instance, if the query is about finding somebody who can translate a piece of text for me, then the function naturally is going to be combining a language test that that person has taken with an approval rating from the system that gives me, how serious that worker is on the platform. So as Toon said this earlier today, the algorithm or the function or the ranking logic does not necessarily have to use protected attributes. Okay, so this one in particular is simply combining some attributes that make sense for the task that I need. Okay, but despite that, there may be hidden correlation with the protected attributes or the red attributes that end up favoring some groups of individuals over others. Okay, so what does it entail to study discrimination on online labor markets? So what it entails is to first collect data, okay? Because we are not the ones who have designed the algorithms. We don't necessarily know how the actual ranking is done. What is the logic of the ranking for individual on individual platforms? So the first thing that we need to do is to launch a number of queries and get the rankings of individuals that are returned. Then potentially we may need to enrich the data because some of the protected attributes may not be available. So we need to do something to figure out, what are some of the attributes that describe the individuals. And then we need to quantify discrimination. So let's take this example of work that was done a while back. And it was this case study on TaskRabbit and Fiverr. And the three questions that were asked were, how do perceived gender and race, and in particular in this work, only two protected attributes were dealt with. How do perceived gender and race and other demographics, more generally, influence the social feedback workers receive? And the social feedback here is basically the reviews and the thumbs up, thumbs down, and the ratings that individual perceives. The second question is, are there differences in the language of the review? Do people choose to write reviews differently depending on whether someone is Black or white or male or female and so on? And finally, the third question that was addressed was, do workers' demographics correlate with their position in the search results, which leads us to the question of discrimination in ranking on freelancing marketplaces. So in this work, as I said, TaskRabbit and Fiverr was used for this period of time, in 2015. And so the data was collected from those websites by launching several queries, either basically queries that rank individuals or rank tasks. And the statistics are given here, about 13,000 search results for TaskRabbit, 7,000 for Fiverr, with some information about the demographics. And this information about the demographics was not actually provided by those websites. So what the authors of the paper did is they crowdsourced the images of people to infer gender and race. Okay, so this is the part where data is enriched based on the profile images of the workers. Okay, and these statistics in the table come from that phase. So I'm going to give you a summary of these findings, okay? Because what I want to do after that is describe a piece of work that we did where we took a step back and formalized all these problems together into a single framework. So basically, this is what was found by analyzing the data, right? And all results are statistically significant. So on TaskRabbit, it was observed that women, especially white women, received 10% fewer reviews than men with equivalent work experience. Okay, so some of this information was available in TaskRabbit, such as work experience, and some of it was, as I said, labeled by crowd workers using the profile picture. It was also observed that Black workers, especially men, received significantly lower feedback scores, right, meaning the ratings, than other workers with similar attributes. It was observed that workers who are perceived to be Black, especially men, received over 30% fewer reviews than other men. They also received significantly lower rating scores. And only workers with no profile images received lower ratings than them. Also, about the language of reviews, reviews for workers perceived to be Black women included significantly fewer positive adjectives, while reviews for Black workers in general use significantly more negative adjectives. And finally, workers perceived to be Asian, especially men, receive significantly higher rating than rating scores than others. It was also observed that the ranking algorithm produces results that are significantly correlated with race and gender. And this was the part that had to do with, is there any correlation, even if allegedly those platforms do not explicitly use race and gender for ranking. In fact, that correlation was observed. It was observed that the ranking was changing from city to city. So basically the feedback from people, if we assume that the ranking is learned, right, based on the thumbs up, thumbs down, or generally the social feedback obtained, then seemingly one could say that the ranking is very much dependent, the social feedback is very much dependent on people in different places. Well, a plausible explanation is that the algorithm is designed to take customer behavior into account, which is most likely to be the case, which is the case, for instance, for most ranking algorithms online, such as, for instance, Google search would take, the feedback, the social feedback on all sorts of signals, including the fact that you click or not on some links, into account. So there is this loop that is happening between the feedback that is received by individuals and their ranking, beyond the fact, that they are qualified or not for a job. And on Fiverr, in fact, the results were inconclusive because at the time, the authors did not know how to deal with the ranking of tasks. And hopefully in the next part, I'm going to show you how to do that. So let's take a step back, okay? And the purpose of taking a step back here is to try and set up a framework for designing a fairness model on freelancing marketplaces. So what are the elements that we have been considering in this first part of the discussion? The elements are user groups, right? And by the way, referring back to Toon's talk this morning, I am interested in group fairness, right? So it's like that first branch that he described, and not individual fairness, okay? So what are we dealing with here? We're dealing with a set of labeled groups, right? So groups that are labeled with protected attributes. We're dealing with a set of locations because the people look for jobs in specific locations or from specific locations, right? Sometimes, in particular, the jobs that are not all fully virtual. And we're also dealing with a set of job-related queries, right? So what a query is home cleaning, logo design, website design, and so on. So these are our elements, the elements that matter. And what we'd like to do is to compute at any moment, right, for any combination of group, query, and location, a discrimination value, okay? And the way I'm going to be defining this discrimination value to encapsulate a variety of fairness measures is by saying that the discrimination of a group for a given job or query at a given location is basically computed as the aggregated, or in this case, the average, pairwise distance between that group and every other comparable group, which I'm going to call the variance of a group. So what are the variance of a group? The variance of a group are defined along one dimension, on one attribute. If my group is Black women, then my variance would be Black males, okay, along the gender. Or they would be Asian women along the ethnicity, or white women along the ethnicity. So by changing one attribute at a time, I consider that these are the comparable groups that I have. So if my group is Black women, it's going to be compared against all these comparable groups, compared with some function And the discrimination of Black women for a particular search or a particular job or particular query at a given location is going to be computed as an aggregated value. Okay? So what this allows me to do is also to put a wildcard for queries and for locations. So if I want to know how my group is discriminated against across all job searches at a particular location, I can do that. Or if I want to know how my group is discriminated against for a particular job search across all locations or in a given region of the world, I can do that. So I'm going to give you some definitions we used, okay? And then I'll talk about how we ran our experiments. In fact, this work, we did it both on Google Job Search and on TaskRabbit. Okay? On Google Job Search, what happens is that jobs are ranked and not people. And we'll go into the details of how we're computing the discrimination of a triple group query and at a given location. On TaskRabbit, as we have said earlier, people are ranked. And what I'm going to be doing is computing the discrimination of a group for a query at a given location as in many different ways. So one way to do it is by looking at the exposure of the individuals, okay, an aggregated exposure of individuals as a function of their position in a ranked result, and combine it with the relevance of those individuals. Okay, so if I look at it at the individual level, so at a particular worker level, which is the exposure of W, given that I don't have the internals of the algorithm, right, and I am just scraping data and getting ranked lists of results for particular queries at specific locations, I'm simply going to be computing exposure as a function of the rank of the individuals or their position in the result of the search. Okay? So basically, the higher the rank of a particular individual, the higher its exposure. And same thing, I don't have the actual value of the relevance that was computed in the system to rank the individuals, and I'm going to be computing the relevance as a function of the rank of the individual, okay? And then I'll aggregate all these for a particular ranking of, say, 50 people, for instance, in a particular group. I will aggregate them and I will compute the absolute value of the difference between the exposure and the relevance. And this gives me one notion of exposure. There are many, many other notions. I can also look at the distribution of scores or the distribution of ranks in my case, right? That have been assigned to individuals in a group and compute a distance between those distributions. This is what the EMD, or the Earth Movers distance, is doing. It's simply saying that the distance in exposure of individuals in a group G and its variant G prime is a difference between the histograms, or a distance between the histograms of their rankings. There are, as I said earlier, many ways of expressing this between G and G prime, between a group and its variant. And earlier today, Toon told you about a number of other ways to do that, such as statistical parity, or many others that were redesigned, particularly in this other paper from Cornell, redesigned to be applicable to ranking, right? Since now we're talking about ranking and not classification. So let's go back to what we defined, okay, earlier. So as I said, what I'm going to be doing is simply computing the discrimination of Black females, say for a particular query and at a particular location, okay. And let's say that the result of my query is what I have at the top of my my picture here. Right, so I have two ladies, W5 and W7, that were ranked in this order because they are ranked on basically on some value, and I am going to be computing their aggregated exposure, which is basically based on what I had shown earlier, right? So the formula that I use, that is based on the individual position of individuals in the list, is going to be used to compute the exposure of those individuals. And that gives me a certain value. And I can do that also for all the comparable groups, right? Black males, Asian females, and white females, okay? And aggregate that information. And that is going to give me, in this case, 0.19 for exposure, 0.15 for relevance, and I'll compute the difference, the absolute value of the difference, and it gives me a single discrimination value for that group of individuals against all its variants for a given query at a given location. Similarly, for EMD, as I said earlier, I can plot I can compute the distribution of ranks of individuals in each group and compute the discrimination of that individual for that query at a given location as simply the averaged distances of the rankings of all its comparable groups. So that's for the case where we're ranking people. Now on Google job search, or we also looked at Facebook job search, what happens is that people search for jobs. And what they see as a result is a ranked list of jobs. Okay, so we are in a different setting where it is not the requesters that type a query and get a ranked list of individuals, as just saw for TaskRabbit. These people who are looking for jobs, and they get to see a ranked list of jobs. Okay, and one way to compute discrimination is to simply look at individual rankings of jobs that are obtained by people in the same group, for instance, here for Black females, and compute the difference between the rankings that are obtained by people in their variants or their comparable groups, such as Asian females. Right? One way to do it is in a rank-aware or non-rank-aware. In this example is simply one that shows how to compute the set-based distance between the set of jobs that were offered to me, right? To all the ladies who are in the group of Black females, and the set of jobs that are provided to the ladies that are in the group of Asian females. And you can see here that it is all an aggregated pairwise difference. Okay? So by doing so, I'm able to assign, again, a discrimination value to a group for a given query at a given location, regardless of whether it's people who are ranked as a result or jobs that are ranked as a result. And of course, here, more than one way of comparing sets of results can be enforced. So what is the benefit of doing that? The benefit of doing that is that now I can take a step back and start asking questions or solving problems on top of that generic model. And we've identified, we designed 3 types of problems, right? So one type of problem is what can be called worker fairness. Okay. So what this problem does is that it takes the data as input, it computes all those discrimination values that we know how to compute based on our definition of discrimination of groups, and then it provides as output groups. Okay? For instance, here I can look for the 2 groups that TaskRabbit discriminates the most against, regardless of the query, meaning the job or the location, or I can make it specific to a location, right? I can also have another type of problems. I can search for what we have called query fairness. Okay? So in this case, what I'm doing is I'm taking the data as input, and as a result, I have jobs. Okay? So in this case, an example would be, what are the 5 least discriminating jobs for Asian males at all locations? Okay? So I could look for the 5 discriminating jobs for Asian males in California also, right? And finally, we have this other type of queries that are location fairness. Here, the result is going to be a set of locations. So out of a number of locations, which one is the least discriminating for women looking for an event staffing job on TaskRabbit? Okay. So these would be the type of queries that the the framework enables. And then we can also do other things. We can start doing comparisons between groups. So for instance, a group comparison would compare two groups across a number of locations. Here, I could, as an example, I'm able to say something like, I've quantified the discrimination for males, regardless of jobs, regardless of locations, okay? And same thing for females. And I can see that, in fact, here, the higher the values, it is a discrimination that I'm quantifying, the higher the value, values are between 0 and 1, and the higher the value, the higher the discrimination. So what this is telling me is that females are at least 1.5 most likely, 1.5 times most likely to be discriminated against across all locations for all jobs. Okay, you may think this is a very coarse, sort of quantification, and I might want to break it down per location. And in particular here, I'm only showing 2 locations for which the trend is reversed, where males are more discriminated against than females at these locations. And this data comes from TaskRabbit. And this is across all jobs. But of course, you know, I may be interested in looking at specific jobs or job categories. Okay. Similarly, I can be comparing queries or comparing locations, meaning that my the 2 columns that I have here won't be male and females or groups, but they would be, for instance, 2 jobs, right, that are compared for different locations or for different demographics. So to enable that and do that quickly, because obviously we're dealing with a number of groups and queries and locations, we've designed several indices, right? So we've designed 3 types of indices. So there is an index that we call group-based index that records, basically it records a ranked list of groups and associates to each group on the left-hand side here the discrimination for that it has that it experiences for a particular query location. Okay, so this index would be created for each query location pair. Okay, or if I'm interested in aggregated queries and aggregated for certain job categories or aggregated locations for certain regions in the world, I could create it for those. I can do that also for the other 2 dimensions, which is to create an index of jobs, right, for group location pairs, or to create an index of locations for group query pairs. And this facilitates processing and allows me to use, for answering the type of queries that I stated, to use algorithms that are very fast, Fagin algorithms that are top K algorithms that are very quick. So let me tell you about the results of our experiments. And so what we did here is, as I said earlier, we've used TaskRabbit, over 3,000 workers, over 5,000 query location pairs. And basically we crawled the results of running these queries on TaskRabbit. And we scraped the ranking of workers on that platform. And we ended up with about 56 cities, mostly located in the US and a few in the UK. On Google Job Search, the approach was different. As I said, on Google Job Search, jobs are ranked, not people. And so what we did is that we, in fact, used TaskRabbit to bootstrap our search queries for Google. And to do that, we took the top 10 and top bottom query location that we had from TaskRabbit, and we generated, for those queries, we generated equivalent search terms using Google Keyword Planner, and those became the search terms that were used to run queries. And to run the queries, we developed a Google Chrome extension that basically just sets the browser location automatically and runs queries, every number of minutes to sort of deal with the noise and so on. Okay. So how were the experiments deployed? So on TaskRabbit, as I said earlier, we basically went ahead and ran a number of queries. And for each obtained ranked list, we crowdsourced the result to other individuals to assign gender and ethnicity. Okay? So we did just like our colleagues from Cornell, because we needed to infer the protected attributes of people who were ranked. And we also had query and location that were set in the query initially. Then all of that went into our fairness evaluation box, and we ran a number of our problem definitions, you know, the group fairness, the worker fairness, and the location fairness. On Google Job Search, things were architected slightly differently, as I said. TaskRabbit results were taken, and from the TaskRabbit queries, we generated search terms using Google Keyword Planner, and those search terms then were considered the ones that were going to be used to search for a job. And to do that, we went on Prolific Academic, that is another crowdsourcing platform that allows very fine targeting of individuals based on demographics, because we wanted to make sure that people who were hired for the jobs had the actual demographics that we were interested in. And so we asked them to install our Chrome extension, and that extension ran the queries automatically that we wanted, for which we obtained the results. Okay, so this is really how we architected the way we would enforce, in one case, from TaskRabbit, get the gender and ethnicity of individuals using crowdsourcing, and in the other case, enforce the gender and ethnicity of individuals who perform the search through the Google Chrome extension for Google Job Search. Okay. All right, so some results. This is a set of results on TaskRabbit, where by running our group fairness, job fairness, query fairness, and location fairness queries, we could observe a number of things. For instance, here you can see that regardless of whether we're using EMD or exposure, the way we've defined it, that results largely sort of agree, in fact, in the ranking. For group fairness, it's telling us that Asian females on TaskRabbit, regardless of jobs and locations, are the most discriminated against. Okay, white males are the least discriminated against. Okay, we could also look at particular jobs. Right, handyman is the most discriminating job, while running errands seems to be the least discriminating jobs, right? And you see there are slight differences between the EMD version and the exposure version here. And similarly, we did that for different cities, and you can see which cities are the most discriminatory. This is across the board for all ethnic groups and all gender groups, but one could also obviously do it for different groups. Similarly, the comparisons that I had told you about, we could see, for instance, that some cities inverted the overall sort of observation. For instance, here we can see that females are more discriminated against than males across all of the data that we had on TaskRabbit, but when we dive into specific cities, specific towns, we can see that it's not always the case. Okay, that's it. So this was for the part that was looking at formulating fairness and using that to run all sorts of queries. Let me just spend a few minutes on the question of repair, and I'll finish with some open questions. All right. So basically, the question of repairing discrimination has attracted quite a bit of attention lately, because initially it was the initial question was how to make the assessments and provide tools to observe basically the discrimination. Eventually, later to bring that to a court of law. But the question of repair was looked at later, and it was looked at from three perspectives. From the perspective of maybe the problem is in the data. Maybe the problem is in the initial data distribution. And I don't need to go into more details about this. I mean, Toon has spent quite a bit of time telling you about it. And I just wanted to give a reference here from the fairness of ranking perspective, one piece of work, I think it's one of the early pieces of work that examined how to characterize fairness, with respect to data distributions, and how to treat it as a data repair problem by intervening on the data, the input data. Maybe if I change the distribution of males and females, I will observe, I will do a better job, right, at the ranking. So that's for the first part. The second way of dealing with it, right, or of addressing this question of fairness in ranking is to basically study the ranking function, study the ranking algorithm. And there's one piece of work here that I like quite a bit. It's the second reference that basically looked at if my ranking function is a weighted linear combination of 2 dimensions, right, like the one I showed earlier, language test and approval rate. If I were to change the weight of those 2 dimensions, how would that affect my ranking? And then ultimately, what one would want to do is to design a fair ranking scheme, or at least the fairest, right, among all the possible ways of weighing the dimensions that matter for the ranking. So one observation is that on online labor markets, you don't have access to the input data, right? And you don't have access to the algorithm. So the only thing that remains for you is the outcome, right? The output, the ranking of individuals. And one could go about repairing the discrimination by adjusting individual workers, maybe the ratings, for instance, for TaskRabbit, since the ratings are provided as feedback from input, to compensate for the bias that is observed in the ranking. For instance, if we quantify that Asians receive systematically lower ratings than others, then we would adjust the ranking upwards according to the amount of rating, lower rating than they have received in the input. This is referred to as equality in outcome. So you act on the outcome of the ranking, as opposed to equality in treatment, where you're actually acting on the ranking logic or the ranking algorithm. And this could directly mitigate the effect of social biases, such as the ratings that people have received, the language in the reviews, right? Without necessarily changing the behavior of people, which is something much harder to do, right? To go and educate people and tell them you should write, you should not choose, more negative adjectives when it's a Black woman. But this could also be attacked, because it could be construed as unfair reverse discrimination. And there is a lot of debate around that, and affirmative action and so on. And to finish this, I just have another two minutes where I want to, again, take another step back and ask about what do workers actually want. And there was this study that was really exciting, and I liked it a lot. I highly recommend it, where basically people were polled, and workers on Amazon Mechanical Turk were polled and asked what was their motivation. Why did they go and complete the tasks? Okay, the purpose of the study was different. It was basically to revisit some of the motivation models that were developed in the 70s. About what motivates people in the workplace, and see if those motivation factors still hold on platforms that are online. And you can see here that while payment is basically a high motivation for people to go and complete tasks online, there is a number of other factors that are all the way at the top, right? Which are about, whether the job gives you feedback on your performance, right? Whether the job necessitates more than one of your skills to be completed. There is also what is referred to as human capital advancement. I mean, people replied saying, again, on a scale of 0 to 3, people replied saying that they went and completed tasks because they learned something, because they could signal, they could do social signaling, because they could talk to others, right? So there is more to human beings, right, than simply, reducing them to a number of factors and saying, this is how I'm going to be ranking jobs for them. Okay, so a number of open questions that I think, would be really interesting to address from a research perspective. So one aspect, as I said, that seems to matter to people is feedback, right? How am I performing compared to others? Okay, which by itself, of course, requires to quantify how well somebody is, how well are the contributions of an individual, and compare them to others. How am I growing compared to others? Right? What am I learning compared to others? Which would require to quantify workers' competencies and skills and compare it to others. And then how do we integrate workers' performance into the assignment of tasks to workers? Right? Which would require to observe workers as they complete those tasks and design adaptive algorithms, and really require to rethink the way we're assigning tasks to them to both integrate, what they're looking for, right, and what matters to them as a factor, for instance, how they're performing, but also, of course, some fairness in the ranking. And finally, closer to the topic of the talk, questions such as, providing sort of a temporal element, adding a temporal element. Do adverse working conditions for women and minorities cause them to drop out of the freelancing workforce at a greater rate than men? And what this would require to do is to conduct a longitudinal observation study of worker behavior over time, and observe beyond simply the question of, how are people ranked and what is their access to work. Really, what is the impact of these platforms and these rankings on individuals, on individual engagement on these platforms. So these were my last words, and this is just a reference to a piece of work that we did as part of a workshop, a Shonan workshop in Japan, where we talked about a dream future, a future of workplace where humans would be empowered by getting help from the machine, as opposed to just being to the service of the machine, labeling data for AI algorithms, where they could also enhance their capabilities through things like upskilling and receiving feedback from the system while feeling safe. And with that, I thank you for your attention, and I'm ready for your questions.
Thank you very much, Sihem, for the inspiring talk. There are a couple of questions in the chat, and to all the participants, if you have any question, please raise your hand. We have now the opportunity to ask directly Sihem.
Yeah, I can see some of them. I mean, you can obviously ask me, and I can answer.
Whatever you prefer.
Okay, so if anyone has questions, raise your hand, and I'm looking at you right now. And meanwhile, I'm just going to be answering questions the order in which they appeared. So Irini was asking about the fact that we're considering multiple attributes, and that's true. The initial pieces of work in fairness in online labor markets were only considering one attribute at a time. But what we're doing here is we're considering combinations of attributes, or what people refer to also as subgroup discovery, right, in the data mining community. No, we do not assume that attributes are binary. Our attributes could take any number of values, because the notion of a variant of a group is basically any other group whose value for a particular attribute is different. After observing fairness differences or speculations, is it possible to look deeper into the root causes of bias? Very good question. And how? Yeah. All right, two questions in one. So thank you, Irini. So we tried and we failed miserably. So we tried because the first thing we did is we simply looked at the data distributions, because one of the reasons is simply that, that your database will contain 20% females and 80% males, right? And even if there is very little difference in relevance, the fact that, the data distribution is the way it is, will exacerbate any small difference in relevance. We did see that. We saw that some of the results we got were sort of correlated, in fact, with data distributions, but others weren't, simply because we don't have access to the ranking logic. We don't know exactly what went into the ranking logic, and it's not just about data distributions. How could one remedy that? I think first, the idea of making the study of input data, ranking logic, output orthogonal, right, is a very good first step. For instance, the piece of work that looked at the problem as a repair problem simply said, let me isolate what in the data may be the cause for my ranking, right? And if I do it in a completely sort of naive way, I simply do interventions, right? I would intervene on my data and look at the result of my ranking if I don't have access to the ranking logic, right? And I can sift through all possible interventions, right? Or all possible worlds and say, you know, for instance, what is a world that yields the highest or lowest discrimination? Okay. Okay, so that's one element of answer. Did we look at differences over time? No, we did not. And I think the last point I raised about things that have to do with, you know, do these working conditions, you know, yield sort of, or sort of push certain minorities or certain groups out of the system over time is something that would be really, really interesting to look at. But no, we did not look, we only looked at like one snapshot of the data at one moment in time. Another question from Georgia. I wonder to what extent known database repair methods can be adapted to bias mitigations, or whether we need totally new methods in the spirit of database repair methods. Yeah, I wonder too. Yeah, new database methods. Sure. I mean, obviously, I think, you know, the right practice is to look at existing data repair questions first, obviously. I think it very much depends on what we want to do. Like, do we want to study what the impact of intervening on data is, right, on the result? Okay. And that is fine, you know, studying that, to study that, I think a lot of the work that's been done for database repair would be extremely useful. If we want to study both that and the behavior of the ranking itself, I think that would require going beyond the repair, the data repair methods, because the data repair methods, to the best of my knowledge, haven't been looked at in conjunction with the ranking logic.
Maybe, can I interrupt a bit? Maybe you can clarify what are the data repair methods? Are they similar to what we call pre-processing methods to fairness? So changing the data, this could be changing the labels, undersampling, oversampling, weighting, etc.
Yes. Okay. So the data repair method go maybe a little bit beyond that, because they would, for instance, you're assuming that something in your data is flawed. Okay. For instance, you know, like a typical example is you have the same record for the same person in call details data, for instance, a phone company. And I mentioned that because that's something that we looked at ages ago when I was at AT&T. And the same individual would have kind of the same or a similar address, right, in the two records, right? So this can be, you know, it can come from the fact that you've integrated data from different sources, or there was a mistake in entering the data and so on. And you have, in the database, in data management community, there are all sorts of methods to sort of try and repair such errors in the data. Okay. Mm-hmm. And yes, so thank you for insisting, because this makes me think of another thing. Like, if you're able to quantify how by how much you are discriminating against a certain group of people, right? Then that quantification can be considered as an error in the original data, and trace back, right? And using, you know, some provenance methods, tracing back where that came from. You know, except that this requires to incorporate a ranking logic in the system, right? And I think most of this work, or maybe even all of the work, did not take into consideration ranking. Mm-hmm. Was there any difference? Oh, more questions. Was there any difference observed between online tasks and in-person tasks? We did not look at that. Yeah, that would be interesting. I'm pretty sure there is something there. Okay, why the profiles with no photo were more discriminated against? Is there an explanation? No, actually, I think one of the results in that paper was that Black males were discriminated against more than people who didn't have pictures. Okay, and people who had pictures tended to get, I only showed you some of the results, but another result was that people who displayed their picture got more feedback than those who didn't. Voila. And then there is one other question. Do you believe dynamically changing the bias could help the system suggest more fair ranking? At a certain point in time, Black men receive more bad reviews, so the system could be biased in a positive way towards them at this moment. Or could this dynamic change in bias have a negative impact, such as introducing new, different type of bias in the system? For sure. I mean, again, I think the problem cannot be studied in isolation. Okay. I think it needs to be framed, right? Basically, it needs to say, if my goal, right, is to fix exposure, right, since we're talking about ranking, for some group of individuals, this is what I should be doing. And then this should be accompanied with, and this is how this hurts these other groups, okay? And also, I am a firm believer of fixing things in the outcome of the algorithm, right? Rather than doing disparate, basically equality in treatment. To me, I think we should just do equality in opportunities, really, right? But that's, again, once we start debating, and it's 2 minutes past the hour, but when we start debating, I think it becomes a question of, I don't want to say politics, but at least policy. Voilà.
Any other urgent question, pressing question before we close? I think you answered already many. Thank you very much, Sihem, for this very interesting talk and your time. So thank you very much.
Thank you, everybody. Good luck with the rest of the day and for tomorrow.
Thank you. And to everyone, we have now a lunch break. So enjoy your lunch, and we meet in 1 hour with another tutorial. So enjoy. Bye-bye.
Hello everyone, I am Dimitris Tesmelis from Greece, and I hold a bachelor's degree in Informatics and Telecommunications issued by National Kapodistrian University of Athens, and a master's degree in Big Data Management and Analytics, jointly issued by UPC, ULB, and Central Supelec. Currently, I am a PhD candidate at Athena Research Center, and I'm working around applying machine learning techniques within databases. With machine learning being closely coupled with AI, I'm looking forward to learn how fairness can be applied to such systems.
Hello, I'm Eliana Pastor. I'm a postdoc at Politecnico di Torino, Italy. My research interests are on explainable AI and responsible AI. In the last period, I've worked on posthoc techniques to analyze the behavior of machine learning models from the perspective of both single instances and a subgroup. The strict link between explainable AI and the assessment of fairness has strongly led me to an increased interest in fairness in AI. I think that the Greek ACM-W Winter School is a great opportunity for me to further increase my knowledge in the field of fairness in AI. I look forward to interacting with speakers and the other participants. Bye.
Hi everyone, I am Eli Papadopoulou. I am from Greece. My background is on library science and information systems, and I'm currently doing my master's degree on public policy and public management at the Athens University of Economics and Business at the Department of Management of Science and Technology. I'm also affiliated with Athena Research Innovation Center in Greece, where I work on national and European projects that deal with open science and research data management. Research data is my passion, and that's why I'm also interested in learning more about artificial intelligence and machine learning. Data is a basic component in machine learning pipelines. And my master's thesis tries to combine all this knowledge and all these different aspects of public reforms and research data and artificial intelligence to try and understand how they can be applied at the Greek research area and how everyone, all the stakeholders involved, can co-develop those frameworks at the legal, ethical and logistical levels. I'm looking forward to meeting all of you, and thank you very much for the opportunity to be around you, and talk to you soon. Bye, thanks.
Hi everyone, my name is Jan Bachmann. I am currently living and studying here in Vienna as a PhD candidate in network science. I am affiliated to the Networked Inequality Group at the Complexity Science Hub here in Vienna, but also to the Central European University, which is where I'm doing my degree. My main research focus right now revolves around studying the algorithmic fairness performance of graph neural networks based on their network structures. So I want to study varying network structures and how they affect, as an input, the graph neural networks, both in unsupervised tasks such as creating node embeddings, but also for supervised tasks such as node classification or link prediction. In case you want to contact me about anything, really, feel free to shoot me a message on one of these channels. Yeah, looking forward to be working with you. Bye.
Hi, my name is Karima Makhlouf. I am a PhD student in INRIA Leaks École Polytechnique. This is my first year. My supervisor is Katushia Palamedesi, and I am a member of the COMET team. So I work in general in ethical considerations in machine learning and in particular fairness. So we worked before on the problem of applicability of fairness notions in real life applications, and we work currently on causality and fairness in machine learning. Thank you, and see you in the winter school.
Hello everyone, my name is Kornelia Papanastasiou and I'm a PhD candidate at the Department of History and Philosophy of Science at the National and Kapodistrian University of Athens in Greece. My dissertation is entitled Contextualizing the Integration of AI and Big Data into Reproductive Technologies. So it examines the integration of AI into mainly assisted reproductive technologies from a humanities perspective. I research how social biases connected to social inequalities and gender identities are advanced through their embedding into the technological design of these technologies. I'm really happy to be part of this winter school, and I'm really looking forward to seeing you and meeting you guys in a couple of days. Until then, bye.
Hi, my name is Melina. I'm a first-year PhD student in computer science at Sorbonne University in Paris, France. My research work really focuses on how to evaluate fairness, which is challenging as it's a context-dependent notion. And in my case, I work with educational applications such as success prediction, clustering groups of students to adapt intervention, or personalizing course strategy according to a student's profile. I attend the school for several reasons. First, to further understand the relationships between biases and fairness. Second, to interact with researchers working on similar topics. And finally, to have a discussion on what we can do beyond biases. That is to say, how, as scientists, not to produce harmful impacts anyway. Thanks for listening and see you soon.
Hello, my name is Parastu. I have a master's degree in electrical engineering, major of control. I'm pleased to be here with you at First Greek Winter School to learn fairness in AI. I'm really passionate about AI field because I think it is really useful and efficient for solving problems of different sectors. I appreciate the Winter School organizers for providing the opportunity to learning this subject. Many thanks.
Hello, my name is Seamus Ryan and I am a third year PhD student at Trinity College Dublin, Ireland. I'm part of the Health Technology Design Research Group, which is a human-computer interaction research group that's focused on digital medicine. My particular field is bridging the gap between engineers, users, and human-computer interaction specialists to deliver fair or fairer digital mental health interventions. Before doing my PhD, I spent 7 years working at Microsoft as an engineering project manager, partially in the Dublin, Ireland office and partially in the Seattle, America office, which is possibly why my Irish accent is not as strong as some others that you might have heard of. I'm looking forward to talking to everybody over the next 2 days.
Hello everybody, I'm Sofia Fadidou. I'm a PhD candidate at the Aristotle University of Thessaloniki in Greece and an early stage researcher at the European Innovative Training Network called RAISE, Real-Time Analytics for the Internet of Sports. My scientific interests fall under the general umbrella of personal informatics. Specifically, I study human behavioral patterns for sustained user engagement. Currently, my ongoing projects revolve around the notions of fairness and bias in self-tracking systems. I'm studying the potential data and algorithmic biases that might or might not exist in self-tracking systems, and hence I'm very interested in this workshop. I'm looking forward to my participation. See you all.
Hello everyone, I am Dimitris Melis from Greece and I hold a bachelor's degree in Informatics and Telecommunications issued by National Kapodistrian University of Athens and a master's degree in Big Data Management and Analytics jointly issued by UPC, ULB and Central Supelec. Currently, I am a PhD candidate at Athena Research Center and I'm working around applying machine learning techniques within databases. With machine learning being closely coupled with AI, I'm looking forward to learn how fairness can be applied to such systems.
Hello, I'm Eliana Pastor. I'm a postdoc at Politecnico di Torino, Italy. My research interests are on explainable AI and responsible AI. In the last period, I've worked on posthoc techniques to analyze the behavior of machine learning models from the perspective of both single instances and a subgroup. The strict link between explainable AI and the assessment of fairness has strongly led me to an increased interest in fairness in AI. I think that the Greek ACM-W Winter School is a great opportunity for me to further increase my knowledge in the field of fairness in AI. I look forward to interacting with the speakers and the other participants. Bye.
Hi everyone, I am Eli Papadopoulou. I'm from Greece. My background is on library science and information systems, and I'm currently doing my master's degree on public policy and public management at the Athens University of Economics and Business at the Department of Management of Science and Technology. I'm also affiliated with Athena Research and Innovation Center in Greece, where I work on national and European projects that deal with open science and research data management. Research data is my passion, and that's why I'm also interested in learning more about artificial intelligence and machine learning. Data is a basic component in machine learning pipelines. And my master's thesis tries to combine all this knowledge and all these different aspects of public reforms and research data and artificial intelligence to try and understand how they can be applied at the Greek research area and how everyone, all the stakeholders involved, can co-develop those frameworks at the legal, ethical and logistical levels. I'm looking forward to meeting all of you, and thank you very much for the opportunity to be around you, and talk to you soon. Bye, thanks.
Hi everyone, my name is Jan Bachmann. I am currently living and studying here in Vienna as a PhD candidate in network science. I am affiliated to the Networked Inequality Group at the Complexity Science Hub here in Vienna, but also to the Central European University, which is where I'm doing my degree. My main research focus right now revolves around studying the algorithmic fairness performance of graph neural networks based on their network structures. So I want to study varying network structures and how they affect, as an input, the graph neural networks, both in unsupervised tasks such as creating node embeddings, but also for supervised tasks such as node classification or link prediction. In case you want to contact me about anything, really, feel free to shoot me a message on one of these channels. Yeah, looking forward to be working with you. Bye.
Hi, my name is Karima Makhlouf. I am a PhD student in INRIA Leaks École Polytechnique. This is my first year. My supervisor is Katushia Palamidesi, and I am a member of the COMET team. So I work in general in ethical considerations in machine learning and in particular fairness. So we worked before on the problem of applicability of fairness notions in real life applications. And we work currently on causality and fairness in machine learning. Thank you and see you in the winter school.
Hello everyone, my name is Cornelia Papanastasiou and I'm a PhD candidate at the Department of History and Philosophy of Science at the National Kapodistrian University of Athens in Greece. My dissertation is entitled Contextualizing the Integration of AI and Big Data into Reproductive Technologies. So it examines the integration of AI into mainly assisted reproductive technologies from a humanities perspective. I research how social biases connected to social inequalities and gender identities are advanced through their embedding into the technological design of these technologies. I'm really happy to be part of this winter school, and I'm really looking forward to seeing you and meeting you guys in a couple of days. Until then, bye.
Hi, my name is Melina. I'm a first-year PhD student in computer science at Sorbonne University in Paris, France. My research work really focuses on how to evaluate fairness, which is challenging as it's a context-dependent notion. And in my case, I work with educational applications such as success prediction, clustering groups of students to adapt intervention, or personalizing course strategy according to a student's profile. I attend the school for several reasons. First, to further understand the relationships between biases and fairness. Second, to interact with researchers working on similar topics. And finally, to have a discussion on what we can do beyond biases. That is to say, how, as scientists, not to produce harmful impacts. Anyway, thanks for listening and see you soon.
Hello, my name is Parastu. I have a master's degree in electrical engineering, major of control. I'm pleased to be here with you at First Greek Winter School to learn fairness in AI. I'm really passionate about AI field because I think it is really useful and efficient for solving problems of different sectors. I appreciate the winter school organizers for providing the opportunity to learning this subject. Many thanks.
Hello, my name is Seamus Ryan and I am a third year PhD student at Trinity College Dublin, Ireland. I'm part of the Health Technology Design Research Group, which is a human-computer interaction research group that's focused on digital medicine. My particular field is bridging the gap between engineers, users, and human-computer interaction specialists to deliver fair or fairer digital mental health interventions. Before doing my PhD, I spent 7 years working at Microsoft as an engineering project manager, partially in the Dublin, Ireland office and partially in the Seattle, America office, which is possibly why my Irish accent is not as strong as some others that you might have heard of. I'm looking forward to talking to everybody over the next 2 days.
Hello everybody, I'm Sofia Fadidou. I'm a PhD candidate at the Aristotle University of Thessaloniki in Greece and an early stage researcher at the European Innovative Training Network called RAISE, Real-Time Analytics for the Internet of Sports. My scientific interests fall under the general umbrella of personal informatics. Specifically, I study human behavioral patterns for sustained user engagement. Currently, my ongoing projects revolve around the notions of fairness and bias in self-tracking systems. I'm studying the potential data and algorithmic biases that might or might not exist in self-tracking systems, and hence I'm very interested in this workshop. I'm looking forward to my participation. See you all.
Hello everyone, welcome back from the lunch. I hope you had a nice break and you are now ready for more knowledge. So we continue with our agenda. So the next topic, the next item in the agenda is a tutorial on fairness in ranking and recommenders. So we already heard about ranking systems in the previous talk by ACM, so it's related to that sense. And this is a tutorial by Evangelia Pitoura, Kostas Stefanidis, and Georgia Koutrika. And hello to all the speakers, so thank you very much, and it's nice to have you here. And a short introduction to the speakers. So Evangelia Pitoura is a professor at the University of Ioannina in Greece. She leads there the Distributed Management of Data Lab, and she works in the area of data management systems, of course, with responsibility aspects taken into account. She has published in many important venues in the data management domain, for example, TKD, TODS, ETPT, SIGMOD, etc. And she's active also in the community through participation in conferences, etc. The second speaker is Georgia Koutrika. She's a research director at the Athena Research Center in Greece, and she works in the area of natural language data interfaces, data exploration, recommendations, and data analytics. And a lot of her work has actually been incorporated in commercial products. So she holds many patents and has a long experience working in different roles at HP Labs, IBM Almaden, and Stanford. And also she is very active in the research community, and she has published in very important venues in this area, for example, again, VLDB, TKD, SIGMOD, etc. The last speaker is Kostas Stefanidis. He's an associate professor at the University of Tampere in Finland, where he leads the group on recommender systems. And he has also a long experience in this area of recommender systems, personalization. So he works in the broader area of big data, and of course, responsibility aspects, focus on socio-technical aspects is part of his research. And he's also very active in the research community, so he participates in several conferences and workshops, and of course publish his work in top venues in this area. So thank you everyone for the tutorial. So we start with Georgia as the first speaker, and you can again, you can pose your questions to the speakers in the chat, or you can raise your hand, and the questions will be handled at the end of each sub part, right? So we have 3 speakers, 3 sub parts, and of course also at the end. So the floor is yours, Georgia.
Thank you, Irini, for the long introduction. You had to introduce 3 speakers, not just 1. So in this talk now, we are going to focus on fairness in rankings and recommender systems. So in particular, we are going to discuss a little bit more about why we care about algorithmic fairness. And then we are going to dive into 3 different categories of methods that help us deal with bias in the algorithms: pre-processing, in-processing, and post-processing. And at the end, we are going to discuss some of the many open challenges that we are dealing with in fairness in recommender and ranking systems. Now, why we care about algorithmic fairness? We have already heard a lot about this question, and I want to spend a few minutes talking a little bit more, giving us more examples, more context. So essentially, nowadays, we live in a world where systems are used to help us in making decisions in small and big things. For example, we want to go somewhere and eat. We may ask a system for restaurant recommendations. Or when we are watching, we want to watch a movie on Netflix, Netflix provides many different recommendations. The same for books, even for people that would be good candidates to date. But then we also have such systems that are used in more critical decisions. For example, we have systems that are used in education for school admissions, in law enforcement for helping with sentencing decisions, with bailing decisions, and so forth. With job recruitment, which of the many candidates should be considered and which candidates should not be considered. Then we have insurance examples, housing logs examples, pricing of goods and services, and Tune in the morning provided several examples of this sort. And now, of course, we understand that when we have an automated system helping us to make decisions or even making decisions for us, how much trust we should put in these systems. So this concern comes from the fact that several different studies have shown that data-driven methods can neither unintentionally encode the bias that already exists in our data, but also our algorithms can unintentionally introduce new types of biases in the output. So essentially, these are two things that we need to consider and take care of. And let us see some examples. For example, a study that was led by University of Southern California showed that when it comes to job advertisements that Facebook shows to their users, they managed to find a case where essentially the type of the job advertisement took unintentionally into consideration whether the candidate was a man or a woman. And in particular, one example of such case was advertisements for delivery drivers. The advertisements were intended for Domino Pizza drivers and for Instacart drivers. They were almost the same. They didn't identify any specific demographic, so they were correct in that sense. However, the underlying population where the algorithm was learning the recommendations was biased. In the case of Instacart, Instacart had more female drivers and Domino had more male drivers. So essentially, Facebook targeted the Instacart delivery jobs to women and the Domino delivery jobs to men. So this is an example here where essentially the algorithm is biased towards the data that it has in their input and targets an advertisement, take into consideration the gender of the person that this advertisement will be shown. Let's go to another example, streaming recommendations. So one of the many platforms that we have out there, Spotify. It produces, for example, every year, top 10 lists of most streamed artists. So the example here is for 2020, but every year we have similar lists. So if you take a look at the list, only 2 of the top names are actually female singers. So now consider that an algorithm takes into consideration this data essentially. It will inevitably generate recommendations that recommend more male singers. So essentially what the algorithm does here, it is that it amplifies existing bias and it even more contributes to reducing diversity in the recommendations that we see. So this is again one big concern. Now let's switch context. Facial recognition technologies. These are very popular in US in law enforcement, and they are actually being used for over a decade. And but unfortunately, there have been many cases where these tools recognize, misidentify people. For example, here, a well-known case of this guy, Oliver, that was misidentified as the perpetrator in one case. As you can see from the 2 photos here, Oliver has nothing to do with this guy. They're totally different people. They don't have any resemblance. However, the algorithm thought that they were the same person. Why this is happening? Well, it happens because the algorithm that was used for the facial recognition technology actually is trained based on images that mostly show white faces. And the result, of course, is that this technology works relatively well when it comes to recognizing white people, white faces, but then it is less accurate, less reliable when it comes to recognizing people of different demographics. So again, and there is also a big, a further story behind that, that they say that, white people train the algorithm with data of white people, and so forth. In any case, the lack of diversity in the training data generates wrong results, and in this particular case, it is a serious example. Now, earlier Toon also mentioned this word-to-vec embedding. Word embeddings that are trained in this particular case using the Google News set. And essentially the embeddings actually reproduced biases that exist in the data. For example, we see here that some extreme female occupations were homemaker, nanny, and nurse. But when it comes to male occupations, we have more fancy occupations like maestro, philosopher, captain, and so forth. Now, one may say that, well, the algorithm learns exactly what we have in the data. The learned associations reflect patterns in the Google News corpus. Yes, this is true, but the problem is that in the same way that you don't want a biased person to make biased decisions, you don't want also your automated system to be biased in the same manner. Now, essentially, fairness means lack of discrimination in very broad terms. This is not a formal definition by far. But where this bias come from? So as we said in the previous example, there are two main sources of bias. Bias that comes from the actual data. For example, because we use the survey to collect the data, but this survey unintentionally or intentionally contained biased questions. Because some specific population is either misrepresented or underrepresented in the input data. Because as we said earlier, the data contains bias because of some historical process that operates on the disadvantage of a certain group. So the data is one part of the problem. Then the algorithm per se may be another part of the problem because it may reflect, for example, commercial or other types of preferences of its designer. For example, the designers may prefer to give specific pricing to a particular group and different pricing to all the other types of groups. Then the processing of the data that happens within the algorithm may be a source of technical bias. For example, we may join different data, or we may filter out some data, and that can create bias because, for example, one of our populations may be now underrepresented. And then, of course, the problem of the feedback loop. We give biased data in the algorithm generates more biased data, and that goes back. So this creates a loop. And there are already many different efforts to deal with bias, to understand fairness, to find new algorithms. And we see dedicated conferences. We see many different initiatives from Google, from Microsoft, and so forth, and a lot of different open source toolkits that provide methods like the ones, or exactly the ones that we are going to see in a while, that mitigate bias. Now, the whole area here is actually very challenging because, to start with, even the concept of fairness is something that we don't understand very well. Fairness in one domain may be different from fairness in another domain, or it may evolve through time and so forth. Then we need to understand what are the different causes that may introduce unfairness in machine learning. And different algorithms may behave differently. So it's not that we can find one remedy for all different algorithms. And then what are the possible different ways that we can modify our algorithms to avoid bias or unfairness? And you have to consider that there are trade-offs in this effort, because on one hand, you have the algorithm that tries to achieve, for example, to provide accurate recommendations. On the other hand, you want these recommendations to be fair, And these objectives may be in conflict with each other. So let's now move on to discuss about particular methods that help us deal with bias. And essentially, we can operate at 3 different levels. First of all, pre-processing methods that operate at the level of the input data. So we transform the data in order to make things better, to remove or reduce bias. Then the second level that we can do something is the in-processing methods, where essentially either we modify our algorithms so that to remove or to reduce cases that these algorithms may generate biased results, or we see new algorithms that were designed from scratch and with the objective of producing fair outputs. And then, of course, we have post-processing methods that do not care about what is the ranking or the recommendation algorithm that you have. They treat this as a black box, and they try to modify the output they see to ensure that this output exhibits some level of fairness. So let us start with pre-processing methods, and there are many different types, and we're going to discuss today a few representative examples. So assume that you have a protected attribute, for example, race or gender, and you want to make sure that the classifier that you trained on your training data does not depend or does not reveal the race or the gender of a particular person. So, for example, if you give recommendations for loans, you don't want the race or the gender to bias the classifier. So, an easy decision for this is to say, okay, I will completely omit this protected attribute, so the classifier will not see that at all, and it will be trained on the remaining attributes. So this is simple, but then it is risky because the classifier may still learn this discrimination, this bias, because attributes may be correlated. For example, race may be correlated with the address of the person. So this method can work only in very simple cases where correlated attributes are not correlated with a protected attribute. Now, a different method now is called class relabeling. So what we do here is that essentially we go to the data set, and in order to remove the discrimination, we selectively change the labels of some objects. So to do this, one method is the following. We train a classifier on the data that we have. Let's assume that we have employees that the classifier will classify as good for a promotion or not. And we are going to rank these employees based on the probability of having a positive label. For example, to be promoted in our example here. Now we're going to select the top K of the minority group. So the top K of, for example, females that would not be promoted. So the gender here is the protected attribute. And that is happening based on the probability of getting a negative label. And we call these the promotion candidates, the candidates that will be promoted. And then we select the bottom K of the majority group. Let's say these are the male employees that will be promoted based on the classifier. So we rank them based on the probability to get a positive label. We take the bottom K, and these are the demotion candidates. And then for the promotion candidates and the demotion candidates, we flip their labels. So by doing this, essentially, we modify, so notice that we modify the actual labels of our training data. So this is quite intrusive. And we achieve to lower the discrimination, but at the same time, we lower the accuracy of the classifier, because now the classifier is trained on some, let's call it fake data that was not actually observed because we changed the actual labels. And let's see an example of how this method works in practice. So we have here employees, okay? There are male employees and female employees. we have here the class, and the class is plus, which means these are classified as candidates to be promoted, and minus, which means these are classified as candidates to be demoted. Okay. Now, based on this classifier, we rank all these employees based on the probability to be promoted. So as you can see here, bias is already evident because all males get high probabilities to be promoted, okay? But females get, in general, very low probabilities to get promoted. And this is something that we want to change. So we take these probabilities into consideration, and we rank we order essentially our employees based on these probabilities. And now here we have the females based on the probability in decreasing order to be not to be promoted, and then we have the females based on increasing probability to be promoted. Okay, so the idea now is very simple. We take from the males the guy that had the lowest probability to be promoted. So this is the guy here. From the other group, from the females, we take the person with the largest probability that it will not take a good promotion, and we flip their their labels. By doing this, and we have to, of course, to decide how many labels we're going to flip, we manage to balance our data set. Again, this is very intrusive. It creates problems in the accuracy of the algorithm, and generally, in very rare cases, it is preferred. Now, having talked about the shortcomings of the previous method, reweighting essentially was proposed as a less intrusive method because we are not going to touch the data at all. What we're going to do here is we're going to give weights for every object, for every employee. Since we're discussing about employees as a running example here. And this weight essentially determines the contribution of this employee, of this observation, to the algorithm that will decide the final classification. Essentially, this method works with this reweighting method works with algorithms that are based on frequency counts, for example, probabilities. So let's see a particular example, a probability-based reweighting method. Let us consider that our sensitive attribute, for example, is gender, okay? Then for each employee, for each object, we compute the probability that this object would belong to a particular class, promoted or not promoted in our example, if independence would hold, okay? So this is the expected probability. And then the weight that we give to this object is essentially the expected probability divided by the observed probability. Let's see an example to make things a little bit more concrete. Again, we have the same employee set here, males and females that will be that have been promoted or not. Okay, so this is our training data. And now, if our data set was unbiased, okay, then whatever we see in the class attribute would not depend on the gender. So, for example, the expected probability for females to be promoted, if these two attributes were independent, would be essentially the product of two probabilities. The probability that you are a female employee, which is 0.5, and the probability of the positive class, which is 0.6. So the expected probability for females to be promoted will be 0.3. Now, if we look, however, at our training data here, they show us a totally different story. Essentially, the observed probability for females to be promoted is 2 out of 10, so 0.2. So what we do here is that we use this as a weight. We take the expected probability divided by the observed probability, and this, in our particular example, gives a weight equal to 1.5. And this weight essentially will boost the contribution of females in the algorithm as if the females were more. Essentially, we do this for all other combinations. For example, if the gender is male and the class is positive, okay, this weight would be given, which means that since more male employees are promoted in our training data, we want to reduce this contribution, the importance of this factor in the training data. Now, the only disadvantage of this method, or the only important disadvantage of this method, is that it only works with certain classifiers that work with probabilities, that work with frequencies. So it cannot work with any type of classifier. Now, going back to methods of pre-processing data that are again more intrusive, we see data transformation methods, where essentially we try to take our training data and of course our test data as well, and map it to a new space using a randomized mapping that of course satisfies certain criteria. And these criteria are the following. We want for sure the first one to control bias, to control discrimination. But in order to do this, we also need to take into account that we don't want to cause distortion of the individual variables. And we also want to make sure that we reserve data utility. Essentially, the discrimination control means that we want to limit the dependence of the output of the algorithm on the protected attribute, on gender, for example. And data utility means that the new distribution of our data should be statistically close to the original distribution. Otherwise, the algorithm will learn something that is not exactly, that's not similar to the initial training data. This one actually works with different classifiers, okay? But it comes also with some shortcomings. It works only with numerical data, since we're talking about transformations, and it also modifies the data. So overall, we haven't seen a method that works for everything or doesn't come or comes for free if you like. Database repair, we also heard about it during Sichem's talk. Essentially, the idea here is that we want to change the data based on methods that repair, that see the problem as a database repair. We want to repair the data, for example, missing data. And again, to minimize the dependence of the output on the protected attribute, but also allow the algorithms to work well and do not hurt the accuracy of the algorithms. So one of these methods is the disparate impact remover, where essentially disparate impact is a metric to evaluate fairness. It compares the proportion of the individuals that get a positive label for two groups. The unprivileged group, for example, in our employee example, these are female employees, and the privileged group, which again in our example are male employees. Now, a last method that I would like to discuss for pre-processing is called data augmentation. And a particular example of data augmentation has been actually proposed in the context of a specific recommendation algorithm, which is matrix factorization. So the idea here is the following. In matrix factorization, you have a matrix of ratings between users and items, for example, users and movies on Netflix. And then matrix factorization generates two tables that are used. So in these tables, you can view them as the user table and an item table, which are described, however, using latent factors. And based on these two, we can then make predictions for missing ratings. So we can make a prediction for a movie that a certain user has not seen at all. Now, the idea of augmentation is that, okay, we do not touch this. We do not go and modify values that are inside here as other methods do, but we are going to add a few more users, and these users will rate some items. Of course, these are synthetic data. They're not real users. But the way that we generate this matrix here is so that if this is taken into consideration with this one here, the result here will be the new user ratings will improve a socially relevant property, will essentially improve the fairness in the result that the users see in the output of this algorithm. Putting all this together, we can take into consideration 3 dimensions: the algorithm, the fairness, whether it is individual fairness, each individual, John, Mary, do they see a fair treatment, or group fairness, all female employees versus all male employees, and also where bias comes in the data. And we see here two different cases. When bias is actually seen in the rows, for example, we may not have enough representatives for a particular minority group, or bias in the column when the features are correlated essentially with sensitive attributes. So if we take this into account and we put them all together, we make the following observations. The first one is that most of the methods that we have seen operate on bias in columns. Data augmentation, database repair are one prominent examples of methods that operate on rows. All of the methods operate for group fairness. Group fairness is actually simpler to achieve and simple to check. And most of these algorithms work with, of course, the exception of suppression that is algorithm agnostic, work for classifiers, rankings in particular. And we see only one example that is particularly proposed for recommendations. The overall message here is, of course, that there are a lot of different machine learning algorithms, and there is a lot of work ahead of us in order to understand how the algorithms, how the concepts of fairness that we want to achieve are combined and what we need to do. So with this, we conclude the part that the first part of this tutorial that talks about pre-processing. If there are any questions, we can discuss them now, or later at the end of the talk. Okay, Abby, go ahead.
There is one question actually by Sophia.
Sophia, yes, please go ahead.
Yeah, thank you for your very interesting talk. I was wondering, could you please repeat a little bit the difference between bias in rows and bias in columns? Does this have something to do also with a differentiation of whether we have bias in the labels in the data set versus bias in the features that you've mentioned?
That is correct. So an example of bias in the rows is the example that we saw at the beginning, that we discussed at the beginning about the Facebook advertisement. The data that Facebook had for the example of Instacart and Domino was data that exhibited bias in the rows, because in the case of Domino's, all rows were mostly about male, so we didn't have enough examples for female drivers. In the case of Instacart, the males were actually the underrepresented population, so we had this problem. Then an example of bias in columns is when, for example, the employee example that we used actually for our discussion, where the probability that someone would be promoted essentially was connected to the gender. And in this particular example, we could see that we didn't have any bias in terms of rows because we had an equal population of women and men, but the labels were biased because, of course, in that case of historical bias.
Thank you very much.
And more questions in the chat, Georgia. Maybe you want to go through them, or should I read them?
I think it would be best for interaction that people actually like Sophia speak up.
So Vasilis, do you want to speak? Okay.
Can you hear me? Yes.
Yep.
Yes. So my question is, having followed your distinction between bias introduced in the data and bias introduced in the model as two big categories, my question is, if we spot that there is bias in the end of the procedure, so we have some data, we have a model trained on them, and after the whole pipeline executes, we find that we have some bias in the outputs of the model. How can we know whether the bias was introduced in the data itself, or the data was clear from bias and then the model came and introduced them? Or in other words, if we apply data processing, pre-processing technique in order to reduce or to exclude the bias in the data, can we be sure that afterwards the whole pipeline will be okay and without bias, since the model that comes afterwards may add it?
Excellent question. Thank you, Vasily. First of all, what you're asking is a difficult problem. So generally, it is hard to make sure that everything works perfectly and we don't have any bias either in the data or in the algorithm, which is even more difficult. Now, there is a family of algorithms that are not pre-processing or in-processing or post-processing. There are algorithms particularly working on to understand where bias comes from and trying different data to see how the algorithm, for example, handles different data. So if I change something in the input, does the algorithm generate the expected result or not? And there are many different methods. It is a difficult problem. And there is also another line of algorithms in this direction that allows the programmer to write assertions inside the code, like assertions that normal assertions that we have when programming, that say, for example, when X becomes greater than 0, stop or do something. So write assertions that check whether at a specific points the algorithm generates expected outputs in terms of, again, of bias. So for example, you could see assertions like, if the female employees are larger than, the sample that I have is larger than 20%, then I expect to have a result over 5% in the input, in the output, something like that. So again, this would be a method for the algorithm to check if it operates correctly or not. And again, these algorithms have nothing to do with in-processing or post-processing. They're a whole different family of algorithms.
Okay, thanks. And a small follow-up. So in general, this whole procedure of debiasing, we can see it as a particularly model-specific procedure. We cannot have a generic framework that solves our problem. So we have to see specific data on the one hand, on the other hand, specific model and debiasing in a model-specific way in both axes, right?
And there's also one more dimension that actually Toon in his talk mentioned more than once. It is the definition of fairness that you're trying to achieve. And there are different definitions and there are different metrics. Which one you choose is also a dimension of this problem and makes it even harder, actually.
Thanks a lot.
Hi, I have another question First of all, thanks for the presentation. I think it gave us a very good overview of all the methods that are used. I would like to ask in specific for data augmentation. You mentioned that we generate antidote users. Can you name an algorithm that's actually used in practice on how to do that?
Matrix factorization in particular. This particular method was proposed in the context of matrix factorization algorithms that are used for recommendations. These algorithms are one of the basic families for recommendations. They are using a matrix that represents ratings. So for example, users that rated movies, and they inject in this matrix additional synthetic users, essentially trying to make the matrix more balanced. For example, let's say that the problem that we initially had in our data was that we had more ratings from male watchers and much fewer ratings from female watchers. Then the added-on data would essentially try to create a balance between the underrepresented population and the overrepresented, if you like, population. So that would be one objective.
And do we have similar algorithms that can be applied in other domains other than recommendation systems?
Unfortunately, so far we haven't seen one, at least to the best of our knowledge. Most of the algorithms are targeting classifiers. There are a couple of algorithms that target matrix factorization. So the one that I showed here with the antidote data is one example. There are a few more. And we haven't even gone to deep learning recommendation methods, where it's rather an unknown territory for now. We haven't even gone there.
So lots of space for future work.
Absolutely.
Great, thank you.
You're doing your PhD. You are in a good place.
And Georgia, can we handle a last question by Katerina for this part, and then if there are more questions, we can take them at the end of the tutorial if there is time.
So the question is there a limit to how many limitations are actually helpful and harmful to the system? Limitations in, I guess, in how we try to achieve fairness. That's how I understand the question. Katerina, please correct me if I got it wrong.
Yes, and how you balance the data set. You try to have a unanimous, not unanimous, you try to have as many rankings from women as from men. When is this ratings, I'm sorry. When is this, all these limitations that you pose and you try to synthetically add users? When does this stop being so representative? So
first of all, it depends on the method. For example, one of the simplest methods that we discussed so far, and in the other parts of this tutorial, we are going to see more methods. But for the pre-processing part, some of the methods essentially do not even go there. For example, suppression is completely agnostic. It will drop the sensitive attribute without taking into consideration what happens. Okay. Then there are other methods, for example, the data transformation methods that try to take into consideration a few objectives at the same time. So the fact that we want to reduce bias, but also, for example, they try to make sure that the accuracy of the algorithm essentially is not hurt. In order to do this, they try to keep the distribution of the transformed data similar to the distribution of the initial data. So it depends on the method, what we if it takes an action or not. That is one. And then the second, of course, is that there are many things that may be need to many different objectives. Okay, that we may need to take into consideration. Algorithms that do take into consideration such objectives, they limit them in certain aspects. So we cannot control everything right now. Data transformation takes, for example, into consideration 3 objectives, which makes already the optimization problem very hard.
Super. Thank you very much, Georgia. Let's move to the second part. So Evangelia will follow. And again, at the end of this part, you can pose your questions and more questions if time permits at the end of the tutorial.
Okay, so hello everyone. For some reason I cannot open my camera, but that's okay, I guess. So in the first part of this tutorial, Georgia presented a couple of examples motivating the need for fairness in recommenders and ranking, and also presented methods for pre-processing, ways for removing bias in the data. In the second part of this tutorial, we will discuss in-processing methods. These methods change the design of the ranking of the recommendation algorithm. Before going into details about the in-processing approaches, I will talk a little bit about definitions of ranking, definition of fairness that are particular to ranking and recommenders. So Toon this morning did an excellent job in describing in depth various definitions of fairness for classification, where we are given some input and the output is a class label. For example, we have an individual and the output is whether the individual will get a loan or get a job. But in many applications, many algorithms, the output is a ranking. ACM give us an excellent example of an output producing a ranking, online markets, where the output is a rank list of workers ranked by some score describing their relevance for the specific job. As another example, consider web search. Here you enter a query and the output is a rank list of documents. Describing a rank list of documents ranked by their relevance to your query. So we will consider rank lists where items are ordered in descending order of some score, where the score is a measure of their relevance. Okay, so once again, the general view of fairness, we have individual-based fairness, where we look at individual items and we ask that the algorithm is fair to these individuals, to its item. And basically we ask that similar items are treated similarly. And then we have group-based fairness. We partition items into groups and we ask that the group as a whole is treated similarly. In this talk, I will consider two groups, the blue and the red group, and the red group is the protected one. As Sihan mentioned this, it's a very important factor in ranking. This is position bias. If you think about it, when we are presented with a list, we read it top down, right? We start from the top item and we go down to the list. So most often we only tend to see only a few top results, and the higher is the list you are in the list, the better. So in a nutshell, fairness in ranking asks, when it comes to individuals, it asks that items with similar relevance score should receive similar visibility, should be placed in similarly good positions in the ranking, and group fairness for ranking asks that groups should receive similar, as a whole, should receive similar visibility. So in the next few slides, I will present some concrete definitions of what visibility means, right? And how you express fairness in the case of rankings. Okay, the first and the simplest way is to use constraints. Given a protected attribute, we can specify an upper bound and a lower bound on the number of items with a specific attribute value that can appear in the top k positions. For example, for the ranking you see on the right, where I have marked with blue the unprotected, the items belonging to the unprotected group, and with red the items belonging to the protected group, we can specify an upper bound on asking that at most 3 blue items are in the top 5 positions, and the lower bound requiring at least 1 red item in the top 5 positions. Some other measures are based on discounted cumulative gain. Most probably you are familiar with DCG. It's a very common way for evaluating the quality of a ranking. And what you do is you accumulate the scores of the items, discounted by the logarithm of their position. So if you want to calculate the DCG at position 5, we sum up the scores of the items starting from position 1. So we have the score of the first item, the score of the second item discounted by the logarithm of its position, and so on. So based on this idea, we have a family of measures for fairness in ranking. One way to use DCG is to accumulate the number of items belonging to the protected class at discrete positions, right? So for example, we choose position 5 and position 10, and we count the red items. With regards to their ratio in the overall population, and we do that the same for position 10, and we discount this number by the logarithm of the position. Okay. And this gives us a measure of fairness, a measure of how many red items are in good positions, right? And there are many other definitions based on this on DCG. For example, instead of simply counting items at discrete positions, we can take membership probability distribution of the protected group at discrete top positions and in the overall population. However, all these counting measurements do not capture the fact that small differences in relevant scores may translate into large differences in visibility or exposure. Because of position bias. For example, think of items that have the same relevant score. You cannot place them all in the same position, right? So this is captured by what we call exposure. And Shihem this morning mentioned exposure. So I will give you a more specific definition of exposure, the definition of exposure in this talk. So assume we have a position discount vector that captions the position bias. So the value of the vector at position j represents the importance of position j. For example, the fraction of users that examine an item at position j. So the value 0.08 here means that the value, the importance of position j is this number. And this works for probabilistic ranking. So where for each item I, we have the probability of I belonging to position j, ranked at position j, and this can be expressed using a probabilistic ranking matrix, doubly stochastic matrix, where the rows are the items, the columns are the positions, and Pij is the probability that item I is ranked at position j. Given the position discount vector and the probability ranking matrix, we can calculate the exposure, estimate the exposure of an item by summing up all the possible positions that I can have. So the probability of I appearing at position J times the importance of position J. And similarly, we can have the group exposure by taking the average of the exposure of the item belonging to the group. Okay. So this is the definition of exposure that captures the skewness of importance in ranking positions. And based on that, we have a variety of measures of fairness. The first one is demographic parity. You have seen it many times today. We ask that both groups have the same average exposure. But as Toon said, demographic parity does not take into account the relevance of the item. So we can take that into account and ask that the exposure for the two groups is proportional to their average utility, to their average relevance. And another measure does not only look at exposure, but looks at the actual click-through rate, that is, and asks that the click-through rate is how many users basically click at an item, and ask that the click-through rate for the two groups is proportional to their average utility. Okay, and then we have then a similar idea of exposure, but for individual items. It's called equity of attention. And here we ask that each item receives attention or exposure that is proportional to its relevance. However, it's very difficult to satisfy equity of attention in a single ranking, because say that two items have exactly the same relevance, it's not possible to put them in exactly the same position. So what we ask is that we have fairness in a sequence of ranking. So say that we have many search results. You ask that the item is treated fairly in the sequence of these search results. We ask that the cumulative attention that an item receives is proportional to its cumulative relevance. Okay, so we have seen a couple of definitions of fairness in the context of ranking. And there are many definitions, many different definitions for fairness from recommenders. I won't talk in detail about them. Of course, you all know what is a recommend system is. You have all of you received recommendations, say for movies, and these recommendations are computing using the various information about the users, the items, and the history of their interactions. So they estimate a score for each user and item that reflects the preference of the user for the items. And then a recommendation list is formed that includes the items that have the highest estimated score. So one way to, one thing that I want to point out about recommendations and ranking in general is that as opposed to classification, we have multiple sides, at least two sides. So in recommendations, we have the items that are being recommended and the users that receive these recommendations. So we can have producer side fairness that focuses on the items, and we want our algorithms to be fair to the items that are being recommended. For example, similar items or similar groups of items should have the same probability of being recommended. And we have consumer side fairness that looks at the users that receive the recommendations. And we ask that our algorithm is fair towards the users. For example, both men and women should receive equally high paid jobs, right? So in recommendation systems, we have at least two sides. Now, as I said, there are many different ways to define producer side and item side recommendations, item side fairness. A simple way is to consider the recommendation problem as a classification problem, where the positive class is the recommendation list. So the output is for an item is the item is recommended or it's not recommended. In this case, you can apply the definitions of fairness that you learned this morning. Or you can consider the recommendation list as a rank list, and you can use the definitions that I have just described. And then there are many other models based on the consumer side fairness, like accuracy, calibration. I think Kostas will talk a little bit about this in the third part of this tutorial. Okay, and before finishing up describing the models, I want to stress out that this is a very broad area. There are many different models depending on the application, and algorithm and the problem. And I do have some biased examples. They are examples of our own work. So another problem in terms of recommendation is a particular form of recommendation where you want to recommend not a single item, but a package of items to a group of people. In this case, we can have different definitions and different types of fairness. For example, fairness proportionality. You need to have you ask to have in your recommendation list at least a minimum number of items that each user in the group likes. And you can have also what we call envy freeness, that you ask that the user believes that the algorithm is fair to him, and he does not feel envious in the sense that others are treated better than the user. Another important problem so far in this school, we have been talking about relational data, right? But there are also networks. So think of social networks, Twitter, right? So in Twitter, you have different groups, say you have men and women. And as you all know, not all nodes are equal, right? Think of influencers. So another form of fairness that is particular to network data is in terms of the position that the nodes hold in the data. So hold in the network. So you want to have networks where both men and women held equally important positions. And we have been looking at that where importance is measured by PageRank. Okay, so with that, I wanted to stress how wide the topic is. And we are only starting to define fairness. Now I will talk a little bit about in-processing techniques. Okay, so going back to the figure that Yuli has shown, we have three types of techniques roughly. Techniques that look into the input data, pre-processing techniques, techniques that look at the algorithms, in-processing techniques, and techniques that look at the post-processing techniques. In processing, we want to modify existing or introduce new ranking and recommendation algorithms on models that produce fair outputs on an input. This kind of algorithms are often called fairness aware or fair by design. And since this in processing, the approaches change the algorithm, they greatly depend on the ranking and the recommendation algorithm, and also on the fair or how we define fairness. So there is a lot of work on the topic, and I will present three different general techniques, starting from adding regularization terms. So when the ranking on the recommendation problem is expressed as an optimization problem, a very common way to achieve fairness is by adding a fairness constraint to the objective function. This depends the particular implementation of this general method depends on the recommendation ranking algorithm and on the fairness definition and the way we formulate this constraint. And I will show you two examples. One example is from ranking and one example is from recommendations. The delta-R algorithm that use the ranking algorithm is the list-based one, and the fairness definition is fairness of exposure. and the beyond parity recommender, where the algorithm is multi-factorization recommender, and the fairness definition is based on error. Okay, so let's talk about the first one. In learning to rank approaches, obtain a ranking function that is learned by solving a minimization problem with respect to a loss function. Most often, the loss function is a measure of accuracy with respect to the training data. And we can roughly distinguish between three approaches: a point-wise approach, where the training data are item score pairs, and we can see learning in this case as a regression problem. Given an item and a query, we want to predict the score. We have pairwise approaches, where with training data are pairs of items, where the first item is more relevant than the second one, and we can see that, consider that as a binary classification problem. Given two items, decide whether the first one is better than the second, and the list-wise approach, where the training data is a list of items ordered by their relevance to the query. And the approach I'm going to describe is based on a list-wise model. So delta R extends ListNet. ListNet is a list-based learning to rank model, where you are given a query and a list of documents with their scores, which express their elements to query, and the goal is to learn a ranking function to predict R hat, the scores, R hat scores, the predict score, that minimize the loss function, which is basically the difference of the predicted from the actual scores. Technically, in this approach, they only look at the top one probability, but for the moment, let's assume that this is, we're given a loss function in this form. Okay, so the delta R approach adds a factor, an additional factor in this loss function. So we have a factor for accuracy, and we have an additional factor that express fairness requirement. And lambda is a hyperparameter that specifies the desired trade-off between accuracy and fairness. Now, how can we express this fairness? In the delta R approach, they use fairness of exposure, and they basically a form of democratic parity, where we want the exposure for the protected group to be similar with the exposure of the non-protected group. And they use a square hinge loss function. They want to maximize this difference. Notice that when the exposure of the protected group is similar, is at least as much as the exposure of the non-protected group, then you optimize for accuracy. You optimize for fairness when the exposure of the protected group is smaller than the exposure of the non-protected group. Now, going back to recommenders, the approach, the beyond parity approach, use a max factorization recommender, where you learn a low dimensional representation for the users and low representation for the items, and your predicted score uses these low dimensional representations. Again, we have a loss function that considers the predicted and the actual scores. And we want to minimize the loss in accuracy and some form of fairness. In this work, their definition of fairness is an error-based one, like the one you heard this morning. So in particular, they want to minimize the errors in the predictions received by the users in the protected group and the errors in the prediction received by the users in the non-protected group. Okay. Now, the other method is based on learning fair representations. And the idea here is to introduce an intermediate level between the input and the output. So you learn an intermediate representation that encodes the input and also hides any information about membership in the protected group. Formally, Z is a multinomial random variable of size k, where each of these values represent a prototype. So its input is mapped to a prototype. It's similar to some of the in-processing techniques we have seen, but it's learned concurrently with it's part of the model. Okay, so in this case, we have a loss function that considers the quality of the encoding. We want the distance from point X to be as close as to the representation in Z. We have also a factor about accuracy. The prediction based on the representation should be accurate, and we have a constraint regarding fairness. In this particular study, fairness is statistical parity. The probability that the random element from the protected groups, that the random element for the protected group is mapped to prototype K is equal to the probability that the random member from the non-protected group is mapped to prototype K. And then we can extend this method that has been proposed for simplification by changing basically the loss function and using one that is particular to ranking. Okay, and there are some methods based on adversarial learning that I won't have time to discuss. Okay, and my last slide is just to show you the breadth of and the different ways that have been used. So for in-processing techniques, Sihem talked about this in his talk also. So so far I talk about approaches that are based on scoring functions that are learned, right? In some cases, we have linear scoring functions. For example, say that we have the case of college admission, and the score depends on, it's a linear combination of the GPA and the SAT score. So basically, the scoring function is a set of weights. Okay. So the problem in this case is formulated as follows. Given a function with a scoring function, linear scoring function with specific weights, find a function that is specify the weights of a function that is fair, but also the similarity between the weights is maximized. Okay. The smallest change in the weights so that you get a fair function. Okay, so this concludes my talk. We have seen approaches. We have seen three different approaches. One is to extend the objective function with fairness constraint. The other one is to introduce fair representations that hide the protected attributes. And then last one is we have shown an example of a linear scoring function where the problem is specified in a quite different way. Thank you.
Wonderful, Levi. Thank you very much. There is one question by Siddharth. Maybe Siddharth, you want to ask directly your question, and another question was handled already by Kostas. So I think this is covered.
Yeah, sure.
Okay.
Yeah, really nice talk. I just wanted to know whether the way the results are displayed also has an impact on the position bias or the exposure bias. For example, if a row has multiple results, then the second row itself will, let's say, have some nth result instead of the second result, but it should be catching the eye of the user more often than something which is on the last column of the first row.
Yes, this, if I understand correctly, you refer to what is called position bias, right? So yeah. It's very important to have results at the top of the list. Okay, so all these measures are trying to capture this, that the results that the position that an item appears is very important. It's very important, and that's why we have these different measures of exposure, DCG. So you don't only need to have your the items appearing in the rank list, but you also care about the position that these results appear in the list.
Okay, thanks a lot.
Thank you.
Great, thank you. Thank you, everyone. And Evie, since we are a bit short in time, what do you think if we Okay, there is another question in the chat. Maybe you can take this also by Eliana. Eliana, do you want to ask directly? And then to Kostas.
Yes, thank you for your time. Okay, thank you for the talk. I have this question. How can we handle scenarios when we have multiple protected groups? So we just not want to focus on one specific protected group, like refer to the attribute gender, but we have many that we want to take care. Can we directly apply this approach, or we need further steps?
Most of the research so far considers single protected attributes. So I guess some of them can be extended for multiple attributes, some of them cannot. So a short answer is it depends on the algorithm, right? So it's a very interesting problem, and there is a lot of current research on addressing multiple groups.
Okay, thank you.
Wonderful. Costa, the floor is yours.
I think you can hear me now. Hello, everybody. My name is Kostas Stefanidis. It seems that we are a bit out of time, or I'll do my best, let's say that we'll be at the end as close as possible, actually, to the scheduled time. So in this part, we will discuss post-processing methods for fair ranked outputs and recommendations that mainly focus on modifying the output of an algorithm. You can see my next slide, right? Hopefully, yes. We will start with some definitions on fairness in recommender systems. Evie already briefly mentioned some of them. We will see next on fairness in predictions, some calibrated recommendations, how we can define pairwise fairness, and we will pay special attention in fairness in group recommendations. So in this case, we focus on recommendations for groups of users instead of individuals. So we will start with a kind of a measure of consumer side unfairness that looks into the discrepancy between the prediction behavior for protected and unprotected users. Specifically, accuracy-based fairness metrics are proposed that measure the difference between predicted and actual scores, which means the errors in the predictions of the items recommended to the users in the protected group and the items recommended to the users in the non-protected group. The motivation of this first approach comes from the STEM example that has to do with recommendation in education in several domains, science, technology, engineering, and mathematics. And according to some statistics, women accounted for only 18% of the bachelor degrees awarded in computer science. The underrepresentation of women causes historical rating data of computer science courses to be dominated by men. And based on this, the learned model may underestimate women's preferences and can be biased towards men. And this is something that leads to unfairness. So in general, we can consider two forms of underrepresentation: population imbalance and observation bias. In the first case, we have different types of users that occur in the dataset with different frequencies. And when focusing on observation bias, here we have certain types of users that may have different tendencies to rate different types of data items. So, motivated by this example, motivated by the STEM example, there is a matrix factorization approach that defines different ways, provide 5 different definitions for count-to-count unfairness, with the actual goal to minimizing it at the end. So, for example, variable unfairness counts the inconsistency in estimation errors across different user types, leading, for example, to have male students that are recommended STEM courses when they are not interested in STEM, while female students not being recommended even they are interested. In turn, absolute unfairness counts inconsistency in absolute estimation error across user types. In the case of underestimation unfairness, we count inconsistency in how much the predictions underestimate the true ratings, in which case missing recommendations are more critical than extra recommendations. Something similar from the opposite side we have when trying to define the overestimation unfairness, while non-parity unfairness counts the absolute difference between the overall average rating of disadvantaged users and those of advantaged users. So those definitions at the end can be exploited to augment the learning objective of the traditional matrix factorization. And if we would like to say it in the simpler words, what we are doing is to add an extra part in the used formulas. Next, we will see a calibration method based approach to producer side fairness this time. So here a classification algorithm is considered to be well calibrated if the predicted proportions of the groups in the various classes agree with their actual proportions in the input data. So, in analogy, the goal of calibrated recommendations is to reflect the interest of a user in the recommendations and with their appropriate proportions. Intuitively, in this case, the proportion of the different groups of items in the recommendation list should be similar with the corresponding proportion in the history of the user. As an example, consider the case of movies recommendations as the items to be recommended and gender as the protected attribute. For quantifying now the degree of calibration, a list of recommended movies with respect to the user's history of played movies. In this case, in this scenario, in this approach, we consider 2 distributions of the genre of each movie. So we have one distribution over genre of the set of movies in the history of the user and one distribution over genres of the list of movies recommended to the users. To compare those 2 distributions, we can use different ways, like, for example, a distance metric like the Kullback-Leibler divergence that is used as a calibration metric in this case. So KL divergence ensures that the genre that the user rarely played will also be reflected in the recommended list with their corresponding proportion. More or less, this means that it is sensitive to small discrepancies between distribution. It favors more uniform and less extreme distributions. And in the case of perfect calibration, its value is 0. Instead of looking at the scores that the items receive, in this case, in the case of pairwise fairness, we look at the relative position of pairs of items in a list of suggestions. So here we have an accuracy-based approach that is pairwise, where the positive class includes the items that receive positive feedback from the user. That can be clicks, ratings, and so on. So we assume a set of items and the G plus and G minus as the groups of the protected and non-protected items. The pairwise accuracy is based on the probability that a clicked item is ranked above another unclicked item for the same user. And the main idea is to ask that the two groups, G plus and G minus, the protected and not protected, have similar pairwise accuracy. We can also distinguish between intragroup and intergroup fairness. So intragroup pairwise fairness is achieved if the likelihood of a clicked item being ranked above another relevant unclicked item from the same group. And we would like to have this likelihood to be the same independent of the group. In the case of intergroup pairwise fairness, this fairness is achieved if the likelihood of a clicked item being ranked above another relevant unclicked item from the opposite group is the same independent of the group. Next, we are moving to post-processing approaches that in general we can say that are agnostic to the ranking of the recommendation algorithm. So typically they take as input a specific ranking and a specification of the required form of fairness and produce a new one, a new ranking that tries to satisfy the fairness requirements and respect the initial ranking to the extent possible. So what follows, we distinguish between methods that achieves actually fairness via a generative process, those that ensure fairness via constraint optimization problem, and we will also see some calibration methods. And at the end, we will discuss some works that offer multiple outputs, and we will see how fairness can be ensured in these cases as well. So the generative process uses a fairness parameter F that satisfies the desired relative fairness of the two groups, the protected and unprotected. And the process works as follows. We start to beat the new ranking by initializing it to an empty list. For each position in the ranking, we perform a Bernoulli trial with probability F. And if the trial succeeds, we select the best item, the best available item from the protected group. If the trial fails, we select the best available item, in this case from the non-protected group. So when F equals to 1, all items in the protected group precede all items in the non-protected group because the trial always succeeds. In turn, if F equals to 0, we have the opposite scenario, and if F is larger than 0.5, then the items in the protected group are preferred over the items in the non-protected group. So, for example, here, you can see on the left side of the slide the original ranking, and we say we want to rank the original ranking by using F equal to 1, then at each position, the red item succeeds, and we show all red items proceed the blue ones. When F, in the last case, is larger than 0.5, then at each position, the probability of selecting a red item is larger than the probability of selecting a blue one. Next, we have the first R approach that also presents a statistical test for the generative model that, given a ranking, determines the probability that the ranking was generated by the model. That is, here the ranking was generated using the model with parameter F star that is equal to F, or whether the ranking was generated with a parameter smaller than F, which would mean that the protected group is represented less than desired. Next, we will see another post-processing approach that formulates the problem of producing a fair ranking as an optimization problem in this time. So here, we assume that F is a fairness measure for rankings. We also assume that U is a measure of utility, let's say, of a ranking for a particular task. And let's also assume that U R given Q is the relevance of the ranking R for a given specific query Q. There are two general ways of formulating an optimization problem in this case. when involving fairness and utility, and namely, we would like either to maximize fairness subject to a constraint in utility, or maximize utility subject to a constraint in fairness. So, for example, here, in the first case, given the utility definition and the fair ranking definition, we want to re-rank the items so that we maximize the utility, as in the first box, and get a fair ranking. That is, we look for the ranking that has the maximum possible utility among all rankings whose fairness is sufficient. Or in the second case, we may want to specify a different constraint for example, you may want to maximize fairness and also keep the utility of the ranked list as close to the utility of the initial rank as possible, or smaller, like in the formula in this case, than a given threshold. And in this approach has been applied to amortized fairness. Here there is an offline version when in general we can say that it is unlikely that equity of attention can be satisfied in any single ranking. So, for example, as Evie discussed previously, we have a sequence of rankings, row 1 to row m. Multiple items may be similarly relevant for a given query, yet they obviously cannot all occupy the same ranking position. And the sequence of rankings offer amortized equity of attention if each item receives cumulative attention proportional to its cumulative relevance. And in this case, unfairness is defined as the distance between the attention and the utility distributions. There is also the online version where the optimization problem can be solved using linear integer programming. And next, we will discuss calibration methods that suggest to re-rank a list of items as a post-processing step. After the re-ranking phase, here we consider the results as fair if they achieve fair representations. So to determine the optimal I star of n recommended items, items here in this example are movies, the maximum marginal relevance function is used. And the function is the one we can see in this formula here. And the game is between accuracy and calibration, and the fair representation is achieved via a diversity measure. Sorry. In a different line of work, we discuss next how to ensure fairness when we have multiple outputs. So when providing rankings or recommendations, users typically pay more attention to the first position and attention wears off for items in lower position in the ranking, as we discussed also earlier. In a situation where the greatest estimated probabilities are quite close or equal to each other, the algorithm needs to arrange them in a proper order and necessarily present high scores in high position. This promotes an unfair result that can be mitigated in the long term by changing the position in sequential rounds of rankings or recommendations. So, in the case of rankings, one approach is to require that ranked items receive attention that is proportional to their utility in a sequence of rankings, actually. This way, the unfair position one item appears in a single ranking can be compensated in the next rankings when it changes position, and the whole session contemplates long-term fairness. However, the act of reducing unfairness implies reduction in the ranking quality due to the perturbation of the utility-based rankings. And the trade-off between ranking quality and fairness can be formulated as a constraint optimization problem, targeting and minimizing unfairness subject to some constraints on quality. Specifically, in the scenario in which we have a sequence of rankings, row 1 to row m, where the items are ordered by the utility score, the aim is at reordering the rankings so as to minimize the distance between the attention and the utility distribution, with constraints on the NDCG quality loss in each ranking. And at the last part of this presentation, we will focus on group recommenders, where we have suggestions for groups of users instead of single users. So in this case, instead of an individual user requesting recommendations for a system, we have a group of users that make the request. For instance, assume a group of friends that want to watch a movie, and each one has their own likes and dislikes. This means that users in a group can be heterogeneous, and the group can include people with potential different interests and preference. So the system needs, in these cases, to properly balance the difference between preferences, user preferences, and offer to the group a list of data items that has a degree of relevance to each member. And the typical way, the traditional ways for doing so, is to apply a recommendation method to each member individually. So this means that we produce for each user in the group recommendations separately, and then aggregate the separate lists into one for the whole group. For the aggregation phase, when trying to aggregate the separate lists, intuitively for each item, we can calculate, for example, the average score across all users in the group reference scores for the item, and this is the average, the so-called average approach. As an alternative, a well-known approach is the least misery approach, in which instead of the average function, we use the minimum function, and this is how it works. So, following such traditional approaches that in most cases try to maximize the group's overall satisfaction with a recommended list, we can face some problems where one or more users do not like the items in the recommendation list. For example, by using the average method, the opinion of some user, some kind of an outlier user, can be lost. So there is a need for more fair group recommendations. Intuitively, in this scenario, fairness attempts to let's say, minimize the feeling of dissatisfaction within group members in order to ensure fairness on group recommendations. So, one of the first approaches focusing in this problem assumes a measure of quantifying the satisfaction or so-called utility of a user in a group, given a list of suggestions. That is, we would like to know how relevant the key recommended items are to the user. Then the group utility, or the so-called social welfare in this work, averages user utilities, using several ways for doing so. And then for achieving fairness, we need to balance the utilities of the users in the group, and intuitively a list that minimizes the dissatisfaction of any user in the group can be considered as the most fair. Several ways for computing individual utility, as in traditional recommender systems, that is the utility of the satisfaction, let's say, of each individual user in the group. For example, here we can just take the average over the relevant scores of the top K items for the user. In turn, for computing the social welfare, which is the utility for the group, we take the average of the individual utilities, one option for doing so, while for computing fairness, we compute the utilities of the users in the group that exploit, for example, the variance between the utilities, or a kind of average function. And for locating the best suggestions, the goal is to maximize both social welfare and fairness, as does the formula we can see on the top of this slide. And a greedy way for doing so is to select an item, when added to the current recommendation list, achieves the highest fairness. More time-efficient alternatives via integer programming solutions are given in this line of work. So, in the next approach, we have a method that resembles actually the ideas from Skylines. So here, the idea is to represent items in space where each dimension corresponds to a group member, and each coordinate equals the relevance of the item for the user. So here we need to define a dominance relation, and according to it, we say that an item dominates another item for a group if, for each user, the first item ranks at least as good as the second, and there exists at least one user for whom the first item ranks better. So this is very, very similar to the traditional Skylines definition. So here, instead of computing users' individual utilities for a list of recommendations, by summing up the relevant scores of all items in the list, we consider the item positions in the recommendation list. The top items, not dominated actually by any other item, are called Pareto optimal. In turn, we can define the n-level Pareto optimal that contains items dominated by at most n-1 other items. And since it is impractical to identify the exact n-level Pareto items, the authors offer a similar heuristic here that can be used to compile and approximately identify the list of the top n suggestions for the group. So one approximation is to ask for top n prime suggestions for each user, having n prime bigger than n, take the union of the individual suggestions and select the n-level Pareto optimal among the ones in the union. Already very briefly, we mentioned how we can define fairness in the case when the goal is to construct packages for groups. It seems that since we are a bit out of time, I'll skip this session. Okay, and I'd like to present one more solution in which we study recommendations for groups when we have multiple interactions with the system. This means multiple outputs, multiple interactions between the system and the user. So let's assume here in the figure a group of 5 users in a movie recommendation scenario where the group interacts 5 times with the system. As you can see, it's a block of columns represent one interaction. As we can see in this case, here we count the satisfaction score of each user separately in the group. And as we can see, user number 4, I mean the yellow one, has a low satisfaction score in all iterations with almost no interesting recommendations. So this means that the recommender in this case is unfair to the yellow user. And as we can see, unfairness continues throughout all 5 iterations, even in the simple case of the average scenario or when using the least misery for aggregations. The idea is to try to make happier this user, and for doing so, to consider both user satisfaction and user disagreements in the group. For counting satisfaction in the proposed work for each user, we directly compare the user's satisfaction from the group and compute from the group recommendations and compute the average group satisfaction. For counting disagreements within the group, we count in this case the difference in the satisfaction score between the most satisfied and the least satisfied user in the group. So more or less, for computing the importance of the important score that an item can have, we take a weighted combination of the traditional average method and least misery aggregation method. Such a method, such an approach includes a dynamic alpha weight that is different in each iteration and is computed by subtracting. It's something similar to the disagreements case, by subtracting the minimum satisfaction score of the group members in the previous iteration from the maximum score. So in general, the dynamic calculations of alpha, of the weights alpha, counteracts the individual drawbacks of the average and the least misery method. Intuitively, if the group members are equally satisfied in the last round, then alpha takes low values and the aggregation will closely follow that of average, where everyone is treated as equal. And as a kind of a proof of concept, when applying such an idea, we can see that the scores of the yellow user who had a low score, for example, at the first iteration, has better score at the next one. So overall, regarding the post-processing approaches, these methods treat the algorithms for producing rankings and recommendations as, let's say, black boxes without changing actually their inner workings. And as a consequence, they may lead to unpredictable losses in accuracy. We conclude this part with some open challenges. So we are talking about so many different definitions about fairness, but for sure it's a very open question to decide which is the most suitable one and for which context, and also understand how people perceive fairness in different contexts. We have many approaches that operate at different phases of data pipeline. We do not have a clear understanding yet about what combinations can be done so as to have our work working best. We need to understand the dynamics of fairness in more complex systems, find satisfying definitions and frameworks that behave well under composition. Also, again, regarding the dynamics of fairness, it's important to build, let's say, systems that adapt to the changing bias in the data. We don't know how the algorithms dynamically affect their environment. Regarding the dynamics, we had something very interesting and similar as a question in Sihem's talk when talking about particular instances of the data in which we count the bias. And of course, we would like to apply more and more fairness in practice, to check all the different alternatives about how we can evaluate fairness and so on. Thank you so much. Thanks for your time. Sorry we are a bit late, or not that bit at the end. Any questions, please?
Thank you, Kostas. You can turn on your camera also, I think, if you want. And are there any questions for Kostas and in general for all the speakers?
Okay, I think that I have to stop sharing before check the panel of Zoom. All right, thanks.
We have a question from Mrs. Calvi. Ms. Calvi, if you want.
Hi, thank you very much for your presentation. I have a question actually for the three speakers. And I was wondering, are you familiar with impact assessments, data protection impact assessment, algorithmic impact assessment? I am asking because I come from a legal background, And let's say that as legal scholars, sometimes we are, let's say, very much enthusiastic about these tools. The data protection impact assessment was introduced by the General Data Protection Regulation. There is a lot of research about how to apply it also to algorithm and artificial intelligence. There are some discussion also about the artificial intelligence regulation proposal and to which extent it will introduce this form of impact assessment. And I was wondering if it's something that also in the field of computer science is researched or not really. Any comments about that? Thank you.
Yeah, maybe I can start. If I got correctly the question, we have some, for example, here at the Tampere University, we have some discussions between teams coming from different domains, like your domain, law, or with some people coming from the philosophy domain. So what are the difficulties that we met in general is to try to understand what we are trying to say, I mean, between the different domains. So we can spend much time to understand what the philosophy means when saying fairness. And our actual target is to try to translate, let's say, the philosophical definitions of fairness in some mathematics so as to be able to propose and suggest formulas and methods, algorithms that implement those things. At least this is my small experience. I don't know if Evie and Georgia would like to add something, but this is, in my experience, how the process works. Try to understand what each other means and try to translate our understanding in our own domain. This is how we'll handle it.
Thank you very much, Kostas. And since we are a bit tight on time and we have another talk and the group meetings.
Oh, sorry for that.
No. I mean, of course, it's great. And the goal is really to have this active discussions and questions and so on, right? Of course, this is the intention. And so to all the attendees, if you have any questions for the speakers of the tutorial, please contact them also per email or in the chat. I hope, Kostas, you also agree. So Evangelia and Georgia are fine with that.
Yeah.
Okay. So please, let's handle the other questions this way, so we can continue with our schedule. So we have another talk for today, and then of course the working groups. So let's move to the next talk. Sophia, are you online? You can start sharing your screen.
Yes, hello.
Okay, wonderful. So the next talk is a bit more practical. I mean, thus far we heard about the theoretical definitions of fairness, discrimination, pre-processing, in-processing, post-processing, etc. So let's see now a bit of more practical, let's say, experience with a particular tool which Sophia and her team has developed. So this is the AI and equality coding toolbox. So Sophia is a data scientist and the program associate and developer of the Swiss NGO Women at the Table. And Sophia, the floor is yours.
Great. Let me just figure the sharing and...
Yes. Share screen at the bottom. Okay, great.
Okay, are you watching the presentation?
Yes, it's not full screen.
Sorry.
Looks good.
Okay. Thank you for the introduction. I also posted the link in the chat. So if you want to follow along, I have created a Jupyter notebook, but you can find it under iaequalitytoolbox.com/resources. And there you can see the Jupyter notebook. So this AI inequality toolbox was based on the idea of the NGO Women at the Table, and was created in collaboration with the Office of the United Nations High Commissioner for Human Rights and its Women, Human Rights and Gender session. So a little more about my background, but you have already presented. So I finished from the Department of Informatics and Telecommunication, DI, from the University of Athens. And then I did my master's in data science at EPFL in Lausanne in Switzerland. And then during my master's thesis, I developed the practical part and the coding toolbox of the AI inequality. And this is me on the right. So a lot of presenters before said and covered a lot about fairness metrics. So I'll try to be more fast on that. And here we will see just what is a human rights-based approach, and then some of the fairness metrics. And then we will move to the notebook, which is the baseline model, some pre-processing, in-processing, and the post-processing techniques, and how they can be applied, as we saw from the previous presentations. So what is a human rights-based approach? Because by now, and for all this talk, you have been aware of the bias and how it affects every part of our life. So in the Jupyter notebook, we try to investigate how code can be debiased and be improved to support the human rights principles of non-discrimination and equality, which means to protect human rights because all humans are equal, regardless of race, ethnicity, and gender, and all the other factors. About participation, so taking a participatory approach in the design of the technology and AI. And finally, accountability, so about reflecting on one's own position of power. So this is what a human rights-based approach example would look like. So it's about taking a holistic approach to machine learning and to creating a model. So it's about asking from the objectives. So what are we creating? Who are we? What is the purpose? Who are we creating for? And who is using the product and who is not using the product? And who is in the team? Who is designing? So is it just computer scientists, or do we have people from other sections and departments? And then moving to the data. So what data do we have? Who is in the data? How do we collect the data? To the model we select, and finally on the outcome. So we want to translate the human rights into practical steps that are clear and understandable. Because many important decisions that affect human rights are made by data scientists at the early stages of technology development. So you've heard a lot today of what is fairness. And we have seen that fairness is not a technical concept. It's a social concept without a specific definition. And a way to ask fairness is by asking fair to whom? Because fairness is a sociocultural concept that is derived from ethics and political philosophy and refers to different conceptions of justice between individuals. And its application can vary according to cultures, religions, and political systems. So a way to approach fairness is by examining data science and research through the lens of power. So we can ask, so fair to whom, for whom, by whom, and with whose interests and goals. Those questions are called to a basic and ethical design process, and they are taken from the book Data Feminism. So all these different school of thoughts and these different answers to the questions can lead us to all these definitions. And currently there are 21 at least technical and mathematical. So for our practice session, we will focus on 3 fairness metrics. And as we see before, we separate them into group fairness and individual fairness. So just a reminder, group fairness is when we separate the world into groups, and then we want the classifier to be equal across these groups. So in our example, we will have the world separated with males and females. Individual fairness means that similar individuals should be treated similarly. So for the group fairness, we will see demographic parity that was explained also in the first talk by Professor Thun, and also in the previous presentation. And so this means that the acceptance rates of the 2 groups should be equal. And then we will also see equalized odds. So the probability of an applicant, for example, being hired and the probability of another applicant not being hired should be the same for the 2 groups. And then for the individual fairness, we will use generalized entropy index. So this measure was derived from economics and was used and proposed as a measure of income inequality in a population. And it's generally derived from information theory. So we already saw that we can't satisfy all the metrics at once. First, some notions of fairness are mutually incompatible and they cannot be satisfied simultaneously. So as a result, there is no single universal metric for quantifying fairness that can be applied to all machine learning problems. And this suggests that fairness is highly contextual for any given machine learning problem. And we saw the trade-off between group fairness and individual fairness, because fairness metrics usually either emphasize on individual or group fairness, but they fail to combine both. And many approaches to group fairness often tackle the between group issues, for example, between males and females, but this can in fact increase the within group unfairness, so between the members of the same group. So we can have, for example, be reducing this between group unfairness, but in fact increase the individual unfairness. And then we already saw that demographic parity and equalized odds are very different definitions and they cancel each other. And you can find also more information on that from the previous talk and also on the notebook. So again, we saw that fairness is complex and the discussion about fairness is a complicated one because first, fairness is highly contextual and there is no one size that fits all. It's not one single metric. Secondly, there are no set answers and often cost and benefit decisions have to be made. So we already saw in the first presentation about the trade-off between fairness and accuracy. So besides from quantitative definitions of fairness allow it to become an additional performance metric in the evaluation of the machine learning model and algorithm. However, increasing fairness can often result in a lower accuracy or related metrics. And finally, fairness is a process. The implication of a metric, it could imply that it's a straightforward process. But fairness can be seen as an investigative process that requires detection, explanation, and mitigation. There is no single fairness checkpoint, and harmful properties can enter our system through biased data and through the data science practices and decisions. And we saw a bit, and we saw the image before about what a human rights-based approach would look like in this pipeline. So all these questions and all these decisions that are being taken. Okay, so now let's move to the model. So for everyone who is following the notebook, this is in part A, baseline model. So in this session, we will start with a simple model that I created a simple logistic regression model, and we'll see how it performs on the previous metrics. And we have seen that bias can be introduced into an AI system at any stage of the development process, from the data you collect, the way you collect it, to the algorithms you are using. And by asking the right questions upfront and during application design, we can prevent many of these biases. So here and in the notebook, the majority of questions comes from datasets for dataset by Timur Gibru and her team. That includes the questions about the data. And then model cards for model reporting by Margaret Missel and al. That are the questions that are about the model. And there are many other different guidelines, like the ethics guidelines for trustworthy AI by the EU, and many other approaches to asking these questions. So let's first introduce our example. I'm using snapshots of the notebook. So here we will use the German credit dataset. It's from 1904, and it's a commonly used dataset for supervised classification tasks and fairness metrics. So it's an old dataset without the GDPR. So we see that we have all the information available about sex, age, foreign worker. It's a rather small dataset. It has 1,000 entries, and each entry is a person who applied for a loan. So each person is classified as a good or a bad credit risk according to a set of attributes. And for each observation, we have 20 variables, including demographic information like age, gender, or even marital status, and financial information, so savings, credit history, assets, and then the decision outcome. So here, the protected attribute is sex, and male is the privileged and female is the unprivileged. So in terms of simplicity, we are focusing on one group. However, we know that we don't have one identity, and we're not focusing on the intersectionality, which is another challenge that we saw from the previous talks. And also, yes, and here in our case, gender is binary, although we know that gender is not binary. So even before we start to touch the data, we should question the origin and the motivation of our data. So we can start. So why was this data set created? And we know that this specific data set was also called StatLog. It was the subject of the databases that was used in a European StatLog project. And also, what was the purpose this data set was created for? And were there tasks that the dataset should not be used? We know that, and it's documented in the UCI repository that this was taken from, that the purpose was to compare the performance of machine learning and statistical models on a set from real-world industrial areas. So another example of the purpose is, we can see it from another famous data set for face recognition, which is called label faces in the wild. So the label faces in the wild data set was created to provide images that can be used to study face recognition in an unconstrained setting. So where we couldn't control for demographics or appearance. So for example, this type of data set could be used for a face identification problem, but it shouldn't be used for tasks that are high stakes. And then we also ask who created the data set and who funded this creation of the data set. So it's important to ask these questions because about funding, for example, there is the source of bias called funding bias. And we have funding bias where when biased results are being reported in order to support or satisfy the research and the funding agency. And then how can the owner of the data set be contacted? And we already have actually this information. It's already in the UCI machine learning repository, and it has the contact details of the professor who donated this data set. So now let's see what we have in our data. we are going to do some exploratory data analysis. And we ask, so who is in the data? What's missing? What's being overgeneralized? What's being overrepresented and underrepresented? And how do the values and the variables reflect the real world? So the real world as it was in Germany in '94. And what might we be leaving out? So starting to separate our data by gender, we see that our dataset is very imbalanced. Males overrepresent the females with a ratio almost 7:3. So we see that it's very imbalanced, and if we don't take any actions, this will affect our model. And then we try and dig in more and understand our data set. So here we see how age plays out with respect to the gender. And we see that the median of women who ask for a loan is 29 compared to men who are 35. So we have like 6 years of age difference. And we can already assume that, okay, age could be playing a role, and the younger you are, maybe the less financially stable you are in order to receive a loan. So we are following this thought, and we plot again the age and the gender with our target variable, which is the credit score. And as we see from in the second plot, as we see from the green curve, so the bad credit score is related to the younger ages. Also, as we try to understand more our data, we need to see, so why are people getting a loan? And this is the information that is in our data set. It doesn't tell us much, but what happens if we break it down by gender? So here, it's interesting to notice in the second plot that in most categories, there aren't many big differences between males and females. However, in categories with bigger differences, women tend to ask more for loans for education and home equipment, while men ask more for business purposes and used cars. And here we have, again, this is not sex separated, but we see again the purpose with the target variable. And we see that education is more likely to receive a negative and a bad credit. So in general, this type of analysis can go on and on until we have a good understanding of our data and its limitations. So now let's move to the model. So for the purpose of this example, I created a simple logistic regression model to use as a baseline, and then to see how it performs on the different metrics. So I chose this model because it's easier to interpret. And here we have the confusion matrix. So while evaluating the overall performance of a model can give us some insight about its quality, it doesn't give us much insight about how well our model performs on different subgroups. So it's important to determine not just about how many correct scores they have, but also about the different types of errors. And then a tool to use that is the confusion matrix. So I guess most of you are familiar with the confusion matrix, but for those who are not, so a confusion matrix is a grid that plots predictions that it's on the x-axis versus the ground truth of the model. And then we have these statistics in a tabular that summarizes how often our model made the correct prediction and how often it made the wrong prediction. So from this table, we are also getting some secondary measures. The first one is accuracy, and then we also have precision. Precision, also called positive predictive value, is the fraction of positive cases that was correctly predicted to be in the positive class out of all the predicted positive cases. So in our example, it is the probability of an applicant with a good predicted credit score to actually have a good credit score. A recall is another metric, and it's also known as true positive rate. It represents the probability of a truly positive subject to be identified as such. So in our example, it is the probability of an applicant with a good credit score to be correctly assigned with such a score. So using the default parameters, we see that the model performs better for males than females. So specifically, we find that in all the metrics, so accuracy, recall, and precision, our model performs better for males than females. So of course, one of the reasons is the very imbalanced data that we have. So in our work, it's important to make a good decision based on the trade-offs between the false positives, false negatives, true positives, and true negatives. And as a takeaway, it's important to evaluate a model performance across all the subgroups than in aggregate. So now let's move on the pre-processing and on the data. So we already saw some examples before, and we will focus on where's the bias in the data and what we can do. And a lot of times, a lot of us data scientists have heard that data doesn't lie or that data beats opinion. But bias in the data can exist in many shapes and forms, and some of them can lead to unfairness in the following learning tasks. So technology as data is not neutral, and it reflects the social beliefs, values, and biases of the designers. So this is the world according to our data. So this is our data set, the 100 applicants. This is taken as a sample from the world as it is, or at least the world as it was in Germany in '94. And between the world as it is and the world according to our data, we have the statistical bias. So statistical bias is a systematic mismatch between the sample that were used to train the predictive model and the world as it currently is. Sampling bias occurs when a data set is not representative of the full population to which the resulting model will be applied. But even if our training data was representative and accurate, then our world, unfortunately, it's not. So here at the top, we have the world as it should and it could be, fair and equal to everyone. And between this and our data set, we have what we're calling societal bias, that includes structural bias, historical bias, and all of these different types of biases. So in our current example, our data set could suffer from societal bias if some people, for example, women, systematically received lower wages. So we already saw some pre-processing techniques. And in general, the pre-processing techniques alter the sample distribution of the protected variables to perform some transformation on the training data. And the main idea is to train the model on the repair data set. So data pre-processing techniques is argued to be one of the most flexible in the data science pipeline because it makes no assumptions of the modeling technique. In general, addressing issues of societal bias may include adjusting data collection, so if we can have more samples, or manually incorporating an understanding of this bias into the model building process. Or sometimes problems related to social bias may not have a technical solution at all. So for example, we know that women apply for a job if they meet 100% of the job requirements, whereas men only apply for the job if they meet 60% of the job requirements. So just by changing the way a job description is, you can have more women applying to it, and then better data, and then more inclusive data. So now we will use the reweighting algorithm. It was also presented in the previous talk. So reweighting is a pre-processing technique that weights the example in its group by showing a different combination directly to ensure fairness before classification. So when we compare the accuracy, we see that we have a slight decrease from the baseline model, but it's still very high. And here we see how it performs on the metrics that we saw before. So accuracy, recall, and precision. And we see that our model performs very well and has improved a lot on the recall. So I remind you that recall is the probability of an applicant with a good credit score to be correctly assigned with such a score. So we see a huge increase if we use this method. So now we will see how this algorithm improved on the fairness metrics we defined before. So again, we have the statistical parity and the equal opportunity, which are the group fairness methods, and then the generalized entropy, which is the individual fairness method. And we compare in each plot. First, we have the baseline model, and then the improved model using the reweighting technique. And again, we saw that our model performs much better in the group fairness metrics, so in the statistical parity and the equal opportunity. And we see this trade-off between the group fairness and the individual fairness, because here it slightly got worse. So the in-processing part C in the notebook. We saw that bias does not only come from the training data, it can also be introduced with inappropriate data handling or as a result of an inappropriate model selection or an incorrect algorithm design or application. So there are different types of bias that can enter in our model, and it has to do about the choices. So the choices for building a model. These include the class of the model, the functional form, the model parameters, among others. And all of these choices can have a ramification for fairness. Then it's about interpretability. Simpler models can help humans understand the basis in which upon a decision was being made. And this can facilitate a normative debate about the legitimacy of that basis. So the disclosure of such details is often essential in the decision-making process. And then we also have feature bias, which is the covariates. So outcome predictions can change depending on what we condition on. So for example, one person A can have a higher predicted value than a person B with a choice of some covariates, but a lower predicted value with a choice of another set of covariates. In the notebook, I'm also using questions from model cards from model reporting. They separate the questions into the model, the choice of the model, and then in the choice of the evaluation metrics that we are using in our model. So we saw that we have accuracy, fairness, the different types of these measures. However, there are other evaluation methods, and it's important to validate these methods. So for example, the metric we choose can introduce an evaluation bias. For example, the IJBA benchmark dataset that was used to evaluate facial recognition system was proven to be biased towards skin color and gender. So even if you build your model perfectly, when you evaluate it on this biased benchmark, then your model is not correct. So some in-processing techniques. In general, an ethical decision-making process might require, among others, the ability to explain a prediction or a decision, which is not feasible with black box models. And we saw that before that many in-processing approaches use on modifying the learning algorithm and some of them trying to find a balance between multiple model objectives. So for example, having a model which is both accurate and fair. And some of these approaches deal by incorporating one or more of fairness metrics in the model optimization function and converts to a model parameterization that maximizes both performance and fairness. So in the notebook, we used the meta-classification algorithm. This algorithm takes the fairness metric as part of the input and returns a classifier optimized with respect to that fairness metric. So we see here a big difference in the accuracy of the model and a big decrease. And then again, we analyze the model using our matrix, our confusion matrix and the metrics. And here again, we don't see that improvement that we saw on the previous example. And this is more obvious when we are using the group fairness metrics. So we see that it's hard and it's practically hard to optimize both for accuracy and fairness. And although in all of the cases it has improved, it's not that much different than before. So the last part is about post-processing. So where can the bias come when we are making decisions? So when we are using the predictions of our model, we are making three main assumptions. So first, all these decisions are evaluated as an aggregation of separately evaluated individual decisions. So this includes that we assume that the outcomes are not affected by the decision of others, an assumption that is known as non-interference. So in this loan setting, denying one family member a loan could have a direct impact in another family's member ability to repay the loan. And this is not captured in the data. Secondly, all individuals are considered symmetrically. So this assumes, for example, that the harm of denying someone a loan to someone who could repay it is equal across people. But denying someone a loan for education would likely have a very different impact in their life than denying a different person a similarly sized loan for a vacation home. And finally, these decisions are evaluated simultaneously. So they are evaluated in a batch as opposed to serially, and they do not consider potentially important temporal dynamics. So on the post-processing techniques, the post-processing approaches tend to apply a transformation to the model output to improve the prediction fairness. And again, as we saw in the pre-processing, post-processing is one of the most flexible approaches because it only needs access to the prediction and the sensitive attribute information. And it doesn't require much access to the actual algorithm or the machine learning model. And this makes them applicable for black box scenario where the entire machine learning pipeline is not exposed. So in our last approach, we are using the calibrated equalized odds algorithm. It's a post-processing technique that optimizes over calibrated classifier score outputs to find probabilities with which to change the output label to an equalized odds objective. Again, we see that our accuracy is reduced a bit, but we see that here it even performs better in the recall for the females. And in general, it reaches a very high level of recall. And again, when we plot the overall metrics all together, we see that improvement between the very big improvement between the group fairness and then how it's slightly decreased in the individual fairness metric. So some key takeaways is that, as we've shown before and all day today, that fairness is complex because the world is very complex and contextual, and it's a process. We need to take a holistic approach to human rights in the context of coding, and then try to translate and create this into practical steps. It's important to understand the historical, social, and cultural concept of who is using the tools and how the use are being created. And it's And it's important to keep asking questions. So at every step, at every decision that we are making, and also documenting that decision. So then we can trace back and go back and try to improve what we've learned. And we also saw some bias and mitigation techniques in data model and prediction. However, as tempting as it looks to solve complicated issues with data, most complex real-world problems require complex real-world solutions. And this is from the UN High Commissioner of Human Rights. So in order to respect human rights, we must ensure that this digital revolution is serving the people, and to ensure that every process is made with the principle of transparency, fairness, accountability. So thank you. I hope you are not very tired, and feel free to contact and visit the website.
Thank you very much, Sophia. Are there any questions? Actually, I see one question by Alla. Alla, please go on.
Hi, Sophia. Thank you very much for the lovely talk. I wanted to ask, at the beginning of your talk, you mentioned that multiple fairness metrics cannot be satisfied at the same time. So I was wondering, what's the decision process that is taken to choose to satisfy some fairness metrics over others?
It's about what the goal, what do we want to achieve? And it's about, again, asking, so what is the final goal? What are the measures? What are the, what do we want to achieve with the model? Who will be using it? By also asking fair to whom we want to make the model.
But I feel like at the end of the day, you'll have to compromise, like in case some of the fairness metrics contradict each other. So I was wondering, like, how could that be addressed, such an issue?
Everything is about decisions. So every decision that you make in the pipeline has a social impact. So that's why it's important to document and to be able to defend why you made that decision and why you chose that. So it's not that there is the answer. It depends.
That's true. And also I was wondering, for the case of like, if you're trying to address discrimination for gender, for example, like also, are you supposed to look at the other sensitive attributes as well?
Ideally, yes, because we don't have just one identity. And it's important to also talk about intersectionality. And it's not men and women that they are one homogeneous group. So we all have these different identities, and it will be important that next approaches also focus on more groups and subgroups.
Okay, thank you very much.
Thank you, Alla. Any other question? There was one by Ellie and Alessandra. So I don't know in which order. So I hope it's okay if we start, for example, with Ellie first.
Okay, since I am muted also, hi. Thanks so much for the lovely presentation. You mentioned at the beginning about data sheets for data sets. And I know that in the European Commission, there is a huge movement trying to, with data management plans, to document all the processes and how we have handled our data sets during a project, from the collection side of things, identifying, writing down the scope, the utility of the data, and so on. There are in the data management plans, which is something similar, but it's not targeted to machine learning. So data sets, it's more on the side of machine learning, as I understand it. For data management plans, there is a standard, let's say, structure and questions that are asked. Is it the same with the data sheets? Is it something standardized that can be used? Or is it something that is ongoing it's under development? It's not standardized yet. So we don't know, for example, we don't have a minimum set of questions that we can ask.
I'm not familiar with the standards that you mentioned now. I just know about datasets for datasets, and it also says that it's just a guideline of a set of questions. So everything needs to be expanded and adjusted to the dataset that you're using, and on the problem you're trying to solve, and the data you're using, and where you used it, and where you collected it. So yes, context is key, and everything has to be adjusted. But I think some of the main questions is also about consent, privacy, and who is in your data, and are people being represented there?
Thank you very much. I'll also add some links in the chat in case it's of interest. Thanks.
Yes, Alessandra, please.
Thank you. So, hi, Sophia. Thank you very much for your presentation. I was wondering if you have, if you could elaborate a little bit more about public participation and your experience with that, the challenges you have faced, something like that. Thank you.
Thank you. So I would say that participation can come in many different terms and in many different stages. So it's also when you design your product, so for whom you're designing to. So also having the end users ideally participate in the design, but also having a more interdisciplinary approach into the design. So not only data scientists, because we don't have all the answers, of course, but also creating projects with lawyers and social scientists. I mean, I have limited experience, but most of my approaches were just, you have this data set, you have this task, do it. So not very open to other approaches, other discussions. And it will be, I mean, it's very interesting because every disciplinary and every section has something to answer and has something to give a different approach to this question. So even reconsidering what is accurate.
Thank you.
Great. I don't see any other question. So maybe just to mention that again, Sophia also shared the notebook, so you can actually experiment by yourselves with all the methods and this reflective process, right? Sophia, I see it as a reflective process on the different choices, decisions that we make during this data science pipeline, from the data to the pre-processing, algorithms, evaluation, etc. So it's really important to kind of question and reflect on our decisions, what is their impact, etc. And I think it would be great actually if you try your favorite data set or a data set in which we are working on using, let's say, this methodology that Sophia explained, and you can actually find the code in the notebook, and maybe of course you can contact Sophia with insights and feedback, etc. Right, Sophia? You would love that probably, right?
Yes, yes.
Okay. Great, super. Thank you, Sophia. And we are done with the talks and presentations today. So it's now time for the group works, right? So we have now a dedicated slot for the group work. So you will be redirected in the different breakout rooms depending on the group in which you are assigned. And you know what you have to do, so hopefully you got more inspiration from the different talks and more insights. And since in these groups we have people from different backgrounds, so the majority is of course computer scientists, maybe it's a good idea to kind of put in practice the question that was asked before, right? So how we work together with our different background, expertises, experiences, etc., right? So maybe this is a good idea for the group work. And with that, we are done for today. So thank you very much for attending, and to all the speakers, of course. And we are looking forward to welcome you also tomorrow. So we start at 9, and have a nice afternoon. At least in Europe, it's afternoon, right? Yes. So that's all from our side. If there are any I don't know, questions, etc., of course, you can post that in the chat or you can raise your hand. But in principle, it's now time actually to switch to the group works, to the working groups. And this is the part that is not live streamed. So that's all from my side and from the organizational, let's say, point of view.
Okay, I'm creating the rooms. Goodbye all. Have a nice afternoon. Technology.